Hi everyone. So now we are going to study common source amplifier. So previously we have seen in which region we have to bias the MOSFET to make it work as an amplifier. So that is saturation region. Now we will assume the biasing is such that it is working in saturation region only. When there is a particular question given in front of you, you will not have to find whether it is working in saturation region or not. They will write down that it is working in saturation region only. Now we are going to study common source amplifier. So you have to assume that this VDD, and this Vin is such that your MOSFET is working in saturation region only. So every time I will not write it, although here I will write MOS is working in saturation region. MOS is biased. MOS is biased such that it is working in saturation region. No matter whatever we study, common source amplifier, different configuration of common source amplifier, common drain amplifier, common gate amplifier, cascode amplifier, every amplifier, in every amplifier, MOSFET is biased in saturation region. Okay, is working in saturation region. So this we have to assume only every time. Now what is V in here? V in is VGG DC bias plus AC signal, Vm sin omega t, right? This we can call DC signal plus small signal AC signal, right? Now we will analyze this amplifier. Why it is called common source amplifier? What is the property of common source amplifier? We shouldn't say property, but how do you get to know if it is common source amplifier? So common source amplifier simply means input is at gate, and output you are collecting at drain. That's it. This is common source amplifier. Input at gate, output at drain. That's it. Nothing that source is common, nothing like that. Input is at gate, output is at drain. That's it. This is known as common source amplifier. So now we will do the small signal analysis. We will not do the DC analysis here. Why? Because we have already seen the DC analysis in assignment number 4. In assignment number 4, we solved many questions like what value should be what will be the value of RD to make it work in saturation region. So why did we do that there? So that you could understand how you can make the amplifier work in saturation region. So now we have done the DC analysis. We have seen the DC analysis question. We have write down the current ID equals to mu n CX WIL VGS minus VT whole square by 2. That we have already seen. DC analysis we have already seen. Now we are going to do small signal analysis only. Small signal analysis means, what do you mean by small signal analysis? AC analysis. So now we are going to do AC analysis only, or you can say small signal analysis. So we will be focusing on small signal analysis only. Small signal analysis or AC analysis you can write. So what different we do in small signal analysis? What will happen? The DC will be shorted. So this VDD will be shorted. VDD will be shorted. Then directly RD is connected. RD is connected. Then directly MOS is connected. This is the MOS which is connected. Source is common already. Now tell me at the input what you will get. Capital VI or small vi? Small vi. Why so? Because VGG is also shorted. This is also DC. So VGG is also shorted. So only small vi you are getting. And this is also your small signal output. We are not collecting DC output. We are not talking about DC. Only AC output we are talking about. Everything is AC here. So AC we are talking about, right? VDD is shorted. So everything is AC now. So what did I tell you? How to solve these problems? What we will do? Let's remove this V naught. So we know that there will be some R naught connected between drain and source. So this is the R naught which is connected, and this is our V naught. What will be the current here? This R naught should be a bit here. I should put R naught. Tell me what will be the current here? What should be the current? GMVI, right? VGS, GM into VGS. The current is GMVI. That's it, right? Now what you can see, there is GMVI current here. From V0 to ground you see two resistance RD. From V0 to ground you see R0. So GMVI, and from V0 to ground you see two resistance RD and R0. Are you getting this point? So can you replace this something like this? that there is this GMVI current flowing. So from V0 to ground, GMVI current is flowing. From V0 to ground, GMVI current is flowing. This is small vi, okay? This is small vi. From V0 to ground, GMVI current is flowing. And from V0 to ground, you are having R0 resistance and RD resistance. So R0 parallel with RD. And this is your V0. Now this GMVI current is flowing from R0 parallel with RD. This GMVI current is flowing like this, R0 parallel with RD. So what will be your V0? V0 will simply be minus GMVI into RD parallel R0. So what will be your V0 by Vi? All of these are small signal. All of these are small signal. We are finding small signal gain actually. So V0 by Vi would be minus GM RD parallel R0. That's it. This is what is called small signal gain. Small signal gain. Small signal gain. V0 by Vi we found. V0 by Vi. What did we do? GMVI current is flowing. That current is flowing from RD parallel R0. That's it. That current is flowing from. Then we wrote down the value of V0. V0 by Vi minus GM RD parallel R0. So this was the first thing that we found, that is small signal gain. Second thing they can ask is small signal output resistance. Small signal output resistance. They can ask this thing. So they will just make this diagram. They will make this diagram because we are talking about small signal. So everything here will be small signal. So they will make this diagram. They will not give you this. And they will ask you what is the resistance seen from here. This is known as small signal output resistance R0. This is what they can ask. What you will do? What did I tell you? How to find the resistance? How to find a port resistance? What did I tell you? Short circuit or open circuit basically nullify the independent sources. Nullify the independent sources. What is the independent source? V in. V in is the independent source. Nullify this. So V in will be shorted. Is there any other source? No. VDD is already shorted. VGG is also already shorted because that is DC. VDD and VGG are already shorted because they are DC. And now small signal V in is also shorted because that is an independent source. So V in is also shorted. Now tell me what is the current here? What is the current here? 0 ampere, right? The current is 0 ampere because VGS is gone. VGS is 0. Gate to source voltage is 0. Current is GM VGS. VGS is gone, so current is 0 ampere. So simply this MOS will be open circuited. That's it. So there is no use of this MOS. So from V0 to ground, what do you see? From V0 to ground, what do you see? From V0 to ground, you see RD parallel with R0. That's it. This is your V0. What did you do? You short circuited the input voltage. So if input is gone, VGS is gone. So MOS is replaced with the open circuit. So from V0 to ground, you see RD. From V0 to ground, you see R0. So from V0 to ground, you see RD parallel R0. And from here, you need to tell the resistance. So what is your output resistance? That is RD parallel R0. That's it. Now the second thing they can ask you is the current gain. Not the second thing, actually it is the third thing. Third they can ask you is the current gain. So what do you mean by current gain? This is your I in, and where will be your I out? So for I out, I should make this ahead. So this will be your I out. or in the opposite direction it can be. They will give the arrow. It's not that they will ask you what is the current gain. They will give the arrow whether they want I out to be in this direction, from right to left or left to right. So we are assuming from from right to left. What will be your current gain? Tell me. What is your I in? You already know it is 0 ampere. So no matter whatever the I naught is, the current gain will be current gain. That is I naught by I in. We already know what is I in. I in is 0. So current gain will be infinity. This is shown as AI. Current gain will be infinity. So no matter whatever the direction we give, we always know for a common source amplifier the current gain is infinity. For a common source amplifier, current gain is infinity because input is applied at gate. If input is applied at gate, then input current is 0. If input current is 0, that means the gain will be infinity. What was the output resistance? RD parallel R naught. You don't need to mug it up. You will, okay, simply remember input is applied at gate. If input is applied at gate, VGS is shorted. So there is no current in the MOS. So only RD parallel R naught will come. That's it. What was the gain? Gain you will also remember. How? GMVI current is flowing. So that GMVI current will be flowing in RD and R naught. So RD parallel R naught, the GMVI current will be flowing. So gain will be minus GM RD parallel R naught. That's it. Well and good. Now one more thing they can ask, that is input resistance. This is all small signal output resistance. This is also small signal current gain. This is also small signal input resistance. So I should write small signal current gain. All are small signal only. Small signal current gain. This will be small signal input resistance. Tell me what should be the small signal input resistance. You can draw the circuit once again. So here you need to find Rin. What you will do, you will apply a Vx and get Ix out of it. Your Rin would be Vx by Ix. Forget about Vx. I know one thing, that my Ix is 0. So my Rin would be infinity only. My Rin would be infinity. For a common source amplifier, input impedance is infinity. Input impedance is infinity. And output impedance is RD parallel R naught. So low input impedance and high output impedance. Well and good. Understood? For a common source amplifier, input impedance is infinity because current is 0. That's it. Now, what is the problem with the common source amplifier? So what was the gain of common source amplifier? Our target for using the MOSFET, our target was to get a higher gain. We got a higher gain because this R naught value is very high actually, and RD value we can also set high. So this RD parallel R naught we can get high gain. But what is the issue? Let's check that out. So the gain we are getting is minus GM RD parallel R naught. You can see, because assuming that here lambda is 0. This we are assuming. So if lambda is 0, that means R naught is infinity. So if R naught is infinity, that means R naught parallel RD will be infinity parallel RD. And what is infinity parallel RD? That is RD only. So this is what we are assuming. So we are assuming here, or you can say RD parallel R naught as well. So there is no issue with that. The issue is with GM. So what is GM? GM is root 2 mu n cu x w by L ID. There were how many formulas of GM? 3 formulas. What was those formula? One was very straightforward, mu n cu x w by L VGS minus VT. What was the second one? 2ID VGS minus VT. 2ID upon VGS minus VT. That was the second formula. What is the third formula? Root 2 mu n cu x w by L into ID. And this RD is there. So now this is your AV, right? This is your gain. Now your gain is the function of ID, and your ID is the function of temperature. So if the temperature changes, your ID will change, and your ID will, if ID changes, then your gain will change, and this is not what you want. You want a constant gain. It's not that at some time my mic will be giving you this much of amplification and at some time it is giving you this much of amplification. Are you getting this point? You want a constant sound. It's not that at some time you are getting high sound and at some time you are getting low sound, then medium sound. You want a constant gain. Let's just assume because of some temperature my ID rises here. In this one, my ID rises. So what will happen? If ID rises, then this gain will rise. And if the gain rises, then you will hear a higher sound. And because of temperature, if ID gets low, then you will hear a lower sound. And this is what not you want. You want a constant sound. So the problem is that dependence on ID. Are you getting this point? So you are not getting a constant gain. So this is the problem. And what else we can say? Yeah, I hope you are remembering the formula of GM because that is very important, right? So basically your function is, your AV is depending on temperature, and this is not you want. So because of temperature change, the gain can change. And this is not desirable. Yeah, one more thing I wanted to ask you. What is this ID? Small signal or large signal? What is this ID? Small or large? Large signal, right? Because I told you GM is a DC parameter. GM is a DC parameter. When you find GM, what formula did you use? ID equals to mu n CXW by L VGS minus VT whole square. Then using this formula only you go to this formula. So ID is DC here. That is the DC current. And one more thing you have to remember here is that with the increase in temperature, ID increases. How did you come up to this? That we will study in device physics. You don't need to understand here because that will take around 30 to 35 minutes. If ID increases, sorry, if temperature increases, ID increases. That you need to remember. What if someone asks you? But that is very rare. No one will ask you these things. But just for your reference, ID is proportional to the temperature. If temperature increases, ID increases. Okay. So that is the problem. Now, how we will eradicate this problem? That is the thing. So this is how we are eradicating this problem. We are using a diode connected load. Here, what we were using? We were using a RD value. Now, instead of RD, we are using this configuration. So what changes it will bring? Let's check that out. This is known as diode connected load. Okay, let's not. What should we do? Okay, I should make a line like this. This is diode connected load. No need to do the DC analysis because we know using the DC parameters only, using the DC biasing only, MOSFET is working in saturation region only. So we are not doing the DC analysis. We will only do the small signal AC analysis. Small signal AC analysis. Small signal. Let's do it on next page only. Small signal analysis or AC analysis, you can say. So let's copy this circuit. So if you are doing the small signal analysis, what will happen? VDD will be shorted. This VDD will be shorted. And in the input, you are having only the small signal. You are only having the small signal. For now, I am assuming. Assuming lambda is equals to 0. This is what I am assuming for now. Tell me one thing. What will be the current in M2? What is the current in M1? Tell me. That is GMVI. That's it. GM1 VI. GM1 VI. Small signal it is, so I am writing GM1 VI. What will be the current in M2? What will be the current in M2? What is the VGS of M2? VGS of M2. VGS of M2. That is 0 minus V naught. Right? So what will be the current? Minus GMV naught. Right? Minus GMV naught. Or you can say in the upward direction GMV naught. Are you getting this point? Let's just see, this is a MOS. Here the potential is A, here the potential is B. If I am writing the current in the downward direction, if I am going this way, so I will write GM A minus B. And if I am writing the current in upward direction, what I will write? GM B minus A. Are you getting this point? This is happening only for small signal. This is small signal current. Everything is small signal here, not large signal. You can't say, sir, from source to drain the current will not flow. That is the case in case of large signal. In case of large signal, drain to source only current will flow. But in small signal, the current is very small, so it can flow from source to drain as well. So you will not think, sir, how the current is flowing from source to drain. It can flow because this is a small signal. In actual, there is a large signal current. Let's assume there will be some 2 milliampere current that is already flowing from up to down. That is large signal current. And this small signal current GMB minus A, that will be some 2 microampere. So that will not affect our DC operating point. This point I have already explained to you. So small signal current can flow from down to up or up to down. You don't need to think that MOSFET will be turned off. Turning on MOSFET or turning off MOSFET depends on DC biasing, not on AC. Turning on MOSFET or turning off the MOSFET depends on the DC biasing, not on AC. So in case of AC analysis, we don't need to think whether the MOSFET is on or off, because that we have already seen in the DC bias. We have made the DC bias such that the MOSFET is on and it is working in saturation region. Now there is very small signal. So because of this small signal, our DC bias is not getting affected. Are you understanding this point? Are you connecting this point? Right? So current in upward direction will be, we are going from upward direction, so from lower node to this node we will go, upward direction. So GMV node, in upward direction we are having GMV node current. Right? In upward direction we are having GMV node current. So in both M1 and M2 same current is flowing because lambda is 0. There is no R not connected. So both in M1 and M2 same current is flowing. Right? In M1 and M2 are having same current. That means this is GM2. That means GM1 VI is equals to minus GM2 V naught. That's it. So what is your value of V naught by VI? That is minus GM1 by GM2. This is your small signal gain. This is your small signal gain. Now what did you understand here? Let's write down this gain once again. Your gain is minus GM1 by GM2. What will be your GM1? That will be 2 mu n COX W by L ID1 divided by root 2 mu n COX W by L ID2 AV. Also this can vary because GM1 is for transistor M1 and this is for transistor M2. So mu n COX W by L can vary actually. It's not that mu and Cx will vary because they are constant parameter, almost constant. They are also not constant. That is very in depth of device physics. No one will ask you this. But mu and Cx you can consider they are constant parameters, but W by L can change. This can have higher W by L. This can have lower W by L. So W by L can change. Width and length you can change. Mu n is the mobility that is constant for an electron. Even Cx is constant. So W by L can change. So this is the gain. Now here what do you see in this circuit? The ID current. What is ID current? Large signal DC current. ID is DC current. So here what you can see, ID1 is equals to ID2 because complete MOSFET will be having the same current. ID1 is equals to ID2 is equals to ID. Look here, the large signal DC current is same, is equals to ID. So what do you get? Your AV is only depending on W by L. That's it. And W by L is on your hand. You can change W by L. You can keep any value of W by L you want. Are you getting this point? ID1 was depending on temperature, but W by L doesn't depend on temperature. W by L is not a function of anything, right? So this here you are getting constant gain, and this is what we wanted, constant gain. So we wanted a constant gain, and by using this diode connected load, we have achieved this. What did we do? We used the diode connected load. What did we get to know? That the current will be GMV0 upward direction, GMV lower direction. So here we have got the gain. And if GM2 and GM1 are equal, the gain would be 1 only. That's it. Now write down the gain for this configuration considering lambda is not equals to 0, right? Considering there is some R0. So we will write down the gain. We will also find many other things. We will find that input resistance, output resistance, everything we will find. So now we are going to write the gain considering that lambda is not equals to 0. That means R0 is available. Mole signal. Why is this lagging? Mole signal gain started lagging again. Okay, I will have to pause the video. Yeah, actually it started lagging. Now it is working fine, I guess. So what was our circuit? This is our output. This is our output. Here we will be having R0 2, right? R0 1. This is M1 and this is M2. So here we are having R0 1. This is VDD. This is VDD, which is grounded. VDD is grounded. Here you can see which is grounded. Now between drain to source you are having R0 1. Here what you will have? This is also grounded because VDD were connected here at both of the sides. So both VDD are grounded. Now between source to drain you will have R0 2 as well. But this is source, this is source. What is drain? Drain is grounded. So this is also grounded. So R0 2, right? Now tell me one thing. What is the resistance you see from here in upward direction? Okay, let's not go by resistance. Okay, this is V0. What is the current in upward direction? GMV0. This is V in. What is the current in downward direction? That is GMV in. Now you have to write the simple KCL at this node, at V node. So KCL at V naught. So what will be your KCL at V naught? So from V naught, you see GM V naught going outside. This is GM2 V naught actually, and this is GM1 V naught. GM2 V naught going outside. Then you see GM V naught going downward, GM1 V naught going downward. What else do GM1 V naught? No, it's not V naught. This is V in. GM1 V in going downward. What else current do you see? This current V naught by R naught 2, and this current also V naught by R naught 1 plus V naught by R naught 2 plus V naught by R naught 1 is equals to 0. All current out are outward current. GM2 V naught by R naught 2, V naught by R naught 1, GM1 V in 1, right? So your V naught would be GM2 plus 1 upon R naught 2 plus 1 upon R naught 1 is equals to minus GM1 Vi. Right? Tell me, what do you write? What you can write about this? GM2 parallel R naught 2 parallel, sorry, GM2 plus 1 by R naught 2 plus 1 by R naught 1. What you can write? You can write V naught by 1 by GM1, 1 by GM2 parallel R naught 1 parallel R naught 2. Are you agreeing to this point? Is equals to minus GM1 Vi. Are you agreeing to this point? How did I write it? I told you one thing, V by R1 plus V by R2. If this is the scene, not like that. Yeah, you can, I told you in the previous lecture only, right? If there are lower resistance written like this, V by R1 plus V by R2. So what you can write? V by R1 parallel R2. Right? This is what you can write. So here the same thing is happening. This is V naught by GM2, V naught by 1 upon GM2 parallel R naught 1 parallel R naught 2. Are you getting this point or not? I will explain once more, one last time. So this is V naught into GM2. So what I can write? V naught upon 1 upon GM2. This is V naught into 1 upon R naught 2. So V naught upon R naught 2 plus V naught upon R naught 1. This is what I can write. So what I can write? V naught upon R naught 1 parallel R naught 2 parallel 1 upon GM2. This will be used again and again. So I will not be explaining again and again. I hope you will be comfortable with this. V naught upon 1 upon GM2, V naught upon R naught 2, V naught upon R naught 1. So you can write 1 upon GM2 parallel with R naught 2 parallel with R naught 1. Well and good. Also you can verify by the unit as well. R is the resistance. This is resistance ohm. This is also resistance ohm. GM2 is transconductance del ID by del VGS. So 1 by GM2 will also be resistance. And V by R that will be current. Voltage by resistance will be current. GMVI is a current only. So current equals to current. And resistance parallel with resistance parallel with resistance. So all are resistance as well. So V by R is equals to current. That's it. This is how you can verify as well. So V naught by Vi. What will be your V naught by Vi? From here you can directly see your V naught by Vi is minus GM1 into 1 by GM2 parallel with R naught 1 parallel with R naught 2. That's it. This is your V naught by Vi, small signal gain. And if R naught 1 and R naught 2 are infinity, that means they are very large. If R naught 1 is equals to R naught 2 is equals to infinity, then what will be the gain? Gain will be minus GM1 by GM2. Look, no complex circuitry, nothing, just simple current. No circuitry you need to draw. वो सब T model, pi model, nothing you need to draw. Simply by current equation you are writing it. And once you are comfortable with all those things, you will be writing it very, very quickly. Now I will tell you one more method of this. I told you one thing. If this is the circuit, this is also grounded, this is also grounded, like basically both are shorted, then what is the resistance you see from here? That is 1 by Gm parallel R naught. Do you remember it? In the last lecture itself I told you the resistance from downward 1 by Gm parallel R naught. So V naught can see from V naught to ground, from this node to ground, from V naught to this node. So from V naught to ground you see 1 by Gm parallel with R naught. It's not necessary it should be grounded. The necessary condition is both should be shorted. This is the necessary condition that both should be shorted. So V naught to, and now this is grounded as well. So now you can see from V naught to ground I see 1 by Gm parallel with R naught. Say yes or no. And one more I can see from V naught to ground I can see R naught 1 as well. So what I can say, from V naught to ground I can see R naught 1 parallel with 1 by Gm2 parallel with R naught 2. Say yes or no. From V naught to ground I can see 1 by Gm2 parallel with R naught 2. Also from V naught to ground I see R naught 1 as well. So what I can say, from V naught to ground I see R naught 1 parallel with 1 by Gm2 parallel with R naught 2. Yes or no? Right? So let's see the method 2. What is the method 2? This is your V naught. From V naught to ground you see this much of resistance. Now this transistor is having V in. So that is driving Gm1 V in current. So here Gm1 V in current is flowing through R01 parallel with R02 parallel with 1 by Gm2. This was your transistor. This was your transistor. It is having V in voltage. This was your M1. So the current flowing was Gm1 V in. And this was your output. From V0 to ground, what did you see? You see a resistance which was R01 in parallel to 1 by Gm2 parallel with R02. Say yes or no. You saw, what did you saw? From V0 to ground, you see R02 parallel with R01 parallel with 1 by Gm2. How? By this. Because both are shorted. This is also shorted. This is also shorted. So from here, I can see 1 by Gm parallel with R0. This is the R0. Well and good. Now this GMVI current is flowing through this resistance. Now this GMVI current is flowing through this resistance. So what will be your V naught? V naught will simply be minus Gm into R naught 1 parallel with 1 by Gm2 parallel with R naught 2 into Vi. Basically GMVI current is this flowing. So what is your V naught by Vi? That is simply minus Gm1 parallel with R naught 1 into R naught 1 parallel with R naught 2 parallel with 1 by Gm2. That's it. In one line only you will be able to write down the answer once you do the enough practice. So in the examination this circuit will be in front of you. So what you will see, okay, from V0 to ground I see 1 by Gm2 parallel with R02 parallel with R01. What is the current? GMV in. So that current will be flowing through that resistance. So the gain would be minus Gm1 into 1 by Gm2 parallel with R01 parallel with R02. Within 10 seconds you will be able to tick mark the answer in the examination. That is my guarantee. If you do the enough practice, I will make you solve 15 to 20 question, not 15 to 20, more than this. Every single possible configuration we will be solving. So after that you will be writing the answer very quickly. Are you comfortable with all this? Minus Gm1 into 1 by Gm2 parallel with R02 parallel with R01. Well and good. Let's find more quantities. What we can find? We can find output resistance. So tell me, what will be the output resistance? What will be the output resistance for this? R01 parallel with R02 parallel with 1 by Gm2. Why so? Because this V in will be shorted. If this V in is gone, that means there is zero current. So from V0 you only see R01 parallel with 1 by Gm2 parallel with R02. So what will be the output resistance? That also you can write. For output resistance, small signal output resistance we are talking about. So basically they will be giving this circuitry only. And from here they will be asking you small signal output resistance R naught. This is what they will be asking. So what you would do, you will short circuit the V in. Now what you will say, from V0 to ground, here I see R naught 1. From this V0 to ground, from this V0 to ground, I see one more R naught 2. And here I see 1 by GM2. Here I see 1 by GM2 because this is also grounded. This is also grounded. So from V0 to ground, what is your R0 2? From V0 to ground, you see R0 1 parallel with R0 2 parallel with 1 by GM2. This is the output resistance. R0 1 parallel with R0 2 parallel with 1 by GM2. That's it. And there is this zero current, so it has no use. This is the zero current. So it has no use. This M1 is simply acting as open circuit. M1 is open circuit, only R0 1 is there. So 1 by GM parallel with R0 2 parallel with R0 1. And if there was R0 1, there was no R0 1 and R0 2. That means if lambda was 0, if lambda was 0, that means R0 1 would be equals to R0 2 would be equals to infinity. Then R0 would be 1 by GM2. That's it, right? So from V0 to ground, you would only see 1 by GM2, nothing R0 1 and nothing R0 2, right? Let's move on to the next amplifier, that is common source amplifier with degeneration. This is known as degeneration. Degeneration resistance. This RS is the degeneration resistance. Why it is used? What is the advantage? What is the disadvantage? Everything we will see. Now let's do the DC analysis of this. What we are doing? DC analysis. Okay, this is only the small signal analysis. Let's do the DC analysis here. So how will your DC analysis look like? In DC analysis, you will only consider VGG. This is VDD. This is RD. And this is your V0. Now let's assume because of temperature, your ID slightly increases. Your ID slightly increases. This is the ID which will be flowing from RD as well, from RS as well, because there will be similar current, right? In RD RS there will be similar current ID. So let's assume because of temperature or because of anything, because of temperature, because of any parameter, temperature, ID increases. So what will happen if ID increases? If ID increases, then this potential will also increase. If ID increases, then this potential across RS, we can call this as Vs. So Vs will also increase. If Vs increases, then what will happen? Vgs will decrease. If ID increases, Vs increases. If Vs increases, that means Vgs will decrease. Because what is Vgs? Vgs is Vg minus Vs. Vg is Vgg. That is fixed. And Vs is increasing. If Vs is increasing, that means this potential will decrease. And if Vgs decreases, what will happen to current? What is the equation of current? Some constant into Vgs minus Vt whole square. If this is decreasing, that means the current will decrease. The current will decrease. What is the advantage? The advantage is, by some parameter, if the current increases in your transistor, then the current will not keep on increasing. It will decrease. Increases, then come down. Then again increases, then come down. So it can maintain. The current will be maintained. It's not that it will keep on increasing. So because of temperature or anything, if the current increases, since there is this degeneration resistance that will stabilize the current, so it is stabilizing our circuit. So we are having a stable circuit. Stability is achieved. So till now, this much information is more than enough for you. Later on, we will understand this RS is working as negative feedback. If it is working as negative feedback, that means it is stabilizing our circuitry. So that we will study when we study the feedback topology and feedback amplifiers. So till now, that is enough. That if ID is increasing, your VS is going down. That means your VS is going up. That means your VGS is going down. That means your ID is going down. So if it increases by its own, it is coming down. You don't need to do anything. The circuit is making sure that your ID doesn't increase very much. If it increases very much, your VS will increase very much, your VGS will go down, so ID will go down. So your circuit is making sure that your ID doesn't increase infinitely, right? So this is the advantage of degeneration. Now what will happen to small signal gain, that we will see. What will be the input resistance, what will be the output resistance, everything we will see in common source amplifier with degeneration. So this is the common source amplifier with degeneration. So now we are going to calculate the small signal gain. So for small signal gain, I am assuming lambda to be 0. Why I am assuming lambda to be 0? Because in exam as well, you will see lambda equals to 0. Because if you consider lambda not equals to 0, that means if you consider R naught here, your expression will be very, very bad. Like it will be very, very complex. We will solve that. We will certainly solve that. But 99.99% chances is there that they will ask the gain for only lambda equals to 0. And this is asked many times. So even student remember the answer as well. And I will tell you, you will be also able to remember the answer. But they ask only for the condition lambda equals to 0. It is very rare that they can ask for lambda not equals to 0. That means lambda not equals to 0, right? That means lambda is some value like 0.05. So but it is very rare. So majorly they will consider R naught to be infinity. So if lambda is 0, that what does that mean? That means your R naught is infinity. So here we are considering that case that your R naught is infinity. We will also consider the case where R naught is not infinity. Here I will write down the equation and get to the final answer. But once I write down the equation here, you will realize why it is not asked, because the expression will be very complex. So let's solve this expression once. We are not going to draw any model, nothing like that. We only know the concept of current. That's it. So we are going to find everything by the concept of current. That what will be the current here? Tell me. Vs is the small signal voltage. You can write this is the small signal voltage. Vs is the small signal voltage. Small signal voltage. What will be the current? Current will be Gm Vs minus this source potential. I don't know the source potential, so I am assuming the source potential to be Vx. So my current is Gm Vs minus Vx. So what will be your V naught now? Our target will always be to write down your V naught equation. For writing V naught equation, you need the current. This current you need. So what is that current? That is Gm Vs minus Vx. So what will be your V naught? Your V naught will be minus Gm into Vs minus Vx into Rd. Are you agreeing to this point? Current into resistance. But since it is 0, this potential is 0, then 0 into this potential. Sorry, 0 minus this potential. That will be your V naught. So V naught will be minus Gm Vs minus Vx into Rd. Well and good, very easy. Current is Gm Vs minus Vx. So Rd into Gm Vs minus Vx minus sign will also be there. What will be your V naught? That will be minus Gm Rd Vs minus Vx. Now you can write down the gain. The only problem is this Vx. The only problem is this Vx. So this is the problem. So we have to eradicate this problem. We have to eradicate Vx somehow. You can write down the Vx in terms of V naught as well or Vin as well. The target is to eradicate Vx. How will you eradicate Vx? Some people will do, some people will say that sir, this current is flowing through Rs as well. So what I can write? Gm into Rs into Vs minus Vx is equals to Vx. And from here I can write down the value of Vx. This is also correct. This is also good. There is nothing wrong in that. By this also you will get the final answer. What I did, the same current is flowing through Rs as well. In MOSFET amplifier, only you need to use your brain to write down the expression. Here my target was to eradicate Vx. So how I can eradicate Vx? The current is flowing through Rs as well. So Gm into Rs, Vs minus Vx, that will be the potential, and that is equals to Vx. Current into resistance. This was the current into resistance is giving me the potential, and that is equals to Vx. So from here I can find out the value of Vx. This is also good, but that will take more calculation. So what I can do? What is the current in upward direction? V naught by Rd. This current is V naught by Rd. Say yes or no. And what is the current here? That is Vx by Rx. Vx by Rs. So what I can write? The same current is flowing in the complete MOSFET. From Rd, Rs and from MOS, there is the same current. This current is same in the complete MOSFET. Small signal current or large signal current, the current will be same in the complete MOSFET. What is that current? Whatever it is, but the current will be same. So what I can write? V naught by Rd is equals to minus of Vx by Rs. Say yes or no. Are you guys comfortable with this? Upward current is equals to downward current. So one is upward, one is downward. So minus sign will be there. So V naught by Rd is equals to minus Vx by Rs. So what will be your Vx? Vx will be, from here, what do you get to know? Your Vx is minus Rs by Rd into V naught. This is equation number 2. Your Vx is minus Rs by Rd into V naught. So this is a simpler expression. Now I will put this expression in this one. So what is your V naught? By using equation 1 and 2. What was your V naught? V naught was minus Gm Rd Vs minus Vx is plus Rs by Rd into V naught. So V naught is minus Gm Rd Vs minus Gm Rs V naught. Right? We are just opening the bracket. So this Rd will be cancelled, minus Gm Rd into V naught. What will be your V naught? 1 plus Gm Rs. This I am taking this side, and it will be minus Gm Rd Vs. So what will be your V naught by Vs? That will be minus Gm Rd upon 1 plus Gm Rs. That's it. This is the small signal gain. Small signal voltage gain. Right? This is the small signal voltage gain. What was the small signal voltage gain if Rs was 0? If Rs was 0, if this was your circuitry, if Rs was 0, if this was your circuitry, what was the small signal gain at that time? That was minus Gm into Rs. That's it. This is Rd. So that was minus Gm into Rd. Now if Rs is there, then the gain is minus Gm into Rd upon 1 plus Gm Rs. That's it. The gain is reduced by this factor, 1 plus Gm Rs. Previously the gain was minus Gm Rd because the current was GmVi flowing through this. So the gain was Gm into Rd. That's it. But now the gain is reduced to minus Gm Rd upon 1 plus Gm Rs. So the gain is reduced. Gain is reduced to minus Gm Rd upon 1 plus Gm Rs. This is your small signal voltage gain. What is the current gain here? What is the current gain? Current gain AI. That will be I out by I in. There is no change in I in. I in is still 0. I in is still 0. This current is still 0 ampere. That means current gain is still infinity. There is no change in current gain. What is the input resistance? What is the input resistance? R in. Input resistance. Input current is still 0. Whatever V in is there, but input current is again 0. Your R in is still infinity. So your gain is reduced. It is reduced to GMRS minus GMRD upon 1 plus GMRS. Now the question is, what will be your output resistance? But before that, let's calculate. We have calculated three things: gain, current gain, and input resistance. Now we are yet to calculate the output resistance. So let's calculate the output resistance first. Then we will see the voltage gain considering R naught. We will see that, but let's calculate the R naught first. What will be your R naught? What you need to calculate? This is what you need to calculate, R naught. From here they are asking you the resistance. This you need to calculate. Can you say it is RD parallel R naught? No, you can't say that, right? Why it is not RD parallel R naught? Because here now you are having RS as well. Previously the output resistance was RD parallel R naught, because from V0 to ground you could see RD, and from V0 to ground you could see R naught. Now from V0 to ground you could see R naught, RD for sure, but from V0 to ground it's not necessary that you are seeing R naught. There is something different, and what is different is there, that we will find out. So for calculating the output resistance, what you will do, you will short circuit this. So let's make this circuit once again. This is the MOS you are having. Here you are having RS resistance. This is shorted. And this is your R naught. This is your V naught. And from V naught to ground, you see RD. This is your RD. So from V naught to ground, you see RD. And from V naught to ground, you see one more resistance, that is this RX. Look, this much of configuration is providing me RX resistance. This I am assuming that this resistance is RX. This much of configuration is RS. So what will be my final output resistance? What will be my R out? That will be RD parallel with RX. My R out will be RD parallel with RX. Now my target is to find the RX value. That's it. Did you understand? What did I do? From V0 to ground I see RD. Now I am saying from V0 to ground I see RX, but I don't know what is RX, but that I can find. So my target is to find RX value now. What is my RX? I guess I can copy this circuit only. Forget about this. यार इतना तो बना ही लेता मैं इतनी देर में. This is your R naught and this was my RX. I need to find RX. I can apply some Vx potential here and get Ix current out of it. Vx potential here and get Ix current out of it. So my Rx would be Vx by Ix. Right? Now previously what was happening when this Rs was not there, this small Rs, this was not there, and then what was happening, that your Vgs was 0, then there was no current in this MOS, and there was no current in this MOS. If Rs was not there, if this source was grounded, so Vgs was 0. If source was grounded, Vgs was 0, so there was no current. But now the source is not grounded, there can be some potential. Let's assume this potential is V. There can be some potential, that potential we are assuming to be V. So if this potential is V, then what will be the current in the MOS? In upward direction, the current will be GMV. Say yes or no. I am assuming this potential to be V. So in upward direction, the current is GMV. Say yes or no. Are you agreeing to this point or not? Right? So what I can write? I am applying nodal at Vx. Nodal at Vx. What that will be? So in upward direction, you are having GMV current. Look, this is GMV current. What is the current you are having here? that will be Vx minus V by R naught. Vx minus V by, sorry, Vx minus V by R naught. Say yes or no? Vx minus V by R naught. So what will be the equation? Ix plus GMV is equals to Vx minus V by R naught. Say yes or no? This is the Ix current, this is the GMV current. So Ix plus GMV current is equals to Vx minus V by R naught. Say yes or no? Agreeing to this point? So what I can write? Ix into R naught plus Gm R naught into V is equals to Vx minus V. This is our equation 1. Now what is the issue? The issue is V. You need the expression Vx by Ix. The issue is this V. This is the issue. So you have to eradicate this V. How you can eradicate this V? Some people will apply nodal here. That sir, I will apply nodal here that V by Rs plus GMV is equals to Vx minus V by R naught. From here I can find out the relation between V and Vx. That is good, but that will take more time. So what I will be doing, just see this. What is happening with Ix? This Ix is coming, then it will be divided into two parts. In this part and this part. So Ix is divided into two parts. That one part is minus GMV, Ix is coming, minus GMV, and the other part is Vx minus V by R naught. Are you getting this point? Ix is being divided into two parts, one in the MOS, one in the R naught resistance. After that, what is happening? The current is divided, and then both current will come. Some current will come from here, some current will come from here, and both will be added and will flow here. First Ix was divided and then added. So what is this current? What is this downward current? Tell me, what is this current? This current is Ix only. Basically, this is the scene that there is some circuitry is there. This Ix current was flowing here, and then there was this Rs resistance was there. So Ix current was divided into this and then completely came here. Try to visualize it. Try to visualize this as a black box. So this Ix current came, divided into this black box, and then came out again. Are you getting this point or not? Ix current came, divided into this black box, and then again went out. So this way I can make my calculation more easier. So my V will be, simply my V will be Ix into Rs. That's it. This will be my V. So in the examination, I will use my brain slowly as well and also accurately, because their calculation will be as minimum as possible. They will not ask you very tough questions in case of calculation. They want you to think like that. Oh, Ix is coming divided into two parts and then one current. So V is equals to Ix into Rs. That's it. Now V I can replace here. So by equation 1 and 2, Ix R naught plus Gm R naught. What will be V? V will be Ix into Rs. V will be Ix into Rs is equals to Vx minus V. Vx minus V, that is Ix into Rs, right? So what will be, what we are getting here? R naught plus Gm R naught Rs plus Rs is equal to Vx. So what is your Rx? Rx is Vx by Ix, that is Rs plus R naught plus Gm R naught Rs. This is your Rx. So what else you can write it? You can write it like this: Rs plus R naught you can take common from here, 1 plus Gm Rs into R naught. Or what you can write? This R naught you can keep as it is, plus from Rs common you can take 1 plus Gm R naught Rs. Right? Are you understanding this point? These are also the ways. This is also Rx, this is also Rx. Here I put Rs as it is, I took R0 as common, 1 plus Gm Rs. Here I put R0 as it is, I took Rs as common, 1 plus Gm R0. These are the other ways. Now, some people, what do they do? Approximately it can be written as Gm R0 Rs. Look, this is simple Rs, this is simple R0, this is Gm R0 Rs. So Gm R0 Rs is very much larger than Rs and R0. What we are saying is that Gm R0 Rs is very much larger than R0 Rs plus R0. So approximately sometimes you will find only this much written, Gm R0 Rs. Are you getting this point? Sometimes you will find only written Gm R0 Rs. But you will have to remember this formula as well. How will you remember? So let's write down what you need to remember. Your circuitry was something like this. You will remember this circuitry. What is the circuitry? You will not remember this is the output resistance of something, this is the input resistance of something. You just remember the circuitry. The circuitry should be in your brain. Because no one is going to ask you what is the output resistance of common source amplifier with degeneration. Now, no one will ask you. They will give you a particular circuitry and they will ask you to find the resistance. So I am writing to remember. This you are going to remember, because if you are a good designer, you will remember these kind of things. If you are going to solve the problems quickly, there will be only two to three things that I will tell you to remember. If you remember these things, then you will be able to answer very quickly. What is the first thing that I told you to remember till now? That was this. What is the resistance you see from here? What is the resistance? This is also grounded. Oh, basically both are shorted. What is the resistance? 1 by Gm parallel with R0. This is the one thing that I told you to remember from downward, 1 by Gm parallel with R0. That's it. Now this is the second thing that I am asking you to remember. If you don't remember, it's okay, you can drive it as well. But if you remember, if there is a big complex circuitry, you can write down the answer in 1 minute. Not in 1 minute, even in 30 seconds. So this is the thing that I am asking you to remember. This is shorted, right? This is R0. And this is Rs here. Now, if they are asking you resistance from this side, what is that resistance? That is this resistance R0 plus this resistance Rs plus Gm R0 Rs. This is what I am asking you to remember. To remember RE MEM BER. To remember. Why I am asking you to remember? Because it is very important. It will save your time, it will save your calculations. So this is the only thing I am asking you to remember, and at least remember this thing, Gm R0 Rs. At least remember this thing. Okay. So this is known as output resistance of common gate amplifier. Okay, common gate amplifier. Common gate amplifier. This is the output resistance of common gate amplifier. So we will see it once again when we study common gate amplifier. In common gate, what do? We apply input here and get output here. So this will be the output resistance of common gate amplifier, right? So, but for now we are studying common source amplifier with degeneration. So we are calculating the common source, we are calculating the output resistance of common source amplifier with degeneration. So our output resistance was Rd parallel with Rx. What was the output resistance? Output resistance was Rd parallel with Rx. And what did we find the value of Rx? That is Rd parallel with, this is the value of Rx, that is R0 plus Rs plus Gm R0 Rs. This is your R0. But again, this value will be very large. This value will be very large. And this value will be very small. Previously, what was the output resistance? Rd parallel R0. When there was no degeneration. So R0 is generally R0 is larger than Rd. Rd is very small resistance that you can put. R0 is generally larger than Rd. R0 is a very high value, near to infinity. So what happens? Approximately it is equals to Rd. Here also, this value is also This is also greater than R naught. So this value is also very large. So RD parallel with some very large resistance. This is also approximately equals to RD. So here your output resistance did not change much. This is RD only, nearly RD. Output resistance did not change much. What was the gain? Gain changed. Gain was reduced to minus GMRD upon 1 plus GMRS. What was the current gain? That was same infinity. What was the input resistance? That was also same infinity. So did you understand? Common source amplifier without degeneration and with degeneration. We will compare both of them. But before that, let's find out this. Voltage gain considering R naught. This is very, very less important. No one is going to ask you. Why so? Because the expression will be very complex. Let's check that out. And you can write down the expression on your own as well. First, write down the current. What is that current? That will be Gm Vs minus Vx. This current will be Gm Vs minus Vx. And here you are having R naught. This is your Vs. This is your Vx. So at no, this is not V naught. This is not Vs. This is V naught. Gm Vs minus Vx. This is R naught. This is Rd. This is Rs. So at what I can do, I can apply KCL at V naught. So what will be my KCL? KCL will be Gm Vs minus Vx outward current. What is the other output current? That is V naught by Rd plus V naught by Rd. Till this thing we have done already. There is one more outward current, that is V naught minus Vx by R naught. V naught minus Vx by R naught. That is equals to 0. What is the issue now? Vx is the issue. What is the issue? Vx is the issue. What is the current here? Vx by Rs. This is the first equation. What will be the second equation? Tell me one thing. V naught by Rd is equals to Vx by Rs. V naught by Rd is equals to minus Vx by Rs. Are you agreeing to this point? What I am saying, V naught by Rd is equals to minus Vx by Rs. What is happening? Let's assume this current is minus V naught by Rd. This minus V naught by Rd will be divided into MOSFET and R naught, then again added and then went down. So this current is the same. Minus V naught by Rd is coming, divided into MOS and R naught resistance, then again came down. Are you getting this point? Right? So V naught by Rd minus V naught by Rd is equals to Vx by Rs. So our issue was, what was the issue? Issue was Vx. So you can replace Vx with minus Rs by Rd into V naught. Now by using equation 1 and 2, you will find out the value of V naught by Vs, and that will be very complex. By equation 1 and 2. Gm. Actually, I found it in the rough notebook. Even in the textbook, you will not find it. Nowhere in the textbook you will find it, because this is not asked generally, right? Because the expression will be very complex. That's why it is not asked generally. Plus V naught by Rd plus V naught by R naught, you can say, is equals to Vx by R naught is equals to, okay, forget it, V naught minus Vx, that is V naught into 1 plus Rs by Rd. V naught into 1 plus Rs by Rd into 1 plus Rs by Rd upon R naught is equals to 0. So this is GMVS plus what V naught is having. V naught is having something really big. GMRS plus RD plus 1 by RD plus 1 by R naught plus Rs by R naught Rd is equals to 0. Now this is the expression we are getting, right? V naught by Vs we can write down. This is Gm Vs, that is equals to minus V naught. This will be R naught Rd. You get Gm R naught Rs plus R naught plus Rd plus Rs, right? R naught Rd is LCM. Rs plus R naught plus Rd plus Rs, right? What is V naught by Vs? That is minus Gm Rd minus Gm Rd. Something is wrong in the calculation. Let me check. No, nothing is wrong. So minus Gm Rd into R naught upon Gm R naught Rs plus R naught plus Rd plus Rd plus Rs. Yeah, so this is the final expression. Okay, minus Gm Rd into R naught minus Gm Rd into R naught upon Gm R naught Rs. So yeah, this is the final expression of gain you are getting. Now if R naught is very large, what will happen? If R naught is very large, then what will happen? So let's check. If R naught equals to infinity or very large, then what will happen? Let me add a page. V naught by Vs will be equals to this minus GMRD will be there as it is. R naught is very large. Let's keep it here only. R naught. We have to basically find the limit. R naught is tending to infinity. What will happen to this expression? This expression will be reduced to Gm R naught Rs plus R naught. That's it. Gm R naught Rs plus R naught, because Rd Rs will be very low. R naught is very large, so Gm R naught Rs plus R naught. This is very low. Like 1000, 10,000 plus 10. Nearly it will be 10,000 only. So this is what we are doing. So this expression will be reduced to Gm R naught Rs plus R naught. Gm R naught Rs plus R naught. Now R naught will come out. So R naught will get cancelled. It will be minus Gm Rd upon 1 plus Gm Rs that we calculated previously. This is our V naught by Vs. Right? This is the gain. We calculated the output resistance considering R naught only. If R naught was not considered, what would be your output resistance? If R naught was not considered, what would be your output resistance? If R naught was infinity, your output would have been infinity only. Your output resistance would have been infinity only. Right? If R naught was infinity, this would go to infinite only. But here we are considering R naught. So this is the expression we got. Right? This much would be infinity only. This would be replaced with, like, your output resistance would be Rd parallel infinity. That would be Rd only. Right? If R naught was not there. If R naught was infinity. Here we consider R naught as well, then we got to know this expression is there, but this is not useful. Only this expression is useful. And this also we calculated previously as well. Right? So I hope you are getting comfortable with the amplifiers. Common source amplifier we have studied. First we studied common source amplifier, then we studied diode connected load. First we studied common source amplifier, then we saw what was the problem with that. What was the problem? The gain was depending on ID. So then we studied diode connected load, then we studied this common source amplifier with degeneration and the small signal analysis. What was the gain we were getting? Minus GMRD upon 1 plus GMRS. Input current gain was same, input resistance was same. The problem was with the output resistance. So we calculated the output resistance, that was this Rs plus R naught plus GM R naught Rs. Well and good, right? So I told you to remember this thing, that The resistance we are seeing from here is GM R naught RS. Let's check out one more thing in this lecture only, although this lecture is getting of around 1.5 hours, I guess. Yeah, let's check out one more thing. Output resistance of common source amplifier with degeneration. Just now I got a thought to solve this thing here with degeneration, considering lambda equals to 0. What will be the answer? The answer will be RD only, but let's calculate it. You will learn something new here, I guess. Okay, degeneration, sorry. Yeah, so this was our RD. This was grounded. This was the RS we were getting. Yeah, so from here we needed to calculate the resistance R naught, right? Yeah, so like can you directly say it will be RD only, that R naught will be RD only? Can you directly say that? No, we can't directly say that, because this can also give us some resistance. Lambda is 0, that means R naught is infinity, but this can also give us some resistance, no? Are you getting my point? Let's make this circuit once again. This is your RD. From here, this is your RD. From here, I was calculating R naught. So my R naught will be RD parallel with Rx. I need to calculate the Rx value. My target is to calculate the Rx value. So how will I calculate the Rx value? Let's check that out. Previously, I calculated the Rx value, but considering R naught, there was R naught available, but no, now there is no R naught available. Now my circuitry is something like this. Here I will apply Vx and get Ix out of it. Now this is your V, right? What is the current flowing here in upward direction? That would be GMV. Say yes or no. The current in the upward direction would be GMV. Now here GMV will be equals to Ix only. GMV will be equals to Ix. This is the equation 1, right? GMV will be equals to Ix. What would be the equation 2? The equation 2 would be V by Rs is equals to Ix. This is the equation 2. V by Rs, this current V by Rs is equals to Ix. What did I do? I needed to calculate Vx by Ix. My Rx is Vx by Ix. This is what I needed to calculate, Vx by Ix. But there is no use of Vx here. First, we are writing down the equation that we know. What we know, GMV current will be flowing upward. So GMV is equals to minus Ix, sorry. GMV is equals to minus Ix. And V by Rs is equals to Ix. This is what we got to know. Well and good. Then what do we understand here? What we can do? We can replace by equation 1 and 2. By equation 1 and 2. What will happen? What I can do? I can replace V with Ix into Rs. I am replacing V with Ix into Rs is equals to minus Ix. So Ix will be GMRS plus 1 is equals to 0. So what did I get to know that here? My Ix is 0. Look, I took this problem just to make you understand the analysis. Like, let's just assume in the examination this circuit comes in front of you, R0 is not there, then you will be puzzled there. What will be the resistance? Because you will see that this is not grounded, V is not grounded. You will see that V is not grounded. If V is not grounded, that means there will be certainly some current flowing through it. But the current flowing through it is zero. That we go to understand by this analysis. What did we do? We write down the current GMV is equals to minus Ix, V by Rs is equals to Ix. So here we got to know that Ix is 0. So what will be your Rx? Rx will be Vx by 0. That would be infinity. That's it. So your output resistance came out to be, which was Rd parallel with Rx. That would be Rd parallel with infinity. So your output resistance is Rd. Right? This is your output resistance. R0 is equals to Rd. So from here you only see Rd. But it feels like that there will be some voltage here. But the voltage is itself 0. Well and good. I hope you understood it. Let me put the charger. Then we will write down the conclusion of everything that we have studied. Common source amplifier versus common source amplifier with degeneration. So after now we will write down the conclusion. Okay. Yeah. So this was common source amplifier without degeneration and this is with degeneration. So what is the first point? Here better stability was there, right? Better stability. Because if ID was increasing, then ID was getting down as well. Because VS was getting increased, VGS was getting decreased, and ID was getting down as well. So better stability is there. Here, if ID is increasing, then it can keep on increasing because there is no RS resistance which can take down the ID. So here, less stability. Less stability. Second point, gain, voltage gain, V0 by Vin, small signal voltage gain. That was minus GMRD. And what was the gain here? That was minus GMRD upon 1 plus GMRS. So here there was more gain. Here it is less gain. What was the output resistance here? R out. That was RD parallel to R0. And what was the output resistance here? That was RD. Sorry. That was RD parallel to RS plus R0 plus GM RS R0. Right? So these are the comparison. Let's review the lecture once again, what we have studied till now. Let's review all the slides. So we started with common source amplifier, then we saw what is common source amplifier. Input is applied at gate and output is we are getting drain. Then we saw the small signal analysis, we found the small signal gain, that was GMVI current was flowing from RD parallel R0. So the gain was minus GM RD parallel to R0. What was the small signal output resistance? VI was getting shorted, so RD parallel R0. What was the current gain? Infinity. What was the input resistance? That was infinity. What was the problem? It was depending on GM. GM was directly depending on ID. ID was the function of temperature. So if temperature changes, ID will change, the gain will change, and this is not desirable. So for that you are using diode connected load. So in diode connected load, what did you find? GM-V0 current was flowing upward, GM1 VI current was flowing downward. So the gain was minus GM1 by GM2. Then we found out that the gain is now constant, which is depending on W by L, and W by L doesn't depend on the temperature. Then we saw the small signal gain, considering lambda is not equal to 0, that means R0 is present, R0 is not infinity. So if R0 is not infinity, what we can do? We can simply apply KCL. So upward current, downward current, outward current, outward current. So all outward current are equal to 0. Then we found out the gain was minus GM parallel with resistance. There was second approach as well. So from this V0 node, what we could see? 1 by GM2 parallel with R02 parallel with R01. And the current was GM1 VI. So from there as well, we could find out the gain. What was the output resistance? Output resistance, input will be shorted. So in M1 there is no current. M1 is simply open circuited. If M1 is open circuited, from V0 what do you see? From V0 to ground you see 1 by GM2 parallel with R02 parallel with R01. And if R0 1 and R0 2 was infinity, so from V0 to ground, you could see only 1 by GM2. Common source amplifier with degeneration, RS is the degeneration resistance. So what is the advantage we are getting? If ID increases, because of the degeneration, we are getting the stability because ID decreases. Then we did the small signal analysis considering lambda is equals to 0. Here we are considering lambda is equals to 0. That means R0 is infinity. So we found out the gain. So for finding out the gain, we smartly wrote down the equation. What was the equation we wrote down? First we wrote down the current, then we wrote down the V0 value. V0 was minus GMRD, Vs minus Vx. The problem was Vx. So then we found the relation between V0 and Vx. So what was the relation? V0 by RD is equal to minus Vx by Rs. Then we found out the gain. The gain was minus GMRD upon 1 plus GMRs. This was the current gain. Current gain was simply infinity. Input resistance was also infinity. Then we found out the gain considering R0. But this will not be asked. This is very less important. Why it is very less important? Because the expression is very complex. This is the expression that we are getting. This is very complex. So there is very rare chance that this will be asked then. But we can smartly do the analysis. This is what we are getting. Right? You don't need to mug it up in the examination. If they ask, you can derive it there. Then we are considering lambda R0 to be very large. Then what will happen? The gain will be reduced to minus GMRD upon 1 plus GMRS. Then we found out the output resistance that we have to remember. RD parallel with some RX. So RX we have to remember. RX we found out Vx by Ix. What was the smart move we did here? That Ix is equals to V by Rs. That was the smart move that we did here. So V is equals to Ix into Rs. So that we put in the previous equation that we wrote by simply finding the nodal analysis. Vx minus V by R0 is equals to GMV plus Ix. Right? So this we did. Then the output resistance we got is Rs plus R0 plus GM R0 Rs. Rs plus R0 plus GM R0 Rs. This was the output resistance we found, and this we have to remember. Also, we found out the resistance of common source amplifier with degeneration. With degeneration and considering R0 is infinity, that means lambda is equals to 0. If lambda is equals to 0, it feels like that this will give you some resistance, but there is no resistance. Why it is so? Because we applied it, then we got to know that this is the fixed value, then it is fixed value, then Ix is equals to 0. If Ix is equals to 0, R0 is infinity. So R0 we are getting is R0 parallel with RD. I will give you one more intuitive approach. One more approach I will give you, okay, of understanding this. You are finding output resistance. What you are doing? You are applying Vx, and then you are changing Vx, and then you are getting what is the change in Ix. This is what you are doing, right? You change Vx, then you see what is the change in Ix, right? Are you able to understand this point? What I mean to say is that basically Rx is change in Vx divided by change in Ix. This is how you can write Rx as well. Vx by Ix, or simply from 0 to Vx you increased. So whatever the change you did in Vx, what will be the change in Ix? This is what you need to write. Does Ix depend on the change in Vx? If you are changing Vx, you are changing the drain potential, not gate potential or source potential. If you are changing the drain potential, but the current is not even depending on the drain potential, the current will depend on Vgs minus Vt square. It is not even changing on the drain potential. It is not even depending on the drain potential. So no matter whatever you change, your Ix, the change in Ix will be 0 only. So the resistance will be infinity. Now some people will have doubt, sir, then why in the previous case it was changing? Sir, why in this case you were saying that it is changing? Now if you change Vx, what will happen? If you change Vx, what will happen? This current will change. The current in R0 will change. If the current in R0 is changing, that means this Ix can change, because Ix is depending on the MOSFET current plus the current in R0. What are you understanding this point? If I am changing Vx, the current in MOSFET is not changing. The current in MOSFET is the same. If I am changing Vx, the current in the MOSFET is the same. The current in the MOSFET is GMV, that is not changing. But if I am changing Vx, then the current in R0 is changing. And the Ix current depends on the MOSFET current plus the current in R0. So here your output resistance was something. You are getting some output resistance. But here you got the output resistance to be infinity, because if you are changing Vx, the current in MOSFET was changing. But if you are changing Vx, the current in MOSFET was not changing because it was not depending on Vx. The current in the MOSFET was constant. So the change in Ix was 0. That's why you got the output resistance to be infinity. If you did not understand this, you can do by equation as well. Just the intuitive approach it was that if you are changing Vx, there is no change in the MOSFET current. If there is no change in the MOSFET current, then there is no point of the output resistance. Output resistance will be simply infinity. But in the previous case, if you are changing Vx, there was no change in the MOSFET current, but there was change in the output, this R naught current, the current which is flowing in the R naught. So there was change in the current flowing through R naught. So because of that, Ix was changing, and because of that, you got some output resistance. Say yes or no. Did you understand it or not? I hope you are understanding it. Okay. So in the next lecture, what we are going to see? We are going to see the biasing, best possible way of biasing a common source amplifier. Previously, what we have seen, this is what we have seen. This is how we are biasing. What is the problem in that? That we will see. And how do we eradicate that problem? Then we will eradicate that problem. Then we will do the small signal analysis of that biasing. And after that, what we will see? We will study Miller's theorem. Then we will see more biasing technique, self-bias technique. So we will see those technique and we will do the small signal analysis of those technique as well. And with that, we will be able to complete our common source amplifier. Okay, well and good. So let's meet in the next lecture. Thank you. Hi everyone. So in the previous lecture, we studied about common source amplifier. We saw different configuration: simple common source amplifier, then common source amplifier with diode connected load, and then common source amplifier with degeneration. Now we will see if this is the perfect way of biasing. How we were biasing the common source amplifier? VDD was there, then there was a small signal, this was the small signal input voltage, and then there was this DC bias. So VGG and VDD was responsible for the transistor to turn it on and to make it in saturation region. So VDD and VGG will make sure that your transistor is working in saturation region. But if you are using this biasing, this kind of biasing, what is the catch here? What is the issue? You are using two batteries, VDD and VGG. Here, for giving the DC bias, for giving the DC bias, you need to use two supplies, two battery or two supplies, and that are VDD and VGG. And this is not desirable. When I am designing a particular chip, when I am designing a chip, I will have only one supply, that is VDD. I will not have separately VGG. I can make VGG from VDD. How will I make VGG from VDD? By potential divider. That's it. So this is not desirable. Not desirable. Two supplies are not desirable. I will use only one supply. I will use only one supply. So how will I get VGG then? By potential divider. That is how I will get VGG. So this is the correct way of biasing. This is the first one. We will study more ways of biasing. So this is the first one. So this is the correct way of biasing. What I have done, I am using only one supply, that is VDD. Now this potential I can write down, right, and that will be VGG. Now instead of this V in, this is the small signal V in. Small signal V in. This is small signal input voltage. Here in this V in, you are not giving the VGG. This V in is simply Vm sin omega t. You are not giving VGG here. VGG you can get from VDD only. So here separately you can do DC and AC analysis. Let's do the DC analysis of the circuit. Let's do the DC analysis. So what will happen in case of DC analysis? In case of DC analysis, what happens to capacitor? Capacitors are open circuited. In case of DC analysis, capacitors are open circuited, right? That we have already seen. Capacitors are open circuited. Now what will be this V naught? Tell me. Will this V naught have DC output? Will this V naught have DC output? This is my question. No. Why so? Because there is this capacitor as well. This capacitor C. This is also known as coupling capacitor. This I can call CC1. This I can call CC2. This is also a coupling capacitor. What will happen? There will be some DC current through it. Your V naught here would be VDD minus ID into RD plus some DC output. Your V naught will be VDD minus ID into RD plus some AC output. Sorry, not DC output. DC output is, what is your DC output? That is VDD minus ID into RD. And this DC output will see some capacitor, CC2. It will see some capacitor. So it will not go up to V naught, this final V naught. So this final V naught is the small signal output only. So only small signal will be coming at the output. Are you getting this point? Only the small signal will be coming at the output. So whatever the DC was there, because of this CC2, the DC is not going towards the output. So here I will write small signal output. This shows our small signal output. This is small signal output. But for now we are doing the DC analysis. So this I am writing my DC output. This is my DC output. So what will be my DC output? What will be my VGS value? What will be my VGS value? VGS. That would be VDD into RD, VDD into R2 upon R2 plus R1. That will be my VGS. Simply the potential divider, because the current here is 0 ampere. The current here is 0 ampere. The current is 0, so simply potential divider you can apply. R2 upon R2 plus R1 into VDD. This is your VGS. What will be your ID? This will be your ID. So your ID would be that constant value mu n cox w by 2l VGS minus VT whole square. VGS value you will be having, VT value you will be having, mu n cox w by 2l value you will be having. So you can calculate ID from that. And then what will be your output? Output will be VDD minus ID into RD. That's it. That will be your output. This will be your ID. So you have to set the value of R2, R1 and RD such that your VDS is greater than VGS minus VT. You have to set the value of R1, R2 and RD such that your VDS is greater than VGS minus VT. Also, you have to set the value of R2 and R1 such that your VGS is greater than VT. First point, that is set R1 and R2 such that VGS is greater than VT. Because what is your VGS? That is VDD into R2 by R2 plus R1. That should be greater than VT. We have to set the value of R2 and R1 such that your VGS is greater than VT. This is the first point. And the second point should be, what should be the second point here? On the next page only I will have to write it. Set R2, R1 and RD such that your VDS is greater than VGS minus VT, right? So that it is working in saturation region. What does it ensure? Ensuring saturation region. Well and good. Let's do the, why it is written DC analysis. Let's do the AC analysis. Okay, why did I leave so much of pages there then? Okay, DC analysis is done. We will do the AC analysis now. Small signal analysis or AC analysis. So we will do the AC analysis now. What will happen in the AC analysis? This VDD will be gone. This VDD will also be gone. This cap will be shorted. In case of in case of DC analysis, the cap was open circuited. The cap was open circuited. In this case, this will be shorted. This is shorted now, and this cap will also be shorted. This will also be shorted now. Now what will happen? Oh, and this is not V in. This is your small signal V in. Small signal V in. Everything is small signal V in, and this is your small signal output. This is your small signal output. So what will happen? This V in will directly come here. In case of small signal analysis, there is no use of R1 and R2. R1 and R2 are connected only to make sure that your large signal VGS is greater than VT and your VDS is greater than VGS minus VT. Are you getting this point? I have biased my amplifier such that when I am doing the AC analysis, this V in is completely coming to the amplifier. There is no use of this R1 and R2. Are you getting this point or not? So this V in is completely coming to the amplifier. Between drain to source, there is R not connected. Between drain to source. So this is drain, source is grounded, so R not can also be grounded. So between drain to source, R not is connected. Drain to source, R not is connected. And since this is grounded, source is grounded, so I am making this as grounded as well. Now this is V in. What is your VGS value now? Small signal VGS value. What is your small signal VGS value? That is equals to V in. So what will be the current? Current will be GM V in. That current will be flowing from what? RD parallel R naught. This V in is coming. The current is GM V in. This GM V in current is flowing from RD parallel R naught, because from V0 to ground you see RD, from V0 to ground you see R naught. So from V0 to ground you have RD parallel R naught. So did you understand this point or not? So basically what is the scene here? The current is, again and again I am not going to draw this, just once more I am drawing it. The current is GM V in, that is flowing through RD parallel R naught. So what will be the gain? The gain here would be minus GM RD parallel R naught. That's it. This is the voltage gain, small signal voltage gain. Did you understand this point? This is the small signal voltage gain, that is minus GM RD parallel R naught. Did your gain reduced? Did your gain reduce? No, the gain is the same. But using only one battery or one supply, you have made this amplifier. In previously, you need to use two supplies, but here by using only one supply, you have made this amplifier. There is no change in the gain. What is the change in the input resistance now? If they are saying this is my input resistance, let's calculate small signal input resistance. Let's calculate small signal input resistance. Let's replace this with small signal input resistance. What will be the small signal input resistance? What will happen to this? This will be completely shorted. VDD will be gone because we are doing the small signal analysis, and this V0 will be here. Here you need to calculate the resistance. From this node to ground, what do you see? From this node, from V in, this node is V in only. From V in to ground you see R1. From V in to ground you see R2. Here what is the current? 0 ampere current. So if I am saying I am applying a V in and getting I in out of it, so what will be my R in? That would be V in by I in. So let's calculate V in by I in. So here this potential will also be V in. So V in by R1 plus this current plus this current, V in by R2 is equals to I in, right? This current plus this current V in by R1 plus V in by R2 is equals to I in. This zero, there is 0 ampere current in the input side, 0 ampere current in the MOS. So you just applied nodal at V in. What did you do? You applied nodal analysis at V in. So V in by R1 plus V in by R2 is equals to I in. So what is your V in by I in? That would be R1 parallel R2. Your R in is R1 parallel R2. That's it. And you can directly see it as well. How you can directly see it? Because from this node to ground, R1 parallel R2 is there. So while doing the AC analysis, you can replace this resistance by R1 parallel with R2. Basically, what you can do, like this is your amplifier. So this is the simplest and smallest final circuit. So this will be replaced with RD parallel R0, right? RD parallel R0, because from V0 to ground you see RD parallel R0, and this will be replaced from V in to ground you see RD parallel, sorry, R1 parallel R2. So this will be replaced with R1 parallel R2, and this will be your V in. That's it, right? Okay. And what if they ask you output resistance? Tell me, what will be the output resistance? What will be the output resistance? What will be the output resistance? This CC will be gone. If you are calculating the output resistance, this V in will also be gone. V in is gone. Now VDD is also gone. These VDD are also gone. This is 0, this and this is also gone. So basically I can reduce it to R2 parallel with R1. From this node to ground you are having R2 parallel with R1. This is 0, this node is also 0. This node is at also 0 volt. So this is also grounded. So VGS is gone. What is your VGS value here? Small signal VGS. That is 0 volt. And what you are calculating? Output resistance. You are calculating output resistance. Here you are having R0. So this R0 I will be placing with R0 parallel with RD. Why? Because from this node to ground, from V0 to ground you can see RD, from V0 to ground you can see R0. So collectively I can write R0 parallel with RD. This I can remove, and collectively I can write R0 parallel with RD. So here this is gone, so here there is 0 ampere current. There is this 0 ampere current. So from V0 to ground, what do you see? R0 parallel with RD. So what is your output resistance? R0 parallel with RD. That's it. This is your output resistance. Right, what we are doing, we are applying a voltage V0 and getting I0 current out of it. So what will be your V0 by R0 parallel with RD is equals to I0. Why so? Because there is 0 ampere current. So that's it. So the complete I0 current is flowing through R0 parallel with RD. So what is your V0 by I0? That is R0 parallel with RD only. That's it. So your output resistance is R0 parallel with RD. Right? There is no use of writing current again. So let's forget about the current gain. They will not ask you current gain. Input resistance, output resistance, and voltage gain. This is what they ask. Right? And also if they ask current gain, you can apply some equations and get to the final answer. Now, what we are going to do? Yeah, there will be one question. Why did you use this coupling capacitor? Why did I use this coupling capacitor? This is the question. Try telling the answer on your own. You have seen the DC analysis, you have seen the AC analysis. What is the use of this coupling capacitor? If this coupling capacitor was not there, what would have happened? I would have directly applied V in here. Now what is my V in? My V in is small signal input voltage only. This is not VGG plus V in. This is only VGG. What is my V in now? Only small signal input voltage. Previously what was my V in? Small signal voltage plus DC voltage as well. Now this V in is not having DC component. This is simply AC component. So what would have happened if this was not there? Even in the DC analysis, this V in would have come here, right? And that would turn off the transistor because that is very small. So when you are doing the large signal analysis, what is happening is that this V in is not coming. The small signal input is not even coming. So you can set your operating point. And while doing the AC analysis, it is directly coming. So you can get your final output. Are you getting this point or not? So the coupling capacitor, what does the coupling capacitor do? It prevents VGS to be equals to small signal V. If coupling capacitor is there, what will happen? Your VGS will be equals to, capital VGS will be equals to R2 upon R2 plus R1 into VDD. And if coupling capacitor was not there, only the short circuit path was there, then your VGS would have been small signal V in only. So that is the issue. So what is the use of this coupling capacitor? It is not letting V in come to directly MOSFET, right? So this we will write, use of coupling capacitor. Arey yaar. So I will write it down. Yeah, so this is the reason why do we use coupling capacitor. So first is it helps in isolating the DC bias setting, and second one is, here what did I tell you, in the output you are having only the small signal output, that means you are having only the AC output. So let's assume if you are cascading MOSFET, what do you mean by cascading, that we will see. Okay, no worries, if you don't know what do you mean by cascading, we will see it in further lectures, but let's just write down the point here, that is, if you are cascading most stages, let's assume this particular amplifier, I am connecting this amplifier here, whatever the amplifier that I have connected here, the same amplifier I am connecting at the output. So what will happen? Only the AC part will be going towards the output. DC part will not go, because you don't want the DC, you only want the AC. So coupling capacitor helps in preventing that DC part to go to the next stage. It will block the DC part, only the AC part will go. And from where the DC part will come? Your DC part will come from the supply. So it helps in isolating the DC supply setting. So this is what we have written, helps in isolating the DC bias setting. And if you are cascading 2 or more stages, then only AC signal from the first stage will pass to the second stage and DC will be blocked. So if you are cascading 2 or more stages, then only AC signal from the first stage will pass to the second stage, to the next stage, while DC is blocked. Are you getting this point? Only the AC will pass, and how the DC will come? DC will come from the supply that you are giving, VDD. That will be VDD into R2 by R1 plus R2. Well and good? Yeah. So this is the use of coupling capacitor. They can ask you in interviews that what is the use of coupling capacitor, or in simple MCQs as well. Yeah. So now what we will see? Yeah, there is one more condition, that is, if your small signal input source is having some resistance Rs. This was your small signal input. So it was not having any resistance. Now what we are saying, this is your V in. This complete is your V in. This is your small signal input voltage. Signal input voltage. Basically, what is the scene now? The scene is something like this. This is R1, this is R2, this is RD, this is V0, this is VDD, this is VDD, this was the coupling capacitor. Till now everything is same. Here what did we do? We applied V in. Now instead of this V in, we are going to apply the source plus RS resistance. So it is having some input resistance RS. What changes it will bring? What changes it will bring in DC analysis? Will there be any change in DC analysis? No, because in DC analysis, this complete stage will be eradicated. This complete stage will not come, because capacitor will be open circuited. So this complete stage will not come. So there will be no change in the DC analysis, but there will be change in the AC analysis. What that change will be? Let's check that out. So let's do the small signal analysis. Let's do the small signal analysis. So in the small signal analysis, this will be shorted. This VDD is gone. This VDD will also be shorted. So from this node to ground, you can see R1. From this node to ground, you can see R2. So what you can do, you can replace this resistance as R2 parallel with R1. Well and good. This will also be shorted. So this will be your V node. Now can you write that this potential will be Vs and GM Vs current is flowing through it? Can you write this thing? No. What you can write? That this potential will be some V. This potential will be some V. We don't know what is V, and GMV current will be flowing here. So your V naught, this VDD is also grounded, sorry. And at V naught you are having R naught as well. R naught as well. So basically this writing like this is wrong. So GMV current will be flowing here. GMV current will not be flowing through RD. GMV current will be flowing through the MOS, and that current will go into RD parallel R naught. Because from V naught to ground you see RD as well and R naught as well. So from V naught to ground you can replace it with RD parallel R naught. What will be your V naught? V naught will be GMV into RD parallel R naught. So your V naught will be minus GM RD parallel R naught into V. Now what will be your V? This is equation 1. What will be your V in terms of Vs? Tell me. This current is 0. This current is 0. So what will be the V? Simply the potential divider, right? So V will be R2 parallel R1 upon R2 parallel R1 plus RS into Vs, right? This will be your V. This was your V naught. This is equation 1, this is equation 2. Did you understand this or not? This is having RS, this is R2 parallel R1. Basically this is the scene. R1, R2, V in. This potential. What is your V naught? R2 upon R2 plus R1 into V in, right? So this is what we are doing here. The same thing. The input current is 0, so you can simply say that the same current will be flowing here. Whatever the current is flowing through RS, the same current will be flowing through R2 parallel R1. So your V potential will be R2 parallel R1 upon R2 parallel R1 plus RS into Vs. So that will be your V potential, right? So what will be your V naught? V naught will be minus GM RD parallel R naught into R2 parallel R1 upon R2 parallel R1 plus RS into Vs, and if you are writing the gain, this Vs will come here. This is your small signal gain. So it is the same as the previous one. The difference is this factor. So your gain is reduced if your input is having some source resistance. If your input source is having some resistance with it, then your gain will be reduced because the complete Vs is not coming at the gate. The complete Vs is not coming at the gate. This is the gate. So the complete Vs is not coming at the gate. What is coming at the gate? At the gate, R2 by R1 upon R2 by R1 plus RS is coming. At the gate, R2 by R1 upon R2 by, sorry, R2 parallel R1 upon R2 parallel R1 plus RS into Vs is coming at the gate. Previously, what was coming at the gate? At the gate, complete input was coming. Previously, at the gate, complete input was coming. But now, complete input is not coming. What is coming at the input? This time, at the input, R2 by R2 parallel R1 upon R2 parallel R1 plus RS into Vs is coming. Now that is amplified to output. Amplified by the factor of GM, and that is going to output. So GM into R0 parallel RD minus sign into R2 parallel R1 upon R2 parallel R1 plus RS. This is your small signal voltage gain. I hope you are feeling the chapter. These kind of expression seems very complex to a lot of people, but now it is not complex at all. You simply are simply doing the network analysis, nothing else. You are playing with the current. Just find the voltage, get the current, write the output. That's it. This is what you are doing. Well and good. So this was the voltage gain. This was the voltage gain we calculated. Can you tell me what will be the input resistance? Input resistance. So I guess we can copy this circuit only, or it has been copied only. So in the next slide we will write resistance is input resistance, output resistance, everything we will write. So tell me what will be the input resistance. This VDD will be shorted. So if this is shorted, R2 parallel with R1 will come. This VDD will also be shorted. So from V0 you will see RD parallel with, from V0 you will see RD parallel R0. This is your V0. Let's make it better. Let's make RS here. So if they are asking you what is the resistance seen from here, tell me what is your answer. What is your Rin? What is the resistance seen from here? RS plus R1 parallel with R2. Say yes or no. If they ask you what is the resistance seen from here, what is the resistance seen from here? That is R1 parallel with R2 only. This I can call Rin2. So no one will say that what is the input resistance of common source amplifier, nothing like that. They will make the circuit and they will make the arrow. They will make the arrow and they will ask you how much resistance do you see from here? How much resistance do you see from here? RS plus R1 parallel with R2, right? Because RS and R1 parallel R2 is having the same current. If I current is flowing here, if IS current is flowing here, the same IS current will be flowing here as well. Because the gate will not have any current. This will not have any current. This will have 0 ampere current. So the same current. Now what if they ask you the resistance from here? So RS is gone. Only R1 parallel with R2 you can see. Only R1 parallel R2 you will see. Right? So this was your input resistance. Input resistance. Now what about the output resistance? So while writing the output resistance, what you will do? You will short circuit the Vs. You will short circuit the Vs. So short circuiting the Vs, this RS will be shorted. From here, this R1 parallel with R2 will be shorted. This is your V0 and this is RD parallel R0. Look, these complete are shorted now, right? So R1 parallel with R2 parallel with RS. There is one single resistance. What is the current here? 0 ampere current. Is there any source here? Is there any source which can supply current? No, right? There is no source which can supply current. So this 0 ampere current will be flowing through RS as well and will be flowing through R1 parallel with R2 as well. So there is no current flowing through RS and R1 parallel R2. So whatever the ground is there, that will come here only. This will be 0 volt only. Are you getting this point or not? Or let's just forget it. Let's assume this potential is V. This potential is V. So V by RS, I am applying nodal here. V by RS plus V by R1 parallel with R2, output current I am writing, plus 0 is equals to 0. So what is the value of V you are getting? 0. Right? V by Rs plus V by R1 parallel with R2 plus 0 ampere. All the outward current is equals to 0. So what is the value of V you are getting? 0. So basically this node, this particular node is shorted only now. So again VGS is 0. So again there is 0 ampere current here. So if 0 ampere current is here, that means the resistance you see from here is RD parallel with R0 only. Did you understand this point or not? The gate becomes shorted. If the gate is shorted, source is already shorted. So the current here is 0 ampere. If the current is 0 ampere, that means MOSFET is acting as an open circuit. If MOSFET is acting as an open circuit, so basically from output you only see RD parallel with R0. That's it. Understood? Well and good? Okay. Let's move on to the next bias. But before moving on to the next bias, we have to study a theorem that is known as Miller's theorem. Very easy, very intuitive and very interesting theorem it is. So let's forget about the statement, whatever that is written on the screen. Forget about this. First we will understand what is the theorem, what does the theorem says, and then we will see the proof. So what does the theorem say? There is an impedance Z is connected. Now across the impedance there are two nodes, V1 and V2. Now V1 and V2 are related by a factor of A. V2 is equals to A V1. Impedance Z is there. Impedance Z has two nodes, V1 and V2. V2 is equals to A V1. Now you can break this impedance Z into two parts. So what you will say, I am breaking the impedance Z into two parts. So what you will say, from V1 to ground, I see the impedance Z, that is Z upon 1 minus A. From V1 to ground, I see an impedance that is Z upon 1 minus A. Or what you will say, from V2 to ground, I see an impedance that is Z upon 1 minus 1 by A. So this is the Miller's theorem. You break down this impedance into two parts. Z was connected between V1 and V2. V2 was A into V1. So from V1 to ground you could see Z upon 1 minus A. From V2 to ground you could see Z upon 1 minus 1 by A. That's it. Well and good. Now let's prove this particular theorem. So what we are going to do, this is my V1, this is my V2, V2 is A V1. So from V1 to ground, I will see a resistance. I should say I will see a impedance. That value I don't know, I am calling this as Z1. So from V1 to ground, I see a impedance that is Z1. And from V1, I1 current is getting out. And from V2 to ground, I will see an impedance. That also I don't know. What is that impedance? I will call that as Z2. So my target is to find the value of Z1 and Z2. What is Z1? Z1 is V1 by I1. This is Z1. This is what I need to find. And what is Z2? Z2 is V2 by I2. So this is what I need to find, Z2. Right? So V1 minus V2 by Z is equals to I1. Are you agreeing to this point? See this circuit. V1 minus V2 by Z is equals to I1. Say yes or no. V1 minus V2 by Z is equals to I1. And what is V2? V2 is AV1. V2 is AV1. V2 is AV1. So what will be V1 by I1? That would be Z upon 1 minus A. And that is equals to Z1. Right? So basically Z1 is coming out to be Z upon 1 minus A. What was Z1? Z1 was V1 by I1. Then what did I do? I have the circuit. I told that from V1 I1 current is flowing, from V2 I2 current is flowing. So basically V1 minus V2 by Z1 is equals to I1. So V1 minus V2 is A V1. So from there I am getting V1 by I1 is Z upon 1 minus A. So that is my Z1. What about Z2? What is Z2? Z2 is V2 by I2. So at V2 what I can apply, what I can write is that here what do you see? I1 is equals to minus I2, right? I1 is equals to minus I2. This is also true. So here only I can replace. If I replace I1 equals to minus I2, what I will get? V2 minus V1 by Z is equals to I2. Here I am replacing I1 equals to minus I2. So what I will get? V2 minus V1 by Z is equals to I2. Or from here also you can write V2 minus V1 by Z is equals to I2. That's it. What is V2? V2 is AV1. V2 is AV1. Okay, no. You need to find V2 by I2. So you will replace V1 by, what will be V1? V1 by V2 by A. V1 will be V2 by A by Z is equals to I2. So what will be your V2 by I2? V2 by I2 would be Z upon 1 minus 1 by A is equals to Z2. So this is the proof. Right? Did you understand the proof? What was the proof? V1 and V2 was linearly related by the factor of A. So from V1 to ground you could see a resistance that is Z upon 1 minus A. From V2 to ground you could see a resistance that is Z upon 1 minus 1 by A. So here what did I do to prove the theorem? From V1 to ground I could see Z1 resistance, from V2 to ground I could see Z2 resistance. From V1 I1 current is flowing, from V2 I2 current is flowing. So I could simply apply a KCL KVL here. So V2 minus V1 by Z is equals to I1. So V2 is, what is V2? V2 is AV1. So from there what is Z1? Z1 is Z1 upon 1 minus A. What about Z2? Z2 is V2 by I2. So V2 minus V1 by Z is equals to I2. What is V1? V1 is V2 by A. So from there I got to know Z upon 1 minus 1 by A. That is your Z2. Right? Now, these are the three questions that are in front of you. This is V1, this is V2. V2 is equals to AV1. That is given. V2 is equals to AV1. This is given. V2 is equals to AV1. This is given. So you need to write from V1 to ground. What will be the resistance you see? Tell me. From V1 to ground, what will be the resistance you see? That will be R upon 1 minus A. And from V2 to ground, what is the resistance you will see? From V2 to ground. From V2 to ground, you will see R upon 1 minus 1 by A. From V2 to ground, you will see R upon 1 minus 1 by A. I will write it in a better manner. R upon 1 minus 1 by A. From V1 to ground, R upon 1 minus A. From V2 to ground, R upon 1 minus 1 by A. What about inductor? From V1 to ground, what you will see? From V1 to ground, what you will see? L upon 1 minus A. From V2 to ground, what you will see? L upon 1 minus 1 by A. Now what about this one? From V1 to ground, what you will see? Tell me. Calculate it, then only tell the final answer. Don't be in a hurry. From V1 to ground, what you will see? So I will write down the option. C upon 1 minus A. 1 upon C into 1 minus A. C into 1 minus A. Three options are there. What will be your answer? C upon 1 minus A, 1 upon C into 1 minus A, C into 1 minus A. You are writing the capacitance, not the impedance. Note that you are writing the capacitance, not the impedance. The theorem we proved, this theorem we proved was for impedance. That your impedance will be Z upon 1 minus A. Right? Here, what was your impedance? What is the impedance provided by a resistance? That is R only. So that would be R upon 1 minus A. R upon 1 minus 1 by A. There is no issue with that. What is the impedance provided by the inductor? What is the impedance provided by an inductor? That is Ls, right? Or j omega L. You can write Ls as well, where S is j omega. So the impedance provided by an inductor is Ls, right? So what will be the impedance looking from V1 terminal. From V1 to ground, you would see Ls upon 1 minus A. So if that is the impedance, so what will be the inductance? Inductance will be this much, L into 1 minus A, right? That will be the inductance. Similarly, from V2, what you will see? From V2 to ground, you will see the impedance to be Ls upon 1 minus 1 by A. This is the impedance. If this is the impedance, then what will be the inductance? If I am saying my impedance is 5S, this is the impedance provided by an inductor. So what will be the inductance value? 5 Henry, right? Because the impedance provided by the inductor is Ls. So comparing L, that would be 5 Henry. Are you getting this point? What is the impedance provided by a capacitance? What is the impedance provided by a capacitance? That is 1 by Cs. 1 by Cs. So from V1 to ground, what you will see? 1 by Cs upon 1 minus A. Or you can say 1 by C into 1 minus A into S. This is what you will see. From V1 to ground, you will see 1 upon C into 1 minus A into S. If I am saying I am having 1 by 5 as impedance, this is provided by a capacitor. The impedance provided by a capacitor is 1 by 5s. So what is the value of capacitance? 5. If the impedance provided by a capacitor is 1 by 7s, what is the value of capacitor? 7. If the impedance provided by a capacitor is 1 by C into 1 minus A, then what is the value of capacitance? C into 1 minus A. The impedance provided by the capacitance is 1 upon C into 1 minus A into S. Then what is the value of capacitance? The value of capacitance is C into 1 minus A. Are you getting this point or not? So the value of capacitance here would be C into 1 minus A. Did you understand this or not? So the correct answer will be this. For the inductor, L upon 1 minus A. L upon 1 minus 1 by A. For resistance, R upon 1 minus A, R upon 1 minus 1 by A. For the capacitance, for the capacitance, C into 1 minus A. That is the capacitance. This we are C into 1 minus A. This is the capacitance. What will be the impedance provided? That would be 1 upon Cs into 1 minus A. That would be the impedance. Are you getting this point or not? Say yes or no. Right? So this is the impedance provided. If you know the impedance provided, then you can write down the value of capacitance. Right? This is simple network analysis only, but still I know a lot of guys are not comfortable in network analysis as well. Yeah. So this we have explained. And tell me what will be the value V2 will see. How much capacitance V2 will see. This you should be able to write down. First, treat it at 1 by Cs. If 1 by Cs was there, what was the impedance it would see? 1 by Cs upon 1 minus 1 by A. So 1 by C into 1 minus 1 by A into S. If the impedance provided by the capacitance is 1 upon C into 1 minus 1 by A into S, then what is the value of capacitance? This is the value of capacitance. So the value of capacitance is C into 1 minus 1 by A. So C into 1 minus 1 by A. This would be C into 1 minus 1 by A. So from V1 to ground, you could see C into 1 minus A. From V2 to ground, this would be C into 1 minus 1 by A. And this is very, very important. It will be highly used when we study the frequency response. When we study the frequency response, this is very important, and this is also important. In analog circuits, we don't use inductor much. Inductor is used in high frequency circuits. So one or two example we may see for inductor as well, but mainly capacitance and resistor will be used. So this is the theorem. This is Miller's theorem. We have seen 3 questions here. V1, V2, V1, V2 is connected. V2 is AV1. So what will be the resistance here? R upon 1 minus 1 by R upon 1 minus A, and here R upon 1 minus 1 by A. Similarly, C into 1 minus A and C into 1 minus 1 by A. Well and good. Let's move on to a question. What is this? Common source amplifier with degeneration, and R0 is considered. Here, instead of writing this, what I would have written, I should have written that your lambda is not equals to 0. That means your R0 is finite. R0 is not infinity. So here your R0 will be considered. Now you will say, sir, you told us that you should not remember that formula because no one will ask you. this question. That common source amplifier, they can ask you the gain of common source amplifier. What did I tell you? I told you that they can ask you the gain of common source amplifier with degeneration, but they will say that R0 is infinity. This is what they will say, right? But here they are not saying R0 is infinity. Here they are saying R0 is finite. So how will you calculate the gain now? So that we will apply the formula and then we will calculate. But that will take a lot of time. What is the shortcut? What is the catch here? How will you do it smartly? So let's check that out. What did I tell you? If there is a resistance and the resistance will be having two nodes. This resistance is having one node is V node, the other node I can call Vx. If there is a linear relation between Vx and V node, then you can apply Miller's theorem. So is there any relation? What you can see here is that here Vx by R naught is equals to minus V naught by 2 R naught. Say yes or no. This current is equals to negative of this current. Vx by R naught is equals to minus V naught by 2 R naught. Well and good. So what is your V naught by Vx? That is minus 2. So basically your V naught is minus 2 Vx. V naught is minus 2 Vx. So this V naught I can write down is minus 2 Vx. So now what you can say? From Vx to ground, what was the scene? Impedance Z was there. This was V1. This was V2. V2 was A V1. So from V1 to ground, what I could see? From V1 to ground, what I could see? Z upon 1 minus 1 by A. The one which is alone. What is alone? Who is alone here? Okay, wait a second. Did I do any calculation mistake here? Did I do any calculation mistake? Vx by 2R, Vx by R naught. Yeah. So V1 is this side. V1 is this side. V2 is depending on V1 by minus 2. Right? So from V1 to ground, what do you see? Z upon 1 minus A. So from Vx to ground, what you will see? R0 upon 1 minus A, and A is 2. So R0 upon 1 plus 2, R0 by 3 you will see. Are you agreeing to this point or not? So did you understand this? This is Vx, this is minus 2 Vx. This is Vx, this is minus 2 Vx. The one which is alone, that we will say, that guy will say that from Vx to ground I will see R0 upon 1 minus A, and A is minus 2. So R0 by 3. So the one which is alone, that will have 1 minus A, and the one which is not alone, this guy is not alone, this is having minus 2 with it. So what it will say? From V0 to ground I will have R0 upon 1 minus 1 by A. That means R0 upon 1 minus 1 by 2. So R0 upon 3 by 2. That means 2 R0 by 3. So we will write it down. So what it will say? This was the thing that we have already studied. Let's close it in a box. So yeah. So what Vx will say? That from Vx to ground I will see, from Vx to ground I will see R0 upon 1 minus A, that is 2. So that would be R0 by 3. And what V0 will say? V0 will say that from V0 to ground, I will see R0 upon 1 minus 1 by A, that is 1 by 2. So it will be 2 R0 by 3. From V0 to ground I will see R0 upon 1 minus 1 by A. 1 minus 1 by A. A is minus 2. Here your A is minus 2. A is minus 2. A is minus 2. A you are getting is minus 2. So this will be 2 R0 by 3. This is R0 by 3. So how your circuit is reduced now? From V0 to ground you are having R0 by 3, and here, sorry, from V0 to ground you are having 2 R0 by 3, and from Vx to ground you are having R0 by 3. So this R0 parallel with R0 by 3. Are you getting this point? These will come in parallel. So let's add a page. This was very interesting question. These kind of questions are not asked in GATE yet, but certainly they will be asked, and I am telling you, forget about the student. Even the teachers will not be able to answer. Now, please don't think I am arrogant or anything, but I have seen the content by the educators, how they teach in gate field. So yeah, so there are many loopholes. So these kind of loopholes are there which needs to be filled, and we will fill it. So here we are having V in. This is your V naught. This was your Vx, and in between you had R naught. So this was your R naught. This was your 2 R naught. So what did you concluded? That from V naught to ground you will see R naught by 1 plus 1 by 2. So from V naught to ground you will see 2 R naught by 3, and this 2 R naught is already there. So 2 R naught parallel with 2 R naught by 3. If you calculate it, it will be, as far as I remember, it will be R naught by 2. You can calculate, right? 2 R naught parallel with 2 R naught by 3. So 8 R naught by 3. So this will be 4 R naught by 2. Yeah. So parallel combination will be R naught by 2. And what about this? R naught parallel with 2 R naught. So no, sorry. R naught parallel with R naught by 3. So from V naught to, from Vx to ground we are seeing R naught by 3. So what is that combination? R naught into R naught by 3 plus 4 R naught by 3. R naught by 4. This will be R naught by 4. R naught by 4. This is R naught by 2. So what is the value of V naught by V in now? Our target was to find the V naught by V in. Our target was to find the V naught by V in, right? But if we had found V naught by V in by applying equations, it would be a bit difficult. So better we solved it like this. So what will be our V naught by V in now? We already remember what is V naught by V in. That is minus Gm Rd. What is our Rd now? Rd is R naught by 2 upon 1 plus Gm Rs. What is our Rs now? R naught by 4. That would be minus Gm R naught by 2 plus divided by 4 plus Gm R naught by 4. That would be minus 2 Gm R naught upon 4 plus Gm R naught. This will be your V naught by V in. Well and good. Did you understand this problem or not? What did I do here? I could have simply calculated with the other method as well by writing down the equation, but I needed to apply Miller's theorem. So I applied the Miller's theorem. Vx and V naught, I could find that they are having a linear relation. That is, V naught is equals to minus 2 Vx. So from V naught to ground, I will see R naught upon 1 plus 1 by 2. So 2 R naught by 3, and from Vx to ground, I will see R naught by 3. Now circuit is reduced like this. Now for this configuration, I remember the final answer. That is minus Gm Rd upon 1 plus Gm Rs. Minus Gm into Rd. This is our Rd. So Rd is R naught by 2 upon 1 plus Gm Rs. This is our Rs. That will be 1 plus R naught by 4. And if you don't remember, from here also you can calculate the final answer. But this is the common formula which everyone remembers. So even if you don't remember, from here you can calculate. And if you remember, you can directly apply the formula minus Gm Rd upon 1 plus Gm Rs minus Gm R naught by 2 upon 1 plus Gm R naught by 4. 4 1 4 is there. 2 will go upward, minus 2 Gm R naught upon 4 plus Gm R naught. So this is how I calculated the final answer. There are other ways as well. You can find, simply write down the equation and you will get to the final answer. I guess that will also not be very complex, right? Because if you just apply the equation, that will also not be very complex. You will also get to the final answer very easily. Okay, so you can apply the equations as well, and or by using this thing, by applying the Miller's theorem, you can also calculate. Well and good. Let's see the other way of biasing. So why did we study Miller's theorem? Out of nowhere, suddenly I taught you Miller's theorem. Why? Because we are going to use it. So first we studied about this biasing, that potential divider. Here we are doing the potential divider. So I will call it potential divider biasing. There is no specific name. So let's just call it potential divider. So first we studied about this biasing. This was the first way. I hope you have understood it. You could write down the VGS value. You could write down the V0 value. Then you could do the small signal analysis. When you did the small signal analysis, you could find out the gain. Then you could find out the input resistance. Then you took the condition that your input is having the RS resistance. Then you find out the gain again, and you find out the input resistance and output resistance. Right? Then suddenly I taught you Miller's theorem. Why so? Because now I am going to teach you another way of biasing, that is self bias. So what different we are going to do here? Self bias circuit. This is the self bias circuit. So what is happening here? Yeah. So let's do the DC analysis. In DC analysis, this will be gone. What is this? This is small signal input voltage. Small signal input voltage. This is small signal input voltage. So what will happen? In DC analysis, what will happen? This will simply be replaced with RD. This is grounded and this is RS. And this is your V0. This will be VDD. Right? Tell me one thing. Is there any current in this resistance RS? Is there any current? 0 ampere current is there. You are doing the DC analysis. Why 0 ampere current? Because this will be 0 ampere current. If this is 0 ampere current, then the same current is flowing in this loop. So there will be no current in the RS. Right? There will be no current in the RS. So your VGS, capital VGS is equals to V0 only. And what is your VDS? VDS is also V0. There is no current, so VDS is also V0, VGS is also V0. What is your V overdrive? V overdrive is VGS minus VT, that is V0 minus VT. So here what you can see, your VDS is greater than V overdrive. That means it is always in saturation. So you don't have to worry about this transistor. Here, this transistor will always be in saturation. The only concern is what will happen? Here ID current will be flowing. Now there is zero current, so the same ID current will be flowing here. So the only concern is that VDD minus ID into RD should be greater than 0. Because to turn on the transistor, your VDS should be greater than 0, right? Your VDS should be greater than 0. So only concern is VDD minus ID RD should be greater than 0 and should be greater than VT as well. Why so? Because this is equals to VGS as well. V0 is equals to VGS. So VGS should be greater than VT. And what is VGS? VGS is V0. And what is V0? V0 is VDD minus ID into RD. So your only concern is make sure that VDD minus ID into RD is greater than VT. That's it. Ensuring what this will ensure? Ensuring that MOS is on. And if MOS is on, it will certainly go into saturation region. There is no chance it will go into linear region. There is no chance that this configuration can go into linear region. This will certainly be in saturation region. Why so? Because your VGS is V0, VDS is V0 and V overdrive is V0 minus VT. So that means VDS will always be greater than V overdrive. So it will always be in saturation. Let's assume my V0 is 3 volt, my VT is 1 volt. So what will be my V overdrive? 2 volt. What will be my VDS? That will be 3 volt. So 3 volt will always be greater than 2. So always VDS will be greater than V overdrive. So always it will be in saturation, and you have to make sure that your VDD minus ID into RD, that means your VDS or VGS should be greater than VT. That will ensure that your transistor is on, your MOSFET is on. So this is what you need to ensure. So this is the advantage here, right? Now let's do the AC analysis of this configuration. We are doing the small signal analysis. Now there is a catch in Miller's theorem, and that you will realize here. So this is your Vs, this is your V0. Now what people generally do, those who have already studied, they might have done this thing as well. What they will do, that here we are having RS resistance, this is the RS resistance, this is Vs, one node of RS is connected to Vs and the other node of R, this should not be RS, this should be RF. I should write it as RF, R feedback. Okay, I am really sorry, I am writing RS, it should be R feedback, RF, R feedback. This should be R feedback. So now what will some people say? Some people will say that, sir, one node of RF is connected to Vs and the other node of RS is connected to V0, right? So what they will say, sir, V naught is minus Gm into Rd into Vs, because this is common source amplifier. So V naught is minus Gm into Rd into Vs. So what I can do, I can apply Miller's theorem, and at the input side from the Vs, what I can write, Rf upon 1 minus A, that means Rf upon 1 plus GMRD, and the output side, what I can write from V naught side, at the node of V naught, what I can write, Rf upon 1 plus 1 by GMRD. And now this particular thing is completely wrong. This is completely wrong. Why is it so? Why is it so? What is the catch here? What we are doing wrong here? Why it is wrong? What did I tell you? That Vs and V naught should be linearly related. So it is related by the factor of minus GMRD. Is that correct? When your RF is connected, then will your V naught will be GMRD Vs? It will not be. Why so? Let's check that out. This is Vs, your VGS is Vs, so what will be the current? GMVs. Now will that current flow from RD? Will that current completely flow from RD? Say yes or no? No. The current will not completely flow from RD. That current can go into RF as well. Now you will not say, sir, this current is 0. So how RF will have current? Kyun? The source can drive some current. The source can also drive some current. So the RF current will go into the source completely. So RF can also have some current. In case of DC analysis, RF was not having any current because there was no supply here. So the current has to flow like this. But here we are having the supply. Here we are having the Vs. So even if the current is 0 ampere, even if the input current is 0 ampere, that doesn't mean that RF cannot have some current. Whatever the current RF is having, that will go into the supply, or supply can drive some current. So here we are having Vs, here we are having a node. This will be a battery. So from battery, current can go out, current can come in. So you can't say that RF cannot have some current. RF will have some current. So if RF is having some current, that means the complete GMVS is not going into RD. So V naught is not minus GMRD into Vs. V naught is something different. Are you getting this point? So that we have to find what is V naught. Say yes or no. Understood? So that is wrong here. A lot of time people write it down this way, that V naught is minus GM into RD into Vs, then we can apply this thing. When this will be applicable? When this thing will be applicable? Tell me. When RF is too large. So whenever you are applying Miller's theorem, you need to make sure that your RF, whatever that you have connected, this impedance is very large. If this impedance is very large, then what will happen? The GMVS current will completely flow from RD. Because if RF is very large, it will not drive any current. The complete current will flow from RD. So this is the catch when we are applying the Miller's theorem, and every time we ignore it. So in the examination as well, it will be written that your RF is very large. If RF is very large, that means it will not drive any current. That means the complete GMVS will be flowing through RD. So your V naught will be minus GM into RD into Vs. Now you can apply the Miller's theorem. So in the examination, it will be written. Now let's assume in case of RF, if there was capacitance connected. In case of RF, there was capacitance connected. Then what would have been written in the examination? That CF is very large or very low? Very low, right? In the examination, it would have been written that CF is very low. If CF is very low, that means impedance provided by this will be very large. If CF is very low, what is the impedance provided by the capacitor? That is 1 by CFS. So impedance provided by this will be very large. So the CF will not drive any current. Otherwise, it will drive any current. Well and good. Understood? So here also, this RF will drive some current. So it's not that you can apply Miller's theorem directly. You can apply Miller's theorem, but the value of V naught will be different. Value of V naught will not be this. This is wrong here, right? So the wrong thing is this. So let's write down the correct answer. Also, there will be R naught as well. So there will be R naught as well. RD parallel R naught you can write. So R naught also we will consider. So let's do the correct analysis. What will be the correct analysis? Let's do the, we are doing the AC analysis. So this VDD will already be gone. So this was the MOS. Here you are having the RF. This is V naught. This is ground. So from V naught to ground you are having RD. And also from V naught to ground you are having R naught as well. Because R naught is connected between drain to source. So RD parallel with R naught. This is your Vs. And the current flowing here would be Gm into Vs. That current will go from RF as well and from RD parallel R naught as well. The current will go from RF also from RD parallel R naught. So what you can do, you can apply nodal analysis and then you can find out the final answer. What I am saying, you can apply nodal analysis, nodal at V naught. Nodal at V naught. So what that would give you? V naught into RD, V naught plus RD by R naught. Sorry, V naught by RD parallel R naught plus GMVS, this current plus this current plus this current now, plus V naught minus Vs by Rf is equals to 0. From here you can find out the value of V naught by Vs, right? You can find it out on your own. Or do you want me to write it down? Okay, I will write it down. Okay, so let's write it down. This was the equation. I hope nothing is wrong here. V naught by RD upon R naught, GMVS and V naught minus Vs by Rf. Okay. All the current I have written. From V naught node, this current plus this current plus this current. Nothing else is there. So what I can see here is that V naught by RD parallel R naught plus V naught by Rf is there. Is equals to, no, plus GMVS is equals to Vs by Rf plus GMVS is equals to Vs by Rf. Vs by Rf minus GMVS. All correct? All correct. Yeah. So this would be V naught by Rf parallel with RD parallel with R naught would be equals to Vs by minus 1 by Gm parallel with Rf. Is that so? Minus 1 by Gm parallel with Rf. So what is your V naught by Vs now? That is Rf parallel with RD parallel with R naught minus 1 by Gm parallel with Rf. Right? This is V naught by Vs. Is that correct? Let me check the calculation. Yeah, so that is correct. That will be the gain. There is one more way of writing the gain. We will see method 2 of writing the gain. Method 2. Okay, one more way is there. That is method 2. What is the other way? So the MOS circuit is given. This is grounded. From V naught, what you can see, RD parallel R naught. Here there was Vs, and between this was the scene, right? RF, right? This was the scene. So this Vs is applied to MOS as well. This Vs is applied to MOS as well and also to RF as well. So I can write it down in this manner. Are you satisfied with this? I can write it down in this manner. Vs is applied to both MOS and as well and RF as well, right? Vs is applied to MOS as well and RF as well. And from V0 to ground you see RD parallel R0. So now I can apply superposition. Applying superposition. So first I will consider only this one. First I will consider only Vs, this one. So what will be my V naught? This will be shorted. So from V naught to ground, RD parallel with R naught parallel with RF will come. So what will be my V naught? That would be minus GM RD parallel with R naught parallel with RF into Vs plus. Now what I will do? I will consider only this Vs. Sorry, I will consider only this Vs and this will be grounded. Now if this is grounded, then what will happen? There is no current in this MOS. If Vs is grounded, there is no current in this MOS. Say yes or no. There is no current in this MOS. So this will simply be open circuited. If this is open circuited, then what will be the scene? If you are not able to understand, I will explain it once again. No worries. But till now, try to understand it. So what will be the condition? This will be the condition. Right? Vs, Rf, V naught, Rd parallel R naught, because there is no current in this MOS. MOS is open circuited. Why so? Because Vs is grounded. Vgs is 0. So MOS is open circuited. So what will be your V naught now? V naught will be Rd parallel R naught upon Rf plus Rd parallel R naught into Vs. So what will be your V naught by Vs? That you can write down minus Gm Rd parallel R naught parallel Rf plus Rd parallel R naught upon Rf plus Rd parallel R naught. So that will be the gain. So in the examination, they can give you any expression. They can give you this expression as well. Like they will give you the configuration. They will ask you what is the gain. So in 4 options, you can have this expression as well, and you can have this expression as well. So you should be comfortable with both of the analysis. That what will be the gain. So this can also be the gain, and this can also be the gain, right? If you solve this and solve this, you will get the same answer. You can try solving it down. You will get the same answer. Okay, yeah. So what did we do here? What was the circuit? Let's revise it once again. So this was the circuit. Vs was applied to both MOS and RF. So what did we do? We applied superposition. First we consider only this Vs. We did not consider this Vs. So what will happen? This will be grounded. So RF parallel with RD parallel with R naught will be there. RF parallel with RD parallel with R naught. So what will be your gain? This will become a simple common source amplifier. So what is the gain for common source amplifier? The current will be GMVS here. The current will be GMVS. The GMVS current will be flowing through the resistance RD parallel with R naught parallel with RF. So the gain would be minus GM into RD parallel with R naught parallel with RF. That's it. Then we consider only this Vs. Only this Vs. Now this Vs will be shorted. Now if this Vs is shorted, that means the current is gone. The MOSFET current is gone. So only the potential divider scene will be there. So RD parallel with R naught upon RF plus RD parallel with R naught into Vs. That will be your V naught. So from V naught by Vs, you go to this answer. Well and good. Okay. Yeah. Now this is your gain A. This is your gain A. So if you were saying that this was my Vs, what you were saying that this was my Vs, and from Vs the RF was connected, and this was my V naught. So your V naught was A Vs, where your A was what? This expression. This was your A. Are you getting this point? So your A was, I have to write it down again. Okay. I have to write it down, so I will write it down. Minus GM RD parallel R naught parallel RF plus RD parallel R naught upon RF plus RD parallel R naught. Right? This is again A. Now you can say that, and now you can apply the superposition theorem. Now you can say that from Vs to ground I will see, from Vs to ground I will see Rs upon 1 minus A being this value, and from V0 to ground I will see Rs upon 1 minus 1 by A, and A being this value. Say yes or no. Understood? Understood this analysis? So why did I first I taught you the Miller's theorem, then I taught you the application of Miller's theorem, then I taught you where it cannot be applied. In the self-biased circuit, it cannot be directly applied, that you cannot directly say that my gain would be minus GMRD. No. My gain would be this much. So always, what is the main point that you understood here? That you always have to take in consideration this resistance RF. Here in the previous notes here, that considering R, your V2 was AV1. Here considering L, your V2 was AV1. Here considering C, your V2 was AV2. Are you getting this point? Now in this one, considering R0, even if this R0 is there, still your V0 is minus 2Vx. Are you getting this point? This R0 was there, still your V0 was minus 2Vx. If this R0 was not there, if this R0 was something else, if this R0 was some 6 R0, then what would be your V0? That will still be your minus 2Vx. Then you can again apply the Miller's theorem here. So considering R0, we calculated V0. Are you getting this point? Considering R0, we calculated this V0. What did we do? We applied this current is equals to minus this current. There is no role of R0 here. Are you getting this point? No matter whatever you put in this place, even if you put inductor, even if you put capacitor, even if you put any circuitry, even if you put diode, V0 will always be equals to minus 2Vx. Here also, by making sure that even if the resistance R is connected, your V2 will always be equals to AV1. Here also your V2 is equals to AV1. Here also V2 is equals to AV1, irrespective of capacitance, inductance or resistance. But here, if we connected RF, the gain changed. If RF was not there, the gain would have been minus GM into RD. But if RF is connected, then the gain has changed. The gain has changed to, previously the gain was minus GMRD, now the gain has become this much. So the gain has changed. So if the gain is changed, then this value of resistance will also change. This is not RS, this is RF. So this was the main thing that we always forget, that we find the gain without considering the feedback resistance. What they do is that they forget this resistance, and they write down the gain. They write down the gain is minus GMRD. No, you have to consider this resistance. Considering this resistance, whatever the gain is, considering RF, what the gain you get, right? That will be your A. Your A will not be without RF. You have to consider RF. That is the catch. Okay. Now they can ask you more thing in the self-biased circuit. In the same circuit, they can ask you input resistance. So tell me what will be your answer for input resistance. So in the same circuit, they can ask you input resistance. Yeah. Small signal analysis we are doing. Input resistance means resistance from this side. R in. Tell me what you will do here. What you can do, from Vs to ground, you can replace this RF. That will be replaced by RF upon 1 minus A. And from V0 to ground, it will be replaced by, from V0 to ground, it will be replaced by RF upon 1 minus 1 by A. Right? And this RF will be gone. So tell me, what is the input resistance now? There is no current here. There is 0 ampere current. So what is the input resistance? Rin is simply RF upon 1 minus A. Well and good. And tell me what will be the output resistance? Input resistance slash output resistance. Tell me what will be the output resistance? R out. So for writing R out, what you will do? You will short circuit this. You will short circuit this. If Vs is shorted, that means there is zero current in this one. So from V0 to ground, what do you see? Rd you see parallel with this resistance. Also R0 is there. So Rd parallel R0 parallel this resistance Rf upon 1 minus. So this is the output resistance. This is the R0 you see from here, right? What is the R0 you see? Rd parallel with R0, Rd parallel with R0 parallel with Rf upon 1 minus 1 by A. Vs is shorted. If Vs is shorted, that means there is zero current in the MOS. So MOS is simply open circuited. So Rd parallel with R0 parallel with Rf upon 1 minus 1 by A. 1 minus 1 by A. So this is the output resistance you see, and this is the input resistance. And what is the value of A? Value of A is minus Gm Rd parallel with Rf parallel with R0 plus Rd parallel R0 upon Rd parallel R0 plus Rf. This is the value of A here. So you don't need to mug it up. All these things are for analysis purpose. It's not that I am asking you to remember all these things, but you should have the clear idea of the analysis, how we do the analysis, right? Rf is there, V0 is V0 is related to Vs by a factor of A. What is the factor of A? This is the factor of A. What is R in? What is R0? So everything you are comfortable now. So why did we pick this self biased circuit? First we did the DC analysis. DC analysis was very simple. You have to make sure that VDD minus ID into RD is greater than VT, ensuring MOS is on. Then we saw the AC analysis. Here what did we show? What is the wrong thing that people do? That is they write V0 equals to minus Gm into RD into Vs. They forget that there is RF connected. If RF is connected, the gain will be different. The gain will not be minus Gm into RD into Vs. So the gain will be different. So applying this thing is wrong. This you can apply only when correct only when RF is very high. RF is very high. If RF is very high, that means your V0 will be minus Gm into RD. V0 will be minus Gm into RD, so you can write down this expression then. So it is not usually correct. So for usually correction, you have to find out the value of V0 considering RF. So value of V0 considering RF you got is this much, or you applied second method, then you got this much by applying the superposition. Then you got to know that this is Vs, this is V0. So they are linearly connected like this. So Vs to ground Rf upon 1 minus A, from V0 to ground Rf upon 1 minus 1 by A. So this is how you can replace. So you replaced your circuit something like this. So Rd was there, R0 was also there. From Vs to ground you replaced it Rf upon 1 minus A. From V0 to ground you replaced it Rf upon 1 minus 1 by A. So what is the output resistance? Output resistance is Rd parallel with R0 parallel with Rf upon 1 minus 1 by A. And what is the input resistance? That is Rf upon 1 minus A. And this is the gain. That's it. Are you able to understand? Now we are done with the common source amplifier. After this we will see an assignment. There we will cover up a lot of circuits. In the assignment we will cover up a lot of circuit. We will see every kind of biasing of common source amplifier. And with that we will be done with the common source amplifier. So in the next lecture we will see an assignment, and that will help you a lot in understanding the problems. Okay, thank you. Hello everyone. So in this video we are going to solve the assignment 6. So we have seen the common source amplifier. Now we are going to solve an assignment. Okay, so let's see the questions. This is the first question. You can solve it on your own, then you can watch the solution. This is the first question. I will show you all the questions. This is the second one. This was the second question, and these were the questions. These were the information given, and these were the questions. And, this is the third one. Fourth. Okay, that's it. No other question is there. If there is anything that I missed, this I missed, I guess. Yeah, this is one more question. So you can see all the questions now. Now I will give the solution of all the questions one by one. So let's start solving the first question. So mu n CX W by L value is given, Vt value is given, and it is given that lambda is 0. They are saying that small signal model is drawn. So this is the small signal model. Small signal model means AC analysis. So AC model they have drawn already. There is no VDD bias, there is nothing like that. it is present there, but it is not shown in this model. VDD is present here. There is certainly VDD present. Here there is certainly VGG present. So they are present, but they are not being shown because they have only drawn the small signal model. Now they are saying that the gain magnitude is 8. Gain magnitude is 8. So what is the gain of this circuit? This is a common source amplifier. What is the gain? Simply minus GM RL, right? You know this thing. And the magnitude is given, that is equals to 8. You need to determine the bias current. What do you mean by bias current? DC current. You need to determine the DC current. Now you will say, sir, we need to determine the DC current. So I have to do the DC analysis. And for doing the DC analysis, I need to know the VDD value, VGG value. No, it's not necessary that you need to do the DC analysis. By observing the data, you can find the DC current as well. Let's check that out. Minus GMRL is given, that is equals to 8. So from here, what you can determine? GM into RL is 50 kilo ohm. That is equals to 8. So GM value is 8 by 50k. What is 8 by 50k? Where is the calculator? Eight by 50. 8 by 50k is 0.16 millisiemens. So this is the value of GM we are getting. This is our GM. Now you know the formula of GM. There are three formulas of GM. Mu n CX WIL VGS minus VT. Is that of any use? No, because you need to determine the IDC value. You need to determine IDC value. So that is of no use. The second formula is 2 IDC upon VGS minus VT. The second formula is 2 IDC upon VGS minus VT. So here you need to determine IDC. Okay, that is fine. But do you know the value of VGS minus VT? You know the value of VT, but you don't know the value of VGS. So this is also of no use. What is the next formula? The next formula is GM equals to root 2 mu n COX W by L ID. This is the formula, right? So you know the value of mu n COX W by L. You know the value of mu n COX W by L, and IDC you need to find. And GM value you also know, that is 0.16 millisiemens. From here you can find out the value. So root 2 mu n COX W by L is 100 micro into IDC. That would be equals to 16 into 10 to the power minus 5, right? 16 into 10 to the power minus 5. So it would be 2 into 10 to the power minus 4 into IDC is equals to 256 into 10 to the power minus 10. So IDC here would be 256 by 2 would be 128, and this would be 10 to the power minus 6. So IDC would be 128 microampere. Sometimes calculation becomes a problem in these kind of questions, but here I am showing you every single step of calculation as well, so that you don't mess it up in the examination. So this is how you solve these kind of problems. Just don't get into complex calculations. This is just 0.16 milli, so I wrote 16 into 10 to the power minus 5. Then square will come here, 256 into 10 to the power minus 10. Then IDC would become 128 microampere. This is our final answer. This is a very simple question. Just I picked this question so that you shouldn't think that if I have to calculate a DC parameter, I have to do the DC analysis. No, it's not necessary. Without doing the DC analysis as well, you can find the DC parameter, right? Let's move on to the next question. So this is a big question. There are three questions involved in this one. So the given scenario is mu n COX W by L value is given, VT value is given, the same value is, and transistor is biased at 128 microampere. It is biased at this current only, which we calculated. So it is biased at 128 microampere current. At operating point, your VDS is equals to VGS plus 1. This is your VDS. VDS is equals to VGS plus 1 at operating point. And the bias current flowing through R12 is 10 microampere. What do you mean by bias current? That means DC current. DC current flowing through R1 and R2 is 10 microampere. So you have to determine the VDD value, you have to determine R1, R2 value, and you have to determine small signal voltage gain. So first we need to determine the VDD value. So let's just do the DC analysis first. You have to use the given data smartly. So we are doing the DC analysis first. So while doing the DC analysis, capacitors will be open circuited. This is R1, this is R2. Then there is this MOS, this is grounded. Then there is this RD. VDD is also there. And this is also VDD. You need to determine the value of VDD only. The bias current is, there will be no current here. There will be 0 ampere current here. And the bias current is 128 microampere. This is given. This current is 120. No, sorry. This current is 10 microampere. Sorry. The bias current flowing through R1 and R2 is 10 microampere. So this current is 10 microampere. And this current is 128 microampere. And RD value is given, that is 50 kilo ohm only. This is 50 kilo ohm. So this capacitor is open circuited, this capacitor is also open circuited, right? Only this much circuit is there, this much circuit, right? So you need to calculate the VDD value. What is given? Given is VDS equals to VGS plus 1. What is your VO drive? VO drive is VGS minus VT. VGS minus VT, that would be equals to VGS minus 1, right? So here VDS is greater than VO drive. That means it is working in saturation region. That's for sure. It is working in saturation region. Tell me, what is the value of VDS now? In this circuit, what is the value of VDS? VDS is, this is VDS. VDS is VDD minus ID into RD. VDS is VDD minus ID into RD. Are you agreeing with this point? Because this is drain. So VDD minus ID into RD. So 50 kilo ohm into 128 micro. 6.4 it would be. So VDS would be VDD minus 6.4. This would be your VDS. This is equation 1, I can tell. This is our VDS. Because I am going to use this one. This is given. This thing is given. This is given. I am going to use this one. Now, do you know the value of VGS? No, you don't know the value of VGS. But you know one thing, that is the current is 128 microampere. What is given? Given, that is ID is 128 microampere. This is given. You know the formula of ID, that is mu n COX W by 12 VGS minus VT whole square. That is equals to 128 microampere. Mu n COX W by L value is 100 micro by 2. VGS minus VT value is 1. That is equals to 128 micro. So 2 point, here what will happen? Mu n COX W by L is 100 micro only, you know? Yeah. So what will happen? 2.56 it would be. So VGS minus 1 would be this, and this will get cancelled. This is 50. This is 256. 256 by 100 would be 2.56. And under root of this. What is the under root of 2.56? It is 1.6. So VGS would be 2.6. So VGS value is 2.6 volt. And what is given? This is the equation 2. It is given that VDS is equals to VGS plus 1. It is given. And you know what is VDS? VDS you calculated VDD minus 6.4. What is the VGS value you are getting? 2.6 plus 1. So VDD value will be 10 volt. That's it. This is the final answer. So how did I thought of it? Look, if I need to determine VDD value, that means I have to consider VDD in my equations. I need to take VDD action. I need to take VDD in action. तो मैंने VDD को action में ले लिया. कैसे लिया? How did I take it in action? I determined the value of VDS. VDS is VDD minus ID into RD. So VDD minus 6.4. Now to use this equation, I need to determine the value of VGS. For that, I have the current 128 microampere. So I determined the value of VGS. VGS is 2.6 volt, and then I calculated this value. Well and good. Now I need to calculate R1 and R2. For that I will use this much thing. So I need to calculate R1 and R2. I have the value of VDD. VDD is 10. So let's calculate the value of R1 and R2. So what is given? What is given? Given that VDD by R1 plus R2 is equals to 10 microampere. Are you agreeing to this point? VDD by R1 plus R2, this current VDD by R1 plus R2 is equals to 10 microampere. What is the value of VDD? VDD is 10 microampere. Sorry, VDD is 10 volt. VDD is 10 volt. So 10 by R1 plus R2 is equals to 10 microampere. So R1 plus R2 is 1 mega ohm. This is your R1 plus R2. Now, how do I get another equation? Because there are two variables, R1 and R2, two variables are there. So I need to determine one more equation. So how do I get that? I know one thing, that my VGS value is, I know one thing, that is my VGS value is 2.6. And here what is the VGS value? VGS value is 10 micro into R2. Say yes or no. This potential is equals to VGS only. So 10 micro into R2 is equals to VGS. Here VGS is equals to 10 micro into R2, and that is equals to 2.6. So here what will be the value of R2? That would be 260 kilo ohm, right? Because 10 would come here, this would make 0.26. 0.26 into 10 to the power 6. So 260 kilo ohm. R2 would be 260 kilo ohm. So this is one of the answer. And if R2 is 260 kilo ohm, then what will be the, what is 1 mega ohm? You know this thing. What is 1 mega ohm? 1 mega ohm is 1000 kilo ohm. This is 10 to the power 6, so it would be 1000 into 10 to the power 3. So what will be the value of R1? That would be 740 kilo ohm, right? So we have calculated the value of R1 and R2 as well. Very easy, very simple. Just you need to think in the examination very quickly. If a lot of data is given, you need to think in the examination which data is useful for me. So how you will get that? By the practice. That's why we are solving the question. If we solve more and more question, we will be more comfortable with these kind of analysis, right? I am also telling you how I am thinking the problem. Now the next question is, you need to determine the small signal voltage gain, which is very easy. So how will you determine small signal voltage gain? I guess I can copy this circuit. We will be changing it, but let's just copy it for once. So you need to determine small signal voltage gain. For determining the small signal voltage gain, this biasing we have already seen in the previous lecture, right? So for determining the small signal voltage gain, what we will do? These will be shorted. We are having all the values of R1 and R2 as well. R1 was 740, and R2 was 260. What will happen to this? This will be, this will be shorted. Now both this R1 and R2 will come in parallel, because from here to ground you are having, from this potential to ground you are having 740, from this potential to ground you are having 260. So both will come in parallel, right? And this will also be open circuited. So this 50 and 50 will also come in parallel, because from V0 to ground you are having 50 kilo ohm, from V0 to ground you are having 50 kilo ohm. So what will be our final circuit? Let's draw our final circuit. That would be 100 kilo ohm. Then these two will come in parallel, that is 260 kilo ohm parallel with 740. This we will be having some answer. Then we are having the MOS and from V0 to ground, V0 to ground 50 kilo ohm, from V0 to ground 50 kilo ohm. $50 kilo ohm parallel with 50 kilo ohm would be 25 kilo ohm. So what will be the gain? What did I tell you? First write the potential here. Then this potential will be amplified with GM factor. Write down the potential here. This potential will be amplified with GM factor and will be flowing through this resistance. Right? So you can write down your gain. If you have seen the previous lecture, it will be a cakewalk for you to write the gain. First, determine this potential, V potential, then this will be amplified with the GM factor, the current flowing will be GMV and that will be flowing through the resistance. So this current would be GMV. So first we need to determine this factor. So 260 kilo ohm parallel with 740. So 260 into 740, that would be 192.4. 192.4 kilo ohm. So what will be this potential? 192.4 kilo ohm. 192.4 divided by 292.4. So this potential will be 0.66. 0.658 you can say of Vs. So V is 0.658 of Vs. So what will be your V0? So V0 will be minus Gm into RL. RL is load is 25 kilo into this V potential. V potential is 0.658 into Vs. So you have all the values but you don't know the value of Gm, right? So how we can calculate the value of Gm? Because we have all the data, so certainly we can calculate the value of Gm as well. So Gm, how do we calculate Gm? Since I know the value of Vgs minus Vt as well, I know the all values from, I have multiple formulas. So from anywhere I can calculate the value. The simplest formula I find is 2 IDC upon Vgs minus Vt. So I guess I will apply this formula only. So 2 into IDC, what was the IDC? 128 microampere. What was the VGS value? It was 2.6 as far as I remember. VGS value was 2.6. Here you can apply all the three formulas because you also have the value of mu n CXW by L, VGS minus VT, right? So this is the first formula. What is the second formula? 2 IDC upon VGS minus VT, that we are applying. Also you can apply the third formula, root 2 mu n CXW by L into IDC. So all the values you are having, you can apply any formula. So this would be 256 micro divided by 1.6. 256 divided by 1.6. So 160 micro. We are getting 160 micro. Okay, I guess I calculated the GM value before as well, somewhere here, as far as I remember. Okay, forget it. So GM value is 160 micro. So what will be your V0? V0 will be 166 micro into, okay, let's write it down in this manner, minus 160 into 10 to the power minus 6 into 25 into 10 to the power 3 into 6 into 0.658 Vs. So let's calculate this value. 160 into 25. 160 into 25 into 0.658. That is 2.6 into 10 to the power 3. So my answer would be 2.63. 2.63 minus. So this is my V0 by Vs. So this is the small signal gain I am getting. That is minus of 2.63. Okay, and don't think the calculation are big. These calculations are not big. These kind of calculation are asked in the examination. Even tougher calculation will be asked. So you have to be ready with that, right? So these calculations are very, very easy actually. This is not pretty big. When I deal the gate PYQs, you will see there is tougher calculation involved. Okay, so You should be ready with the calculation. You should be able to deal with micro, kilo. So what is the best way? This is the best way. That micro 10 to the power minus 6, kilo 10 to the power 3. You just need to develop the habit of writing the micro and kilo in the same manner. Even with the milli would be 10 to the power minus 3. So develop the habit of that. There will be square root involved. There will be squares involved. So you should be comfortable with all those things. You should be comfortable with this problem. Let's just assume in some problem you have to calculate root of 10 to the power minus 3. What you will do? The best way is break it down into 10 to the power minus 2 into 10 to the power minus 1. This you know, this will be 10 to the power minus 1 and 10 to the power minus 1. So you just need to calculate 0.1 into root of 0.1. So what will be root of 0.1? 0.1 root into 0.1. So your answer would be 0.0316. So your answer would be 31.6 milli. So that's how you can make your calculation better, because I have seen a lot of aspirants getting confused in these kind of calculation. Just because of calculation, they lose their 2 or 3 marks. So that should not happen. When I teach device physics, that means when I teach EDC, I will take a lot of calculation in action. So I will tell you how to actually solve the problems in the examination, how to actually calculate in the examination by using the gate calculator. So that we will see when we study the device physics, when we study electronic devices. Okay, yeah. So I hope you are comfortable with this question. Everything is clear. Let's move on to the next problem. Yeah, so this is the next problem. So considering lambda equals to 0, that means considering r naught equals to infinity, you calculated the gain to be minus 4. So when you consider lambda is 0, your gain was minus 4. Then later on, after that, you realize that your lambda is not 0, but it is 0.0625 volt inverse. That is the unit. So your lambda value was 0.0625. Then what is the actual small signal gain? Did you understand the question? First you thought that your lambda is 0. Then what should be the gain? If your lambda is 0, then simply the gain would be minus gm into RL. Minus gm into RL. That value came out to be minus 4. So what is the value of gm? 4 by 25k. So what is 4 by 25? That is 0.8, no? 4 by 25. Oh, it is 0.16, yeah. So it is 0.16 milli. So this is the value of gm that came out to be. Now later you realize that your lambda is 0.0625. That means there will be an r naught coming in action. If lambda is not equals to 0, that means r naught is not infinity. So this r naught will come in action. So now what will be your gain? Actual gain. What is your actual gain now? That is minus gm into r naught parallel with 25 kilo. Right? Because r naught will come in parallel to 25 kilo. So this is your actual gain. You have the value of gm. Yeah, I have the value of gm. You have the value of r naught as well. Sorry, you have the value of 20 kilo to 25 kilo as well, but you don't know the value of r naught. So from where will you calculate the value of r naught? Let's call it equation 1. So you need to calculate the value of r naught. We only know the one formula for r naught. What is that formula? If you remember the device physics lecture, what is that formula? 1 upon lambda id. Right? And what is that id? Id set but ideal. So you need to have the id saturation, id set. Since this is working in saturation region only, since okay, is it given it is working in saturation region? You have to consider this is working in saturation region because you are calculating the gain. So you have to consider it is working in saturation region. They should be given in the question. Even if it is not given, you have to consider it. So you just need to determine the value of id. That's it. Your R naught is 1 upon lambda id set ideal case, in case of ideal current. So what is that current? id set that you need to determine. That's it. So from where can you determine that id set current? Tell me. By the value of gm. So what was the value of gm you calculated? 0.16 millisiemens. From here you can calculate 2 into root mu n CX W by L. Mu n CX W by L is 100 micro into id. Since we are taking the same value in all the questions, so id value will come out to be 128 micro here, right? How did I calculate so fast? Because we have seen this calculation before in the previous question here, as I guess in the first question only. Here we have seen the same calculation. So IDC value will be 128 microampere. So this is the ID value, IDC value or ID value. So from here, what will be your R naught? R naught will be 1 upon lambda. Lambda is 0.0625 into 128 micro. 0.0625. So 0.0625 into 128. That is 8. So basically your R naught is 10 to the power 6 by 8. If I need to write it in kilo, so what I need to do? 1000 by 8, right? 1000 by 8. 125 kilo ohm. This would be 125 kilo ohm. My R naught would be 125 kilo ohm. Right? So this is what I needed to calculate. Now I can write my gain. So what will be my actual gain? That is minus GM, that is minus 0.6 milli, right? Minus 0.6 milli. I will write 10 to the power minus 3 into 125 parallel with 25. 125 parallel with 125. These are in kilo, so I will write 10 to the power 3. 125 parallel with 25. So 125 into 25 divided by 150. That is 20.833 into 0.6 into 0.16. That is 3.33. So minus 3.33 is your actual gain. So this is your final answer. So previously your gain was 4, minus 4. Here your gain was minus 4. Then you realize that your lambda is not 0. Your lambda is 0.0625. Then you calculated the gain. So first, what was your gain? Minus GM into RL. So the gain came out to be, and so gain was given, that was minus 4. From there you could calculate the value of GM, that is 0.16. Now what did you see? That there is R naught involved, so your gain would be this. But you don't know the value of R naught, so you calculated the value of R naught. R naught would be 1 by lambda ID set, ideal case, in case of ideal. So GM is this 0.16 millisiemens. So from here you could calculate the value of ID. Now people can have doubt, sir, if lambda is equals to 0, then there is, if lambda is equals to 0, then this is the GM. This GM is for lambda equals to 0. If lambda is 0.0625, then the GM can change. This doubt many people can have. Yeah, this will change. Why it will change? Certainly it will change. Let's check that out. What I mean to say is that, sir, when lambda was 0, then you said your GM is 0.16 millisiemens. But if your lambda is 0.0625, then what will be your GM? It can change, no? It can change, but while doing the AC analysis in the complete MOS amplifier, we will not change it. Whether it is lambda equals to 0 or lambda equals to any value, we take the GM to be the same. What is the scene? What is our ID? ID is mu n Cux W by 2L VGS minus VT whole square. This is the case when lambda is equals to 0. If lambda is not equals to 0, this is the scene. So what will be the GM? GM is del ID upon del VGS. Del ID upon del VGS. So mu n Cux W by L VGS minus VT square. So this GM is corresponding to this lambda equals to 0. And if I do 1 plus lambda VDS as well, because we are differentiating with respect to VGS, so 1 plus lambda VDS will be acting as a constant. So this complete expression is with respect to this. Now you will say that, sir, lambda is very small and VDS is also small. Why VDS is small? No, VDS is not small. We are actually working in saturation region, so VDS is not small. So this complete factor is actually very, very small. So we don't consider it. Are you getting this point? This complete factor is very, very small. So usually we ignore this factor and say that GM is the same for lambda equals to 0 or some value of lambda. Let's assume if lambda was some 4, which will not happen. If that happens, then you need to take this in action. If lambda was 4, then you need to take in action, because this value will be something good now. But if lambda is that much small, then what we usually consider that for lambda equals to 0 or lambda not equals to 0, every time the GM will be same. Although the GM is not same, the formula of GM for lambda equals to 0 is this, and the formula of GM for lambda not equals to 0 is this. Yeah, the formula is different, the value of GM would be different, but very minute. So we take the same GM value. So people can have this doubt, so I already cleared it. Are you getting this point? So 99.99% chances is there that your GM will not change. 99.99% I am saying. In some case, if lambda value is given very large, given very large, then you can consider something. In that case, what will happen? They will give you the value of VDS as well. What is this VDS? Large signal VDS. This is not small signal. All these are large signal. Everything, these are large signal. Everything is large signal. This ID is large signal. Everything is large signal. This R0 is a DC parameter. From DC you are calculating this. 1 upon lambda. Lambda value is constant. ID set. This is large signal. This is DC. So everything is large signal here. This is also large signal. Everything is large signal. So they will give you the large signal VDS value, or you need to calculate somehow. How will you calculate? By using the circuitry. But here they have drawn the small signal model. So you can't calculate VDS value anyhow. Can you calculate VDS value here? By using this circuit, can you calculate the VDS value? Large signal VDS value? No, because you don't even know what is the supply VDD here. Because they have already drawn the DC model only. Sorry, AC model only. They have drawn the AC model only. But for calculating the VDS value, you need the DC model. So you don't have that. So you can't calculate the VDS value. So there is 0.01% chance that the GM value can change. And if that changes, you have the aptitude to get the GM value from there. Well and good. So if anyone was having this doubt, I cleared it. So I can write a note here. Usually we consider same GM value for both of the cases lambda equals to 0 and lambda not equals to 0. So what is the GM value for lambda equals to 0? That is mu n COX W by L VGS minus VT whole square. And what is the value of GM for the case lambda not equals to 0? That is mu n COX W by L VGS minus VT whole square into 1 plus lambda VTS. So here I can write, since lambda is very small, we can take GM of lambda equals to 0 to equals to GM of not lambda equals to 0. Okay, so generally this is the case. Well and good. Let's move on to the next program. So this is the next program, which is very interesting. So I need to see how much of you get the correct answer. So two circuits are given. For both of them, you need to determine the small signal voltage gain, and all the transistors are identical. This is M. This transistor is also M. This transistor is also M. This transistor is also M. So all the transistors are identical. You need to determine the small signal voltage gain. So try doing it on your own. Values are given mu n COX W by L, VT and all those things. So try doing it on your own. First tell me the gain of circuit A. What is your answer? The gain for circuit A, small signal voltage gain. We have already seen this diode connected load, right? Okay, there is some issue. Just a second. Okay. I'm really sorry. This should be like this. I hope you did not waste your time. I'm really sorry for this. There are some people who might have wasted their time here. So both are NMOS. So we have seen the diode connected load, right? We have seen the diode connected load like this. So what should be the gain of first circuit? Now calculate the gain. What is the gain of first circuit? I have modified the circuit. The previous circuit was wrong. I have modified the circuit. What should be the gain of first stage? Lambda is equals to 0, so there is no R naught. So what is the gain? -1, right? What is the gain of this? -1? No. Why? Here the gain was -1 because the GM value for both of them was same. Why the GM value was same? Because both the transistor was having the same current. Upper one and lower one, both were having the same current. Here both are not having the same current. Here this 150 microampere current source is also there. So if M is having I current, then the upper one will be having I minus 150 microampere current. Did you understand this point? So in the first one, both transistor are having, both upper and lower transistor are having the same current, and both are identical. Mu and Cx W by L value is also same. So the value of Gm will be same for both of them, but the value of Gm will not be the same for in the case of B. So let's talk about the circuit A. So I will copy this circuit. So this was the best thing about this. If someone blindly does the small signal analysis, what people would have done, they would have blindly done the small signal analysis. They would have just open circuited it, and then they would have seen, okay, 1 by Gm from here and 1 by Gm from here. So both Gm are same, so your answer is -1. But that is wrong, right? Here both Gm are same because this is the current ID and this is also having the current ID. So let's call is upper and this call is lower. So both Mu upper and ML will have same GM value. Why so? Because we know one formula of GM, that is root 2 mu n Cux W by L ID. Can you apply that formula 2ID upon VGS minus VT here? No, you cannot apply because you don't know the value of VGS here. You know the value of VGS here. What is the value of VGS? Here the value of VGS is 3. But do you know the value of VGS here? No, you only know this is 9. You don't know the value of this. Right? Are you getting this point? You don't know the value of this. So you only know the VGS here, that is 3. Yeah. So you cannot apply that formula. Also, you cannot apply the first formula, that is that is mu n Cx W by L VGS minus VT. Again, you don't know the value of VGS. But here you know everything. Here what do you know? 2 is constant. Mu n Cx W by L is same for both. Here I have written mu n Cx W by L is same for both. Here also, one thing also you know, that ID is same for both. ID, DC current is same for both. DC current is same for both. So GM will be same for both. So what will be the, what do you say? What will be the small signal gain? So you can draw the small signal model. You can draw the small signal model. So how will the small signal model look like? This we have already seen in the previous lecture although. So both will be shorted. Both here will be shorted. This is V naught. We will only consider the small signal input now. Right? Yeah. So what will be the current here? GM V in. And what will be the current in the upper side? That would be GM V naught. So here you can say that GM V in is equals to minus GM V naught. So your V naught by V in would be -1. Let's take the second circuit. This one. So let's call this one as upper, this one as lower. So here, whatever the current is flowing here, I, this current is not the same. Let's call this current as I upper and this current as I lower. So I upper would be what? 150 micro minus I lower. Here the DC current is not same. is not same in both transistors. So GM will be different. So how you can calculate the GM of both of them? You need to find the relation, right? You need to find the relation between both of the GM. So let's first find the value of IL. IL. What is the value of IL? That would be mu n CX W by 2L. I can directly write down the value. Mu n CX W by L is 100 micro. So mu n CX W by 100 micro. Mu n CX W by 2L. VGS. You know the value of VGS here. That is 3. Minus VT. VT is 1 square. Right? VT is 1. What did I do here? I am calculating the value of IL so that I could get to know the value of IU. I am calculating the value of IL so that I could get to know the value of IU. So I am calculating the value of IL, that would be 100 micro by 2 VGS minus VT whole square. So this is 4, so it would be 200 micro. So IL value is 200 micro. What will be the IU value now? So IL is 200 micro, so IU would be 50 micro, right? So if I am saying that GM corresponding to this is GMU and GM corresponding to this is GM corresponding to this is GML, GM lower, and GM corresponding to this is GMU. So what will be the relation between GML and GMU? What will be the relation? How you can determine it? You have two ways. First is that you can determine the value of GML as well, GMU as well, because you have the value of mu and CX WIL as well. You have the value of ID as well. So you can determine the value of GM. But better we determine the ratio, because in the answer we will be needing the ratio only. Because what is the small signal gain? What is the small signal gain here? What is the small signal gain? What is the small signal gain? That would be, the upper current would be GM U V naught, lower current would be GM L V naught, right? GM L V naught. So GML V in, sorry, GML V in. Lower current is GML V in, upper current is GMU V naught. So GMU V naught is equals to minus GML V in. So the gain would be GMU divided by GML. This would be the gain. Did I do the calculation right? V naught by GML divided by GMU actually. GMU V naught is equals to minus GML V in. So V naught by V in would be minus GML divided by GMU. This would be your V naught by V in. So minus GML divided by GMU. Minus GML divided by GMU. So you need to find the ratio, right? This calculation you can do. So eventually we need the ratio only. So what I see here is that, what is my GML? That is root 2 mu n COX W by L ID. This is a GM value. Neither GML, neither GMU. This is a GM value. For both of the transistor, MU and ML, for both of the transistor, mu and CX W by L value is the same. The only difference is ID. So from here you can get to know that GM is proportional to root ID. Say yes or no. GM is proportional to root ID. Did you understand this point? For both of the transistor, mu and CX W by L value is the same. The only difference is root ID. So GMU, what do I need to calculate? GML by GMU. So GML by GMU would be equals to root IDL divided by root IDU. So the current in lower one divided by the current in upper one, but the under root. So current in the upper one is 100 micro, 200 micro. And current in the lower one is 50 micro. So why is that negative sign is there? No negative sign. So GML divided by GMU is, what is that value? Root of 200 by 54. So root of 4 is 2. So GML divided by GMU is equals to 2. So what should be the gain now? That would be gain would be minus 2. That's it. Did you get this answer? Let's call this as equation 1, this as equation 2. So what was different here? Here both of the transistors was not having the same current. If both of the transistors were having the same current, then the GM value would have been the same, right? Root 2 mu n CW root ID. Now both of them are having the different current. Then what was the task? You need to determine the current in both of them. One was having 200 microampere, other one was having 50 microampere. By this formula, we got to know that GM is proportional to root ID. Now, no one will say that, sir, this was the formula, no, 2ID upon VGS minus VT. Then you can say that, sir, GM is proportional to ID. If you say that, you are actually very unattentive. You are not listening to the lecture. Why it is wrong? Because you don't know the value of VGS. VGS is not constant. For this VGS is 3. For this VGS can be different. For the upper one, VGS value can be different. You only know the value of gate potential. You don't know the value of source potential. Here the VGS value is 3. Who knows the value of VGS is 6 here. So VGS value can be different here. So you can't say GM is proportional to ID. You only know one thing, that both of the transistors are having the same mu and CXWIL value. So if both of the transistors are having the same mu and CXWIL value, that means GM is proportional to root ID. That's for sure. That is done. GM is proportional to root ID. Then what was your gain? You could write the gain, because we have already seen this problem in the previous lecture only. So you could write the gain. Gain would be minus GML divided by GMU, right? So your target is to find the ratio between GML and GMU. Then you got to know GML by GMU would be root IDL by root IDU. So IDL value you have, IDU value you have. Both of the values you are having. 200 micro divided by 50 micro and then under root. So that would be 2. So your gain would be minus 2. Did you understand this problem? This was very good problem, and this kind of question can certainly be asked in the written test as well and in the future upcoming gate examination as well. Understood? Well and good. So yeah, always while determining the gain, always while writing the gain, you need to consider the GM values. They can be different as well. So blindly don't go for the AC analysis. If you had gone for the AC analysis, what you would have done? You would have simply open circuited it, then you would have short circuited this, then you could see 1 by GM, 1 by GM, gain 1. That is wrong. You also need to consider that GM values. They can be different, right? Okay, well and good. Let's move on to the next question. This is the last one. Yeah, this is the last question of our this set of assignment. After that, we will be studying common gate and common drain amplifier. After that, we will be solving more assignment, 2 or 3 more assignments, because there will be a lot of problems. I picked only a few problems now. I have a lot of more problems. So that we will see in further assignments. So let's solve this problem. You need to determine the bias current in the transistor. Current in the transistor. So this current you need to determine. Let's call this current as ID. So what is that current? 100 microampere. No, that is not 100 microampere. It is sure that this current is 0 ampere. It is certainly sure. This is sure. But it can drive some current here as well, no? Right? So that 100 microampere current which is coming, that will be divided into this current that is going from 40 kilo ohm and this current ID. Are you getting this point? So that 100 microampere current which is coming, that will be divided into two parts, 40 kilo ohm and then ID. Well and good, understood? So let's call this potential as V. Then what will be this potential? This potential will be V by 2. What is the region of operation here? It is not given that it is working in saturation region. We can determine what is the value of VDS. So first we are calculating the bias current. So for calculating the bias current, you need to determine the region of operation. So first, what is the value of VDS? VDS is V. What is the value of VGS? That is V by 2. What will be V overdrive? V overdrive will be V by 2 minus 1. So here you can see that your VDS is greater than V overdrive. That means it is working in saturation region, right? It is working in saturation region. So tell me, what is the current flowing here in this 40 kilo ohm resistance? In both 40 kilo ohm resistance, what is the amount of current flowing? What is the amount of DC current flowing? What is the amount of bias current flowing? V by 80 kilo ohm. Are you agreeing to this point? This potential is V. 40 kilo ohm and 40 kilo ohm both are in series because this MOS is driving 0 ampere current. So 40 and 40 both are in series. So V by 80 kilo ohm current is flowing. Are you getting this point? This is the potential V. Then there is 40 kilo ohm resistance. Then there is one more 40 kilo ohm resistance. And then this is having 0 ampere current. This is R, this is R. So what is the current here? V by 2R. That's the same. V by 80K. V by 80K current is flowing. What is the value of ID now? What is the value of ID? So basically, the scene is 100 microampere is equals to V by 80K plus ID. So here there are two variables, V and ID. There are two variables which is not desirable. You need to eradicate one variable. So I can eradicate one variable. How? This is how I can eradicate one variable. So ID is equals to mu n CXW by 12, 100 micro by 2. VGS, what is the value of VGS? VGS is V by 2. VGS is V by 2 minus VT whole square. That's it. So this is how I can eradicate one variable. So this value I can put here. Now will it be a very tough calculation? Or is there any other way to determine the values? Because I think this will be a very tough calculation. Let's check it out. If it is tough, then we will find out some way. So yeah, let's check it out. So 100 micro is equals to V by 80K is there. So V by 80K is there, no? V by 80K. So 80K is there. So what I can do, I can write 0. What is 80K? 80K is 8 into 10 to the power 4. What if I write 0.08 into 10 to the power 6? Is that correct? Yeah, it is correct. So I am writing 0.08 into 10 to the power 6. That means micro. Did you understand it? What did I do here? V by 0.08 into 10 to the power 6. 10 to the power 6 went up, it would become 10 to the power minus 6. That would become micro. Right? Why I am doing so? So that I can cancel micro, micro and micro. Now what will come? My ID will come. So ID is 100 micro by 2. That means 50 micro into V by 2 minus 1 whole square. Micro and micro will get cancelled. So 100 is equals to, this will be 100 by 8. What is 100 by 8? 12.5. 12.5 V plus micro and micro are cancelled. This is 50. This bracket I can solve. A square plus V square minus 2AB. So it will be minus V only. This calculation is not tough. Okay, in the examination, these kind of calculation are asked. So you should be ready with that. Don't think that these kind of tough calculation will not be asked. 12.5 V square plus 50 minus 50V, right? So what I can do, 12.5 V square is there. This would be this and this would be minus 37.5V, minus 37.5V, and this would make minus 50 is equals to 0. Well and good. Now I can divide 12.5. V square minus 3V minus 4. Very easy it became, right? It became very easy here. This is the final equation, V square minus 4V plus V minus 4. V value we are getting V minus 4, 1. So from here you are getting two values of V. V values are 2, minus 1 and 4. What will be the correct answer? You already know. This will be the correct one because V cannot be negative. If V is negative, the transistor will be off. So V cannot be negative. V is 4. So your final answer is V is 4 volt. So if V is 4 volt, that means your VDS would be, VDS is 4 volt and VGS is 2 volt. VGS is 2 volt. So what did you need to determine? You need to determine the bias current in the transistor. So ID value would be mu n Cx W by 2L into VGS minus VT whole square, right? 100 micro by 2. What is VGS? VGS value is 2. 2 minus 1 whole square. So ID value came out to be 50 micro ampere. This is the ID value we are getting. That's it. Well and good. Now what is the next question? You need to determine the small signal resistance Rx. So try doing it on your own. Then I will tell you how to determine it. So let's take this circuit and paste it here. Okay. I have to copy again. So this will be your small signal circuit, right? How it is the small signal circuit? This current source is gone. This will be open circuited. VDD is also gone. This is open circuited, and then this much circuit is remaining. So this is your small signal circuit, right? Small signal model. This is your small signal model. You need to determine Rx from here. So what we are doing? Small signal analysis. So you need to determine Rx from here. That would be Vx Ix. So you need to determine Rx equals to Vx by Ix. So tell me, you can apply the nodal analysis. What is the current here? That would be Vx by 80 kilo ohm. What will be the current here? This is Vx, this potential will be Vx by 2. So the current here would be Gm Vx by 2. Right? This potential is Vx, so this potential will be Vx by 2. So VGS is Vx by 2. So the current downward would be Gm Vx by 2. Vx by 80k, Gm Vx by 2 is equals to Ix. So this you need to calculate. Here what you can see, that is Vx by 80k plus Gm Vx by 2 is equals to Ix. So what will be your R out? What do you think? I am directly writing Rx. I hope you will be able to understand. My Rx would be 80k parallel with 2 by Gm. Are you guys able to understand it? How did I write it? 80k parallel with 2 by Gm. Vx by 80k plus Vx by 2 by Gm is equals to Ix. I told you V by R1 plus V by R2 is equals to I. So what will be the resistance? R1 parallel with R2. Right? The resistance is R1 parallel with R2. So same thing is happening. 80k parallel with 2 by Gm. Now again you don't have the value of Gm. So you again need to calculate the value of Gm. So how will you calculate the value of Gm? You need to calculate Gm. Gm means good morning. Very bad joke. इस जोक के हिसाब से मैं कपिल शर्मा शो में तो जा ही सकता हूँ. Okay. So what is the value of Gm? That is 2 mu n Cx W by L ID. So you know the bias current in the transistor, that is 50 microampere. So root 2, you know the value of mu n Cx W by L, that is 100 microampere. 100 micro into 50 micro. Your answer would be 100 into 100. So that would be 100 and micro will come out. So 100 micro. 100 micro. What is 100 micro? Gm is 100 microsiemen. You can calculate this, you will get 100 microsiemen. Gm is 100 microsiemen. So what will be your Rx now? Rx will be 80k parallel with 2 by 100 micro. 2 by 100 micro. 2 by 100 micro. Right? Well and good. 2 by 100 micro. 100 micro means 10 to the power minus 4. 10 to the power minus 4. So it would go up, so it would become 80k parallel with 20k. That is your Rx. So 80 into 20, 16k. So what is the parallel combination of this? 16 kilo. Rx value you got is 16 kilo. Did you understand this? Small signal resistance we calculated. How did we calculate it? We just need to determine the value of Vx by Ix. So we have to anyhow get the value of Vx by Ix. That is our target. So we can apply nodal analysis. The current here was Vx by 80k. The current downward was Gm Vx by 2. So Vx by 80k plus Gm Vx by 2 is equals to Ix. So Vx by Ix, what will be the Rx? That would be 80k parallel with 2 by Gm. So you need to calculate the value of Gm. Gm you can get from the ID value root 2 mu x root mu n Cx double by L into ID. So mu n Cx double by L value you are having, that is 100 micro, and ID value you got, that was 50 microampere. So from there Gm value you got is 100 microsiemens, right? 100 microsiemens, that means here Rx value would be 80k parallel with 2 by 100 micro. 100 micro means 10 to the power minus 4. That means 20 kilo. So 80 parallel with 20 kilo, that would make 16 kilo. So Rx is 16 kilo. That's it. That's the final answer. So this was our assignment 6, which was the first assignment of common source amplifier. There will be more assignments, but before that we will study common drain and common gate amplifier. After that we can see another assignment. So I hope you are comfortable with the problem solving now. So yeah, these kind of calculation, these kind of questions can certainly come into your examination in near future. Well and good. So let's meet in the next lecture. Thank you. Hi everyone. So today we are going to study about common gate amplifier. Then we will study about common drain amplifier. Okay. Yeah. So let's start. What is our common gate amplifier? This is the configuration given. Although here I have used two battery, VDD and VGG, but it will not be the case in the actual biasing. In actual biasing, we will be using only one battery. How we will be making VGG? VGG we will be making from VDD only. And how we will make that? By using the potential divider. Everything we have studied till now. But for the configuration, I have made it like this. Okay. So now what is the specificity of a common gate amplifier? That is your input, small signal input will be applied at source terminal. Small signal input will be at source terminal and output you will be collecting at drain. Small signal output you will be collecting at drain, right? And this gate is common because that is connected to DC supply only. So let's do the small signal analysis. Let's draw the small signal model. So what will be our small signal model? So this VDD is shorted, VGG will also be shorted. This is our RD and this is our small signal V in, right? And this will be our small signal V out, small signal output. Well and good, everything is fine. And between source and drain, between drain and source, you will be having a R naught. So between drain and source, you will be having a R naught. That's it. Well and good. Yeah. Let's find the gain and everything. What we will find? Input impedance, output impedance, gain, voltage gain, current gain, everything we will find. So let's start with the voltage gain. We are finding the voltage gain for the condition that lambda is not equals to 0. That means R naught is finite. R naught is finite. So first we are finding the gain for this condition that R naught is finite. So let's find it out. This is R naught. This was RD, right? RD. Okay. And this is the V in. And this is V naught. Your target is to find V naught by V in. You can apply nodal at V naught. How will you apply? The current here is V naught by RD. The current here is V naught minus V in by R naught, right? V naught minus V in by R naught. Do you know the current here in this MOS? Yeah, I know. What will be the current? The current will be Gm V in the upward direction, because here you are having V in, here you are having 0. So from V in to 0 you are going in this direction. So the current in the upward direction would be Gm V in. So the current would be Gm V in. So basically your Gm V in current is equals to your Gm V in current is equals to the addition of these two current. Or you can simply apply nodal analysis. Outward current V naught by RD, outward current V naught minus V in by R naught, and inward current GM V in. So GM V in would be equals to V naught by RD plus V naught minus V in by R naught. This is V in GM plus 1 by R naught, and this is V naught 1 by RD plus 1 by R naught. Well and good. So here we will be having GM R naught plus 1 divided by R naught. This is V naught. This is R naught plus RD upon RD R naught. So R naught will get cancelled. So what you are having? What will be your V naught by V? This is simple network analysis, nothing else. What will be your V naught by V? That would be RD into this R naught and R naught are cancelled. RD into GM R naught plus 1 upon R naught plus RD. So this is the final expression you are getting. You don't need to mug it up. You should have the aptitude to find it out, right? If they give this configuration and they ask you what is the gain, then you can find out by these simple equation, right? So this formula is not that much important. Why is it so? Let's check that out. Now we are going to find the voltage gain for the condition lambda equals to 0. For the condition lambda equals to 0, this is the formula for lambda not equals to 0. If lambda equals to 0, that means R naught will be infinity. That means R naught is very large. So what will happen here? The GM R naught plus 1 will be reduced to GM R naught only, because GM R naught will be a very large value than 1. Then into RD divided by R naught plus RD will be reduced to R naught only. So what will be the gain? Gain will be GM RD only. What was the gain you find in common source amplifier? What was the gain in the common source amplifier? That was minus GMRD. Your V0 by V in was minus GMRD. Here what is your V0 by V in? That is GMRD. The gain is same. In both of the cases, the magnitude of the gain is same. In common source amplifier, you get the phase shift of 180 degree. Between output and input, there will be a phase shift of 180 degree. Why 180 degree phase shift? Because there is a negative sign. So there is a phase shift of 180 degree, and here between output and input, there is no phase shift. So in common drain amplifier, sorry, not common drain, in common source amplifier and in common gate amplifier, the gain is the same. That is equals to GMRD only. But in common source amplifier, you get a phase shift of 180 degree, and while in common gate amplifier, the phase shift is 0 degree. Well and good, understood. So let's find out the gain for the condition of lambda equals to 0. Although this expression is not that much of famous. Why it is not that famous? Because it doesn't signify anything, right? It doesn't signify anything. This is simply an expression, so you don't need to mug it up. You can derive it in the examination if they ask you, right? Let's go to this condition. This formula is famous, what we are going to derive now. Although we have derived here only, but let's check the derivation here once again. Now R naught is infinity because lambda is 0, so R naught is infinity. So what is the current flowing here in the upward direction? That is GMV in, and the same current is flowing through RD. The same current is flowing through RD. So what will be V naught? The drop here will be in this direction. So V naught would be GMV in, sorry, minus GMV in into RD. So V naught by V in would be minus GM RD. That's it. Did you understand this? Oh, sorry. It will be plus. Sorry, I'm really sorry. It will be plus. Why negative? This is 0. This is 0. Then this will be plus only, no? The current is flowing in upward direction. So V naught by RD is equals to GMV in. Basically, you can say that V naught by RD is equals to GMV in. So V naught by V in is equals to GMRD. So between output and input, and input, there is no phase shift. There is 0 degree phase shift, absolute right. There is 0 degree phase shift. Well and good. Let's move on to the next expression, that is input impedance. You see this expression and I ask you what is the input impedance. Do you remember the formula? What is the input impedance? I have told you to remember one formula. I have told you to remember one formula. What was that formula? Rs plus R naught plus GM Rs R naught. Do you remember it? I told you to remember this formula, right? But is that the same? No. What was the circuit? What was the circuit for this? The circuit was this. And from here you are calculating the R out. So for R out, this was the expression. So don't get confused. There will be two formulas. One looking from downward, looking from source terminal. This is the formula looking for from source terminal. And this is the formula looking from drain terminal. So both formulas are different. You shouldn't be confused. Looking from source terminal, the formula will be different. Looking from drain terminal, the formula will be different. So there we will get two formulas. So you have to remember both of them, but you shouldn't be confused. One is the looking from source terminal, one is the looking from drain terminal. So let's find out what is the impedance do you see looking from the source terminal. So what is the impedance you will see? What you will do? You will apply a Vx voltage and get Ix out of it. Right? Very simple. So you just need to find the relation. So let's make it better. So you apply a Vx and get Ix out of it. You are finding R in here. Now this Ix will go, it will be divided into this and then come out. Ix will go, it will get divided into MOS and R naught and then it will come out, and here you will be having Ix only. Well and good. Understood? So what will be this potential? Tell me. What will be the value of this potential? It will be Ix into Rd. This potential will be Ix into Rd. Why I am writing in terms of Ix? Because I don't want any other variable. I want my expression to be in the terms of Vx and Ix. That's it. This is my target. Are you getting this point? Why I wrote the potential in terms of Ix? Because I don't want any other variable. I only want Vx and Ix. That's it. Okay. So what I can do? I can apply nodal here. Here I can apply nodal analysis at this potential. So from this potential, what are the currents? One current is going outward, that is Ix. Plus, let me write what we are doing first. Nodal at Ix Rd. One current is going outward, that is Ix. What will be the other current? Here, what will be the other current? Other current would be Ix Rd minus Vx divided by R naught. This current I have wrote. This current I have wrote. Ix Rd minus Vx divided by R naught. What will be the next current? This will be the next current. That would be GM Vx. That would be GM Vx. Did you understand it? You are applying the nodal at this node, so you have to write down all the current. There are two current going downward, one current going upward. So actually, what was the direction? Ix was going up, GMVx was also going up, and IXRD minus Vx divided by R naught is going down. So outward current plus outward current equals to inward current. That's it. Very simple KCL KVL, nothing else. So this would be Ix. Here I can take common. If I take Ix common, what do I get? R naught plus Rd divided by R naught. And here Vx will go here. So Gm plus 1 by R naught. So Ix, here I am getting R naught plus Rd, and here Vx is gm r naught plus 1. R naught got cancelled. gm r naught plus 1. So what is your, अरे यार वायर की क्या हो रहा है आज, यहाँ है भाई तू, yeah. So what is your Rx? Rx is Vx by Ix, that would be R naught plus Rd upon 1 plus gm r naught. So this you have to remember. This is very famous expression and this is very important as well. So if you remember this, your large problem will be reduced to very small problems. When we see the problems, when I connect 5 to 10 transistor in one circuit only, then there will be expression like this. If you don't remember, you will have to derive it, and then your problem will become complex. But if you remember these two formulas that I have told you to remember, first is this one, the another one is the output impedance. So if you remember those two formulas, your problem will be very, very easier. So let's check out what we need to remember. So I will just write down to remember. So till now we have two things to remember, REMEMBER. So you have to remember the circuit as well and the expression as well. What is the circuit? Circuit is something like this. For this one, what is the circuit? Circuit is something like this. The gate is common in both of the circuit. Gate is common. This is R naught. This is RD. And from here, looking from source terminal, what is the resistance looking from this source terminal? That would be, what that would be? R naught plus RD. R naught plus RD upon 1 plus GM R naught. That you need to remember. And what was the other thing that you needed to remember? The circuit was something like this. Even the gate is shorted. From here you were looking. Here there was R naught involved. And this was grounded. Yeah. And this was RS. So if you are asked to tell the resistance from here, so what would be the resistance? R naught plus RS plus GM R naught RS. So these two things you have to remember. That's it. Now people get confused. People many times forget which one will be the what formula. Like if I ask them what is the impedance from here, then they will write R naught plus RS upon 1 plus GM R naught. Because they get confused which formula will be applied where. I have seen it happening with a lot of aspirant. Even with me this happens. So how do I remember it? Let's check that out. I will simply tell you a trick. So if I tell you that think of the MOS device in your brain, you have to think of the device. So what is the picture you are getting? This is the picture you are getting. Here there is source and here there is drain. This is the picture you get. If I am telling you to think of the MOS device in your brain, so what was the picture you were getting? Source and drain. Source is behind and drain is ahead. Source is behind and drain is ahead. So if you are going from source to drain, that means you are going ahead. You are at behind and you are going ahead. If you are going from source to drain, that means from here, if you are looking for the impedance from the source side, you are going from source to drain, then your impedance will need two steps. Two steps means numerator and denominator. If you are going ahead in life, you need to put more struggle. Similarly, if you are going ahead from source to drain, you need to put more struggle. That means you need two steps. Two steps means numerator and denominator. So by that you can remember, okay, I need two steps. That means R naught plus RD upon 1 plus GM R naught. And if you are going backward, you don't need that much of struggle. In one step only you can come backward. Because if you are going ahead in life, you need to put more struggle. But if you are getting backward, you don't need to do anything. You can just open Instagram and scroll reels, right? Reels अगर scroll करोगे तो आराम से पीछे आ ही जाओगे, है ना? So you just need to open Instagram and scroll reels. That is not a tough task. So if you are going behind, you just need one step. If you are going ahead, you need two steps. So this is how I remember. If I am going from source to drain, okay, I am going ahead, so I need two steps. So R0 plus RD upon 1 plus GM R0. Two steps means numerator and denominator. If I am going backward, that means I am going from drain to source. That means I need only one step. So in one step, R0 plus RS plus GM R0 RS. So in your mind, you will remember these two formulas, this formula and this formula. But you will eventually forget which formula will be used for what. This happens many times. Okay. So yeah, now we will not forget. So these two formulas you have to remember. Well and good. Let's move on to the next one. Here we will find input impedance again, but for the condition of lambda equals to 0. Lambda equals to 0. Oh, okay, forget it. I can make the new circuit only. So lambda equals to 0. The condition is lambda equals to 0. So you have to find the impedance from here. Tell me what will be the answer. In one step only you need to tell me the answer. I told you one thing. From source to gate, I see how much resistance? 1 by GM. Remember it? I told you to remember it. From source to gate, I see 1 by GM resistance. Or you can derive it as well. If you need Rx here, that means you will apply Vx here and Ix, get Ix out of it. What is the current flowing? What is Ix? The current flowing is GMVx only, right? The current that is flowing is GMVx only in the upward direction, because this potential is Vx, this potential is 0. So current flowing in the upward direction is GMVx. So GMVx is equals to Ix. So Rx, that is equals to Vx by Ix, is equals to 1 by GM. That's it. So the resistance is 1 by GM. That's it. Or I told you to remember as well, from source to gate, I see 1 by GM. From source to gate, I see 1 by GM. From source to gate, I see 1 by GM. This is also very, very important. It is used a lot of times. From source to gate, I see 1 by GM. Well and good. Let's move on to the next thing, that is output impedance. We are writing output impedance considering that input source doesn't have any internal resistance. Input source. What is our input source? Input source is Vin. So our Vin is equivalent to simply this Vs. That's it. Our Rs is 0. This is what we are considering, that our Rs is 0. 0 ohm. So considering this, we are writing the output impedance. So let's make the circuit only. Let's not copy it. So we have to write the output impedance. This was already grounded. This was RD. This was grounded. This was our V0. From here, we need to calculate the output impedance. So here we were having our Vs, right? Here we were having our Vs. So this will be grounded because it is not having any internal resistance. So this will simply be grounded. And here we are having R0 between drain and source. Between drain and source, we are having R0. So tell me what will be the output impedance? Gate is shorted and source is shorted. VGS is gone. Gate is 0, source is 0. VGS is gone. That means here there will be 0 ampere current. So this is open circuited. So from V0 to ground, what do you see? At this node, if you come, you say from V0 to ground I see RD, from V0 to ground I see R0, and there is 0 current here. So from V0 to ground, you only see RD parallel with R0. That's it. Your output impedance is RD parallel R0. Say yes or no. So you don't need to mug up any formula. रट्टा किसी का नहीं मारना है. I am giving you the concept. रट्टा जिसका मारना है, मतलब जो याद रखना है. Whatever that you need to remember, I am writing it down here. This is what you need to remember. And 1 by GM also. From source to gate, I see 1 by GM. That is very simple thing. If you remember these formulas only, then you will be able to solve very complex circuit within second. Otherwise, you will have to derive there. So that's why I have seen I have been studying analog electronics for 4 years now, and I have seen nearly around 300 circuits. So by remembering these formulas only, I am able to answer those circuit very, very quickly. Otherwise, you will see solutions of gate, like you might have seen the solution of previous gate year questions of MOSFET amplifier. I have seen them. I have seen a lot of educators solving those problems by very rigorous analysis, and that analysis is not useful in the examination. So if you just remember these things, no matter how complex they make the circuit, you will be able to answer very, very quickly. Well and good. Let's move on to the next one. So here RD parallel R naught, because VGS is gone, so 0 ampere current, RD parallel R naught. Now we will be writing output impedance considering input source has some internal resistance. So input source has some internal resistance. So what is your input now? Your input is Vs, that is having some internal resistance Rs. This is shorted. This is having internal resistance Rs, and here you are having Vs. Here you are having Vs, but that will be grounded. And this is R naught. So you need to find the impedance from here. R naught. Tell me what will be the answer. I will directly write down the answer and you have to tell that okay, you understood. So R naught will be RD parallel R naught plus RS plus GM R naught RS. That's it. Did you understand it or not? Because we have seen it multiple times, 2 or 3 times. From V naught to ground, this is V naught, and we are getting I naught out of it. And our R naught is V naught by I naught. So from V naught to ground, I see a resistance that is RD. And from V naught to ground, I see one more resistance that is Rx. So my final answer is RD parallel with Rx. And what is Rx? Rx is R naught plus Rs plus 1, R naught plus Rs plus GM R naught Rs. This I am remembering. Why I am remembering? Because it will help me to reduce my calculations. So this I will be remembering every time. As an analog designer, if you go in any company, you will see every analog designer remember these formulas. Everyone. Because it helps us to reduce our calculation. So these two formulas everyone remembers. And once we study Cascode amplifier, you will realize the importance of these formulas. Okay. Well and good. Everything is going good now. Let's move on to our next point, that is current gain. What is current gain? This is the input current, this is the output current. Tell me what is the current gain here? What is the current gain? Here I in is equals to I out. This current that is going in, the same current is going, I in will be divided into these two, and then addition of these two current will come out. So I in is equals to I out. So I out by I in is 1. So common source, not common source, common gate amplifier is known as current buffer, because here current gain is 1. So it is known as current buffer. Whatever the current you gave in the amplifier, the same current you get at the output. So it is known as current buffer. So there is one other name of common gate amplifier. That is current buffer. C buffer I can write. Current buffer. Well and good. Let's move on to the next one, that is common drain amplifier. Now we will be analyzing common drain amplifier. So in common drain, input will be at gate and output will be connecting at source. Gate to source. Well and good. So this is your common drain amplifier. So small signal input is at gate and small signal output you will be collecting at source. Right? So small signal model, what will be small signal model? I am drawing the small signal model. VDD will be shorted. Biasing everything we know, because we will not be using VDD and VGG. We will not be using two batteries. We will be getting VGG from VDD only by potential divider, right? But to make the smaller circuit, we are doing like this, because we have studied the common source amplifier very deeply. Now studying common drain and common gate is cakewalk for us. Within 30 minutes we have completed common gate amplifier. If I had not taught that much in depth for common source amplifier, we would have taken time in common gate, but we have studied very depth of common source, so we are not taking that much time. Now we are studying common drain amplifier. So here only small signal Vin will be there, because these are shorted. VDD is shorted, VGG is also gone, so only small signal Vin is there. This resistance is Rs, this resistance is V0, and here you are having R0 as well. So between source and drain you are having R0. So here you are having R0. There is one more way I can make it. So from V0 to ground you see R0, from V0 to ground you see Rs as well. So I can make Rs parallel with R0, right? Rs parallel with R0 will be there. Why it is there? Because both are connected between V0 and ground. So MOS is there. Sorry. MOS is there. This Vin is there. This is grounded. From V0 to ground you are having Rs, and V0 to ground you are having R0 as well. And this is your V0. Right? Now you can do the small signal analysis. So we will do the small signal analysis now. First we will find what that is most important. We will find voltage gain. So this is the method one that we are talking about for finding the voltage gain. So what will be the voltage gain? Tell me what is the current flowing in the MOS? That is GM V in minus V0, right? GM V in minus V0. Say yes or no. Are you agreeing to this point? Right? Now the same current will be flowing through this resistance. So GM V in minus V0, that is the current, into resistance. What is resistance? Rs parallel R0. Current into resistance will be equals to V0 only, right? Did you get it? Understood? So GM Rs parallel R0 into V in, then minus GM Rs parallel R0 into V in, that would be 1 plus GM Rs parallel R0 into V0. So V0 by V in would be GM Rs parallel R0 upon upon 1 plus GM Rs parallel R0. So that is the voltage gain we are getting. So generally what happens, that GM Rs parallel R0 is nearly equals to 1. Is very greater than 1, because I told you these values are very large. So GM Rs parallel R0 is generally very large. So this value is very larger than 1. So what will happen? What will happen to gain? So if this is very large, then this expression will be reduced to GM Rs parallel R0 only. So the gain will be 1. The voltage gain will be 1. Voltage gain is 1. Now, where was your input? Input was at source. Where you are getting the output? Input was at gate. You are getting the output at source. So common drain amplifier is known as source follower. Common drain amplifier is known as source follower, because here you are getting the gain 1. It seems like that the output is same as the input. So where you calculated the output, the same input is coming out. Are you getting this point? Without any phase shift, there is 0° phase shift. Without any phase shift, the same input is coming at the source. So that's why it is known as source follower. So your input is following the source. Your input is following the source. So your common drain amplifier is oftenly known as common source follower, because your output is simply equals to the input. So basically your input is following the source. Are you getting this point? So common source amplifier is known as source follower. Not common source amplifier, sorry, common drain amplifier. Common drain amplifier is known as source follower. What was the other name of common gate amplifier? What was the other name? Current buffer. The other name was current buffer. And what is the other name of common drain amplifier? That is source follower. Well and good, understood? The name of common gate amplifier. What was the other name of common gate amplifier which we studied previously? That was current buffer. And what is the other name of common drain amplifier? That is source follower, because here output is following the input. Basically your input is following the source. Your same, whatever the input you applied, the same input you are getting at the source. So it is following the source. That's why it is known as source follower. Say yes or no. Understood? So these are the other names. So sometimes in the question they can write down, okay, a source follower amplifier is given. So what will you understand? That common drain amplifier is given, and they say current buffer is given. That means common gate amplifier is given. Well and good. Let's move on to the next thing. We will find the voltage gain, but by one other method. So we have to find the voltage gain now. This was the first method. What would be the one other method? You have to record the video by turning off the fan. And here in Bangalore, आजकल गर्मी बढ़ गई है बैंगलोर में, पता नहीं क्या हो रहा है. Okay, then yeah. So I know one thing, that is I know my T model. Here I am having V in. From here to here I see 1 by GM resistance. Right? This is my V node. This is RS parallel R naught. Well and good. Let's call this resistance as R. We will write it down later on. For now I am calling it R. From upward direction some current would be coming. I know that current would be GM V in minus V naught. GM V in minus V naught. But that current doesn't matter to me, because here the same current is flowing. In complete one, the same current is flowing from 1 by GM as well, and from RS parallel R naught as well. So 1 by GM and R both are having the same current. So I can simply apply potential divider. So what will be my V naught? My V naught will be R upon R plus 1 by GM. Handwriting बड़ी खराब आ रही है भाई. V naught would be R upon R plus 1 by GM into V in. That's it. Potential divider it is. V naught would be R upon R plus 1 by GM into V in. So V naught by V in would be GMR upon 1 plus GMR. That is the gain. What is R here? R is RS parallel R naught. The same gain you are getting. This is just the second method. What is that method? From V in you see here 1 by GM and RS parallel R naught. So simply you can apply that. What you can apply? Simply you can apply potential divider. So this is acting as a potential divider. So by the concept of potential division, you can apply, you can get the formula R upon R plus 1 by GM. So GM R upon 1 plus GM R. Well and good. What do we need to find now? Okay, so we will find out input resistance, output resistance, and current gain. So let's find out current gain. Tell me what will be the current gain? Output current divided by input current. Whatever output current you get, what is the input current? Here is the input applied. Input current is 0 ampere, right? Input current is 0 ampere. The current gain would be infinity only. And what will be the input impedance now? Tell me, what will be the input impedance? That would also be infinity. R in would be V in by I in. Whatever V in would be there, but I know that my I in is 0. So current gain would also be infinity. Now tell me what will be my output impedance. चल रहा है ना भाई वीडियो. Output impedance. Let's calculate the output impedance. So this was your V in, which will be shorted. Okay, let's write it down V in only for now. This is common drain amplifier, so here drain is shorted, and here you are collecting the output. This resistance we are calling is RS, right? We are calling this as RS. And from V0 to this side as well, you see R0. Between source and drain, you see R0. So in conclusion, you make it like this. Now you need to tell the output impedance. So what you will do for getting the output impedance, this will be shorted. Now tell me one thing. What I can say? From V0 to ground, I see RS parallel with R0. And from V0 to ground, I see 1 by GM. Say yes or no. From source to gate, I see 1 by GM. From source to gate, I see 1 by GM, right? So you can say that from V0 to ground, I see RS parallel with R0, and from V0 to ground, I see 1 by GM as well. So simply, my output resistance, where I was calculating my output resistance, this is my V0. So here I was calculating my output resistance. So simply, what is my output resistance? From V0 to ground, I see RS parallel with R0, and from V0 to ground, I see 1 by GM as well. This is my output resistance. That's it. Well and good. Also, you can find out how you will find out. From V0, you will get I0 out of it. So if this is V0, that means in upward direction, the current is GM V0. And in downward direction, the current is V0 by RS parallel R0. So you can apply the nodal. What will be the nodal? Outward current GM V0 plus one more outward current, that is V0 RS V0 by RS parallel R0, that is equals to I0. So what will be your V0 by I0? That would be 1 by GM parallel with RS parallel with R0. From here as well you can find it out, right? Just the equation I wrote, nothing else. Or directly you can see from V0 to ground I see RS parallel with R0, and here from V0 to from source to gate, I see 1 by GM, and gate is grounded, so I can see from V0 to ground I see 1 by GM. So 1 by GM parallel with RS parallel with R0. Well and good. Say yes or no. Understood? Comfortable? Okay. So here next I have put some question, but let's just write a summary. We have seen three kind of amplifiers, so we will write down a summary and we will note down a point. So let's write down a summary. First one being the common source. Common source amplifier. Here we will consider R0 to be infinity. Okay, for now we are just writing down the summary, so we are considering R0 to be infinity. What is the voltage gain? GMV in current is flowing, that is flowing through RD, so voltage gain would be minus GM RD. What you can write down? That there is 180-degree phase shift between input and output. This is one important point, that there is 180-degree phase shift between input and output. Well and good. Input impedance is infinity, current gain is also infinity. What is the output impedance? R naught. What is the output impedance? Output impedance is simply RD parallel with R naught. This is also a very important point, that there is 180-degree phase shift. So what do you understand here is that if you give a, if your input rises like this from 0 to some value, then what will happen to your output? Your output will rise but in negative direction. Let's assume this is 0. So your input is rising from 0 to Vm, then your output will rise but in negative direction. So in theoretically we can say that your output is decreasing. If your input is increasing, then your output is decreasing. Did you understand? So if it rises from 0 to Vm, then your output will go to minus Gm Rd Vm. 0 to Vm, output is minus Gm Rd Vm. Well and good. Let's write down about the second one here only, that is common gate amplifier. Common gate amplifier. So here gate is common and output you are collecting at drain. Here you are having the input, output you are collecting at drain. RD. So what will be happening here? Here in upward direction GM current will be flowing. Here the current flowing was GM but in the downward direction. Here in the upward direction GM current would be flowing, and that current will be flowing through RD. So your gain would be AV. Your gain would be GM R naught. GM RD, sorry. GM RD. Your gain is here GM RD. And what is the important point here? That is between input and output, there is 0-degree phase shift. Phase shift. So there is no phase shift between input and output. 0-degree phase shift. So if your input is increasing like this from 0 to Vm, then your output will also increase. From 0 to Vm it is increasing, and then your output would increase from to GMRD Vm. Did you understand it? If it is increasing from 0 to Vm, your output would increase GMRD Vm. So in common source amplifier there is a phase shift of 180 degree, while in common gate amplifier there is no phase shift. And this concept will be used a lot of times when we study the feedback amplifier. So I will be using common source amplifier and I will directly say the signal is inverted. So we should have good aptitude to understand why signal is inverted, because there is 180-degree phase shift. So this is common source amplifier. What is R naught here? Multiple formulas we have studied, but following this expression, what will be R naught? In this circuit, what will be R naught? RD parallel R naught, right? RD parallel R naught. Why so? Why is it so? Because Vin will be shorted, so VGS is gone, so RD parallel R naught it will see. What is the current gain? Current gain is 1, because whatever the current that is flowing in the input, the same current is flowing in the output. So current gain is 1, and that's why it is known as current buffer or C buffer. Well and good. Let's move on to the next one, that is common drain amplifier. So in common drain amplifier, what do you do? In common drain amplifier, drain is shorted, you apply your input at here, you apply your input and your drain is shorted and you collect your output at source. So what is the gain you get? How you can write down the gain? Gain you can simply write down by potential divider. So the gain you get is GMRD upon 1 plus GMRD. That is nearly equals to 1. This is the gain you get, which is nearly equals to 1, and you can call it as source follower, because your input is following the source. This is source follower. And what do you see? There is 0-degree phase shift between input and output. There is 0-degree phase shift between input and output. This is also you can see. And what else? What is the input impedance? Input impedance is infinity. What is the output impedance? Output impedance by this circuit. What is the output impedance? That is RD parallel R0 parallel 1 by GM. We are not mugging up anything. We are not mugging up anything. From V0 to ground I see RD. From V0 to ground I see R0. From V0 to ground 1 by GM I see. That's it. My output impedance is this. This is my output impedance. Well and good. Is there anything else? Yeah, that is if this rises from 0 to Vm. So V0 will also nearly rise to till Vm only. There is very less current voltage gain. So it will also nearly rise to Vm only. Well and good. Nearly Vm. Actually, V0 will be lesser than Vin only. The gain cannot be higher than 1. Gain will always be less than 1. So it will be nearly Vm only. So this is the conclusion of whatever that we have studied till now. Let's solve the assignments that is given. Not the assignment, sorry. 3 questions are there. All of them looks similar, but there is something different. That is the value of RDS. So that is different. In this question, what is the first question? You need to find the small signal voltage gain V0 by Vin. What is this VB? It should be given that VB is the DC bias. VB is the DC bias. So you need to find the small signal voltage gain. So try doing it on your own. You can do it on your own. So try doing it. So what we are going to do, we are going to copy this circuit. We have to find the gain. Since this is the DC bias, that means it will be shorted, because we are doing the small signal analysis. So this will be shorted. What will be happening to VDD? This will also be shorted. VDD will also be shorted. Tell me what will happen to M2? VGS is gone. VGS is gone, so there will be no current. So M2 is simply open circuited, but there is R0 connected. Between drain and source, there is R0 connected. So M2 is simply replaced by R02. They are given RDS2. This is RDS1. So this is R01 only, and this is R02 only. So sometimes they write it RDS, drain to source resistance. Okay, you don't need to be confused. Sometimes they write RDS, that means drain to source resistance. That's it. So this is R01 only, this is R02 only. So VGS is gone, so this will be gone, so this will drive 0 ampere current. So there is no use of M2. M2 is open circuited, but there is R02 connected. So this will be R0. So how your circuit is reduced now? The circuit is reduced to something like this. RD plus R02, because RD, there is no current here, so this is simply open circuited. So RD and R02 comes in series. RD and R02 comes in series because there will be same current here. So both of them comes in series. Did you understand? There will be same current. If there is I current here, the same I current will be flowing here. So they come in series. So RD plus R02. And this is V in. This is V0, and this is grounded. What will be the gain now? What kind of amplifier it has become? It has become as what? Common drain amplifier. And what is the gain? We are not mugging up the gain. We can write it right down by the concept of potential divider. So what will be your V0 by V in? You simply need to divide the potential. Yeah, one more thing. From V0 to ground, here you see R0 2 as well, right? R0 1, not R0 2. This is R0 1 because this is M1 transistor, so this will be R0 1. So from V0 to ground, you see R0 1 as well. So from V0 to ground, you see RD plus R0 2, and from V0 to ground, you see R0 1 as well. So what will happen? This R0 1 here will come in parallel. And for now, let's call this as resistance R dash. So what will be the gain? Tell me what will be the gain. You can simply apply the potential divider, that would be R dash upon R dash plus 1 by Gm. So the gain would be Gm R dash upon 1 plus Gm R dash. That would be your small signal gain. That's it. Got it? What did I do? I saw this circuit which was given. This circuit was given. So my VB is the DC bias, that will be shorted. So this complete is gone. There is zero current. So now M2 will be replaced with simply with R02. And then I got to know that my R and R02 are in series because both of them will be having the same current. So R plus R02. From V0 to ground, I see R plus R02. Similarly, in M1 as well, from V0 to ground, I see R01 as well. So from V0 to ground, I see RD, not RD. This is not RD. This is R only. So this is R plus R02. And from V0 to ground, I see R01 as well. So R plus R02 parallel with R01. So this is the resistance I am seeing from V0 to ground. And from V0 to ground, I see one MOS as well. This is the MOS. Now it has become common drain amplifier only, but I don't need to remember what kind of amplifier it is. I can simply do the analysis. How do I do the analysis? I know that from V in to here, I see 1 by Gm resistance. So I can simply apply potential divider. That's it. And by applying the potential divider, I get R dash upon R dash plus 1 by Gm. So that is Gm R dash upon 1 plus Gm R dash, right? Or you can say the current here would be Gm V in minus V0. By that also you can find out the expression that we have already seen in the derivation of common drain amplifier. But you don't need to mug up any derivation. You don't need to mug up any formula. In the examination, directly you can write down. What you need to remember? Those two formulas, input impedance and output impedance. Looking from source, looking from drain. That's it. From drain to source, if you are going, you need only one step. And from source to drain, you are going, you need two steps. That means numerator and denominator. That's it. Are you following it up? Are you following it up? Say yes or no. Right? So R dash upon R dash plus 1 by Gm. So Gm R dash upon 1 plus Gm R dash. So what is my R dash? Let's calculate my R dash. R dash would be R plus R02. What is the value of R plus R02? R plus R02. So let's calculate it. IPL चल रहा है भाई, खुल जाए यार. R plus R02. 4.6 plus 23.89. 4.6 plus 23.89. 28.49. 28.49 kilo ohm parallel with R01. What is R01? R01 is 20.63 kilo ohm. 20.63 kilo ohm. 28.49 into 20.63. So parallel combination I have to calculate. To 20.63 into, so 11.96 kilo. 11.96 kilo ohm I am getting. So this is my R dash. Let's calculate Gm R dash. What will be my Gm R dash? What is the value of Gm? Which Gm? This Gm. Gm1 I should have written here. This Gm. Because the transistor M1 is used only. The Gm of transistor M2 is not used. The Gm of only transistor M1 is used. So I should have written Gm1 here. Gm of this transistor. So Gm1 R dash. What is the value of Gm1? Gm1 is 1.92. 1.92 milli into 11.96 kilo. So basically kilo and milli will be cancelled into 1.92 into 1.92. That is 22.97. 22.973, whatever it is. So what will be my gain? My gain would be 22.97 divided by 23.97 plus 1 reciprocal into 22.97, 0.958 or 0.96 nearly. So this is my gain. My gain is coming out to be 0.96. Well and good. What did we do? You must have understood. Here I see R02, R plus R02 comes in series, R01 is in parallel, R plus R02 parallel with R01. This is R dash, so my gain is Gm R dash upon 1 plus Gm R dash. R dash value I get calculated from the given data, Gm1 R dash value I calculated from the given data, and my answer came out to be 0.96. Let's move on to the next question. What is the different thing here? The same circuitry is given, everything is same. The different thing is that, decoding हो रहा है. The different thing is that now RDS2 is infinity. RDS2 is infinity. So what will happen? Let's copy this circuit in the next page. So again, what is going to happen? This will be VB will be shorted. This is shorted. Now this RDS2, this is infinity. RDS2 is infinity. Even this current is gone. Here also there is 0 ampere current. So what is your circuit left? Your circuit is left something like this. This is V in, this is grounded, this is V naught. From V naught to ground you are having R naught 1, and at the lower side you are having this resistance R, and rest of the side is open circuited. That's it. Did you understand this point or not? Did you understand this? Look, what is the scene? This R and the lower side M2 is completely open circuited now. M2 is completely open circuited because there is 0 ampere current and RDS2 is also infinity. So this is completely open circuited. So in R there will be 0 ampere current. Right? Now what is the current coming from here? Let's make this R01 a bit ahead. This is your R01. Now what is the current coming from here? That is Gm V in minus V naught. Right? Now that current cannot go in R. So it has to flow like this. Say yes or no. So the complete current is flowing in this loop only. Did you understand this point or not? Gm V in minus V naught current is flowing. That current cannot go in the R resistance because R is completely open circuited. So if the current goes where it will be from where it will be coming back. If there was ground, then we could say that current can go because the current can go into ground and from here it can come back. But the problem is what? The problem is there is no ground. There is no ground, so no current can go. The current going will be 0 ampere. So that Gm V in minus V naught, that current is flowing, that has to flow through R naught only. And if the current is flowing here, it has to return back here as well. So in the complete loop, the current is flowing. That current is keep on flowing in this loop. Now, what will be the drop here? What will be the drop here? That drop will be Gm current into resistance. So Gm R01 into V in minus V naught. This will be the voltage drop. The current is Gm1 I should write, right? Gm1. The current is Gm1 V in minus V naught. So that current is flowing through R01. So what will be the drop? V naught into Gm1 V in minus V naught into R01. So that is the drop. Now this potential plus this potential is equals to 0. Ground. Simply KCL KVL I am applying. Or you can say this is 0. This potential will be Gm1 R01 V in minus V naught, and that potential is equals to V naught. Did you understand this? This is simple network analysis. This is 0 volt. This is 0 volt. Then from 0 to you are coming here. This potential will be Gm1 R01 V in minus V naught. So basically Gm1 R01 V in minus V naught is equals to V naught. Say yes or no. The complete current is flowing in this loop. So the potential across R01 is GM1 R01 V in minus V naught. Right? So 0 plus GM1 R01 V in minus V naught is equals to V naught. So here GM1 R01 V in is equals to 1 plus GM1 R01 V naught. So what will be V naught by V in? V naught by V in is GM1 R01 upon 1 plus GM1 R01. That's it. So did you understand how did you derive this formula? So in the examination, these kind of questions are asked, and for a lot of aspirants, these kind of questions are very tough. I can guarantee you 99% of aspirants are not able to answer these kind of questions. Forget about aspirant, even forget it. Okay, yeah. So a lot of people are not able to answer. But if you have the concept clear, if you have the concept of network analysis clear, just the basics of network analysis, you can answer these things. Just M2 is open circuited, RDS is also open circuited. There is no current in the R2. So the current that is flowing in M1, that is flowing through R01 as well. So the current is flowing in this loop only. And then you can write down the potential. So the potential here is GM1 R01 V in minus V naught. So 0, then GM1 R01 V in minus V naught is equals to V naught. So from there V naught by V is GM1 R01 upon 1 plus GM1 R01. So let's calculate the value of GM1 into R01. So GM1 into R01. So 1.92 into R01 is 20.63. That would be 39.6096. So here we can calculate the final answer. So 39.6096 divided by 40.6096. So divided by 40.6096, that would be 0.975, and this would be 0.975. So this is the answer. So answer would be 0.975. Well and good. Let's check out one more question. The same kind of question is there, exactly the same circuit is there, but now what is the scene? The scene is both RDS1 and RDS2 are infinity. So let's check out what happens. So let's copy this circuit once again. What will happen to M2? What will happen to this VB? VB will be shorted. So what will happen to this M2? It will completely be open circuited, right? Because here RDS2 is also infinity. So M2 will be completely open circuited. Oh, what I am doing? There is no resistance. This is the scene, right? There is no R02. There is no R01. Sorry, there is no R01. Now, this can have no current. This can have 0 ampere current. And since there is no R01, the same current will be flowing from here. The scene is the source of the MOS is open circuited. Even the source of MOS M1 is open circuited. That is the scene. The source of M1 is open circuited now. In the previous question, what was happening? You were having R01. So whatever the current that flows, that has the path to flow from R01. But now, what is the scene? Whatever the current is flowing, let's just say I'm saying my current flowing is GM V in minus V naught. Now this current doesn't have any path. This current doesn't have any path. This current cannot flow. From where it will flow? In the previous question, it had the path from R01. In this question, it has two paths. From R01, it could have flown from R plus R02. So the current was flowing from R plus R02 parallel with R01. The current was flowing like this. The GM V in minus V naught current was flowing in R plus R02 parallel with R01. In this question, it was flowing from R01. In this question, it doesn't have any path because both of the R01 and R02 are infinity. And this R cannot have some current because there is no ground mentioned. This is open circuited. So if resistance R is open circuited, it cannot have any current. So basically, what did you understand here is that your GM V in minus V naught is equals to 0. So from here, what could you see? That your V in is equals to V naught. So what is your gain now? The gain is 1. That's it. So 3 different questions and 3 different gain. Just by changing the value of R01 and R02. Here both were infinity, so there was no path, so gain was 1. Here one was infinity, one was not infinity, one was finite, so this was the gain. And here both were finite, so this was the gain. 0.96, then 0.975, then 1. So are you able to understand common source amplifier, common drain amplifier? I hope you are getting very much comfortable with MOS amplifiers. If you are getting comfortable, please write it down in the comment section and do share it with your friends so that they could also realize what kind of content is being taught here. Okay, so yeah, let's meet in the next lecture. In next lecture, I am going to tell you a very interesting method, that is GM R out method for finding the gain. So by using this formula, your calculation will be reduced a lot. You will be writing the answer very quickly. Okay, so we will study this in the next lecture. Then we will study all the amplifiers using Pmos as well. Whatever that we studied using Pmos. So we will quickly finish that off. Then we will move to Cascode circuits. Okay, thank you. Hi everyone. So let's see an interesting method of finding voltage gain. This method is known as GM R out method. So if a very complex circuitry is given, then using this method your gain will be found very easily. So that is a very good method, very intuitive method. So when you see a complex circuitry, we should rather use this method for finding the gain. So this method is known as GM R out method. So voltage gain of any configuration would be GM into R out, capital GM into R out. Now this capital GM is not equals to the small gm. Now this capital GM is not the transconductance of a MOS. It can be different. So these are not the same. This is the first thing you should know. Now what is capital GM, what is R out, that we will find out. So this is just a simple circuitry is given. You have applied an input, you are collecting an output across a load. So your gain would be GM into R out. That's it. This is what I have written here. Given circuitry is there, Vs you have applied, you are collecting an output across the load. So your gain would be GM into R out. Now what is capital GM? So what you will do for finding capital GM, you will short circuit the output. You will short circuit the output. Short circuited the output and find out the current in this branch, I out. The current is outward. Are you getting this point? Let's just assume if something is made like this, whatever input is there, something will be there. This is your output. So what you will do, you will short circuit the output, and then you will find the outward current, the current that is going into the output, going into the ground. So outward current you need to find, not the inward current. Do you remember the Norton theorem? Norton theorem. What do we find there? The current going into the output. So this is what you need to find. This is actually a Norton theorem only. Okay, this is nothing, just a Norton theorem. Yeah. So this current you will find shorting the output and the current that is going into it. So what is our GM? Output current by input voltage. So I out by Vs. Everything is small signal. Everything is small signal. All these are small signal only. I out by Vs. That's it. This is your GM. Very easy. Short circuit the output, then find out the output current divided by Vs. And what is R out? We have already studied. What is R out? Just you need to calculate R out here. The same way that we used to find out. Nullify all the independent sources. So if I nullify all the independent sources, that means Vs will be shorted. Vs is gone. Nullifying all the independent sources. I need to apply V naught here and get out of I naught out of it. So what will be my R out? V naught by I out. That's it. What you need to do? You need to short circuit, or not short circuit, you just need to nullify all the independent sources, and thus then just apply V naught and get I naught out of it, and R out would be V naught by I out. That's it. Well and good. Let's see the example. It will be more clear now. So you have to find the small signal gain. Find small signal gain. Find small signal gain. So first thing what you will do, first your target is finding GM. So for GM, what did I tell you? Short circuit the output. This is my V in. Now here I am having a load R naught. My V naught should be shorted. Here it is shorted, and the current should be going in. This should be my I out. What is the current here? GMV in. Now tell me, this GMV in current, here the current also will be GMV in. Will this GMV in current would be going into R naught? No, there will be no current going into R naught because R naught is shorted. This point is 0, this point is also 0. Between 0, 0, R naught is shorted. What is the potential across R naught? That is 0 volt only. So this complete GMV in current is equals to I out. So I out is equals to minus GMV in. Why is it negative? You can see the direction. I out is the outward current. That's why I told you the current would be going into the output. So what will be your capital GM? What is capital GM? I out by V in. That would be minus GM. So this will be your capital GM. What is the second thing? You need to find R out. So how do we find R out? Although we already know what is the R out for this circuit, R naught only. But what is the method? Just short circuit the input. So if I short this, and then I need to find the R out. From here I need to find out R out. So that would be what? R naught only. This would be R naught only. So this is my R out. So V in is gone. So GM V in is gone, right? VGS is gone. This VGS is 0. So this complete MOS will be replaced with open circuit. So from output you see only R naught resistance. So R out is R naught. So what is the gain? Gain would be GM into R out. That means minus GM into R naught. Now people will say, sir, why we are solving it with this method? I already know the gain GM V in into R out. Yeah, I know you know the gain. But when you see a complex circuitry, then it will be used. So this was just an example. We solved an easy example, but we will solve a complex circuitry as well. So when you see a complex circuitry, this will be used, right? Now solve this problem. This also can be solved very easily, but yeah, solve by GM R out method only. Because learning this method is also very important, because sometimes in the interview, they can ask you to solve a particular circuit by using GM R out method. That they can solve that, like they can ask you, like, can you solve this problem using GM R out method? So you should be knowing this method, and a lot of designers use this method. A lot of designer. When you go into the industry, you will see a lot of designer use this method for finding the gain. So what is the first task? First task is to find GM. Output should be shorted. V in is there as it is. This is the output, right? It is shorted. This is RD. What is the current flowing here? Tell me. This potential source is 0. Source is what? 0. And what about this potential? This is V in. So what is the current? GMV in. And what is I out? This is our I out. The current going into the ground. Now tell me where this GM V in current will go. Will this current go through this R naught? No, because R naught is across 0 and 0 potential. This potential is 0, this potential is also 0. So R naught is across 0 and 0 potential. Will this current go into RD? No, because RD is also across 0 and 0 potential. So the complete current will be going in the I out only. So here you can see that I out is equals to GMV. So what is my capital GM? Capital GM is equals to GM only. So here capital GM is equals to GM only. What about R naught? Can you find out R naught on your own? If you can't find R naught for this circuit, then you need to study again, right? Because till now you should be able to find the R out value. Those who are able to find out the R out value, they can proceed with the lectures. Because till now we have studied a lot of circuits and you should be comfortable with finding R out. Oh, this is not R out, this is RD. So from here we are finding R naught. So what do you see? From V0 to ground I see R naught. From V0 to ground I see RD. From V0 to ground I see 1 by GM. That's it. From V0 to ground I see 1 by GM. From V0 to ground I see R naught. From V0 to ground I see RD. That is RD parallel with R naught parallel with 1 by GM. So here what is the voltage gain? Voltage gain is GM RD parallel R naught parallel with 1 by GM. So generally a lot of times the gain are written like this. So if you see gain written like this, you would find out that this gain is written using GM out method only. Because if you find by the equations, you will get a different gain. Although the gain will be different, but the expression will be different. Are you getting my point? Your expression can be something like this. What is R naught parallel GM? R naught parallel 1 by GM. That would be RD parallel. R naught parallel GM would be R naught parallel into 1 by GM. So that would be R out upon GM R naught plus 1. Or even the simplified version. So if you solve by the equation, you can get some expressions like this. But if you see the expression written like this, you would know that this gain is find out. This gain is find out by the using GMRS method. Okay. Let's move on to the next circuit. This circuit, here you have to consider that R01 and R02 are very high. This is the thing you need to consider. Then you need to find out the gain. So let's first find out the GM value. GM value we need to find out. So what you will do, short circuit the output. This VB is the DC supply. VB is the DC supply. So this will also be shorted. Then you need to short the output. So what will be I out? Current going into the output. This will be I out. What is the current flowing here? GMV. Now they are saying that R01 and R02 are very high. They are not saying that it is infinity. They are saying it is very high. So ideally what should happen? This GMV in current should flow through R01 as well. It should flow through R02 as well. It should flow through this MOS as well. Then it should go into I out. Are you getting this point? The GMV in current can flow through R01, R02 or through this MOS and then it should go to I out. But they are saying that R01 and R02 are very high. So we can consider them, they are infinity. So if they are infinity, then this complete GMV in current is flowing through the upper MOS, through M1. Okay, this is GM2 in. So we should write GM2 in because this is M1, this is M2. This is M1, this is M2. So this complete GM2 in current is flowing through M1 and that current is I out only because this I out current is flowing through M1 as well. So I out is equals to GM2 in minus sign. Certainly minus sign is there because the direction is opposite. So capital GM would be minus GM2. That's it. What about R out? What about R out? For finding the R out, here we had the DC bias. This will be shorted. This is V0. This was your M1. This was your M2. What will happen to M2? Even this V in, this will also be shorted. This V in will also be shorted. So tell me what will happen to M2? M2 will be replaced with the R02 resistance only. Here we will consider R0, right? Because R0 is very large, but it's not infinity. R0 is very large. So here we will consider R02. and also here R01 is also there. R01 is also there between source and drain. Between source and drain, R01 is also there. So in M2, what you can see that Vin is also gone, so VGS is also gone. Complete VGS is gone. So here M2 will be simply be replaced with R02 only. So what is your circuit? R02. Tell me what is the resistance here? Do I need to find it out or do I remember it? Do I need to find out or do I remember it? What is the formula? R01 plus R02 upon 1 plus GM R01. Is that correct? You are going from drain to source. You are going backward. So you only need one step. This is wrong. Okay. You are going from where you are collecting the output from. You are going from drain to source. This is where you are seeing from this is where from where you are seeing the resistance. यहाँ से resistance देख रहे हो. You are going from drain to source, right? And from drain to source, I told you one method. If you are going from drain to source, that means you are going backward. So you need only one step. So in one step, how will you write? R out would be, I should write like this. R out would be R01 plus R02 plus GM of what? This one. GM of this one. So GM1 R01 R02. So do you remember this formula? R01, this resistance plus GM of the transistor that is there into R0. Previously, how did we used to write? R0 plus RS plus GM R0 RS. That's it. This can be approximated to GM R01 R02 because this value will be very, very large. So what will be your gain? The gain would be nearly, I should write, because even our GM value is near. This is not perfect. Even our GM value is not perfect, right? Because here we have made the assumption that R01 and R02 are very high, so the complete current is going in the output. So that is the assumption there. So minus GM2 into this output resistance, that is R01 plus R02 plus GM1 R01 R02. Now this can also be approximated. So what is your gain? GM of both of the transistor into R0. I am not seeing the expression. There is someone messaging me. This is what I am seeing. मैसेज किसी का नहीं है कि कोई डाउट ही पूछ रहा है वैसे, और किसी का मैसेज आता भी नहीं मेरे पास. Yeah. So gain is minus GM2 GM1 R01 R02. This particular structure is known as Cascode, although we will study it, but to give you a heads up, I show the expression here only. So I hope you are understanding. First, what did we do? First, we find out the I out value, that was minus GM2 V in. So GM value was minus GM2. Then we find out the R out value. And how do we find out? Because we already remember the formula. The formula is R01 plus R02 plus GM R01 R02. Well and good. So approximately this was the gain. Now we will see a problem where you cannot assume that your R01 and R02 are very high, because I have taken the value to be very, very low, 2 kilo ohm only. Here I have written a note. This question is framed by me only. So I have written a note. Generally GM values are in millisiemens and R0 values are in mega ohms. We took such values only for the understanding purpose. So generally these values are not these kind of. R02 cannot be 2 kilo ohm. In a practical circuit, R02 will be very high. It will not be infinity, but it will be in mega ohms. But we can frame the question with any values, and even in the examination or even in the interview, they can ask you any kind of circuitry with any kind of values. So you should be able to solve it. Try to solve the question. The same circuitry is there, whatever the circuitry we saw in the previous problem, the same circuitry is there. Now I need you to find the final gain. So try finding the gain by the GMR out method only, because if you go by the equations, it will take a lot of time. So find the gain by GMR out method. Let's solve it. Let's copy this circuit. Short circuit the output. First is GM value you need to find out. So short circuiting the output. Here you need to find out the current. So let's make a better circuit. And I will short circuit the output. We are finding the value of GM. What will be the current here? This is M2 and this is M1. What will be the current here? GM to V in. This is correct. Now you cannot say that the complete current will be going in the output. You cannot say that. Why so? Because R02 and R01 values are not very high. This is R02 and here you can make, this is your R01. Now where will this current be divided? This GM-V in current will be divided into three parts. It will go into R01, it will go into R02 and it will go into M1 as well, right? This GM2V in current will go into R01, R02 and M1 as well. Well and good. Now how will you find out which one will have what amount of current? And why we are finding these current? Because what will be your I out? What will be your I out? Tell me. What will be your I out? The current in R02 plus the current in M1. Are you agreeing to this point? This current plus this current is equals to I out. Say yes or no. Current in R02, current in M1, addition of those current is equals to I out. Say yes or no. Well and good. So you just need to find out the current in M1 resistance and you need to find out the current in R02 resistance. So tell me how much current will be going. What is the value of R01? 2 kilo ohm. What is the value of R02? 2 kilo ohm. Both are equal. So this is certain that R01 and R02 will be having the same current. That's for sure. You need to divide the current from this node. You know the current in one of the nodes. And now you need to divide the current in three nodes. I will give you a simple network analysis question. If I am saying this is 3 ampere current source, here I am saying I am having 1 ohm resistance. Here I am saying I am having again 1 ohm resistance. And here I am saying I am again having 1 ohm resistance. You need to divide the current from this node. So tell me in each node how much current would be going. In this resistance 1 ampere current would be going. In this resistance 1 ampere current would be going. And in this resistance 1 ampere current would be going like this. Say yes or no. Right? 1 ampere, 1 ampere and 1 ampere. Right? Well and good. So similarly, what amount of resistance do you see from here? This VB is shorted for sure. From V node, what amount of resistance do you see? From V node to ground. From here to ground, what do you see? 1 by GM. Say yes or no. From V to ground, you see 1 by GM. From V to ground, you see R02. From V to ground, you see R01. So you can simply replace it something like this. From V to ground, I see R0 1 by GM1. And here I am having a current that is GM2 V in. Here I see R02 and here I see R01. This is the same as the circuit that I just now discussed. What is the value of this? 1 by GM1, that is equals to 2 kilo ohm. This is also 2 kilo ohm. This is also 2 kilo ohm. Although all are grounded and whatever the current that ground is eating up, all are grounded. Whatever the current that is going here, that will be our final answer. right? So 2 kilo ohm, 2 kilo ohm and 2 kilo ohm. So here 1 by 3 part would be going of GM2 V in, and here also 1 by 3 part would be going GM2 V in. Wait a minute, what would be the direction? What would be the direction of current? That I need to check out. Yeah, this will be the direction of current only. The direction of current would be GM2 V in by 3. This is GM2 V in by 3. And what about this? This would be in this direction. GM2 V in by 3. Are you able to imagine it? This node, if you are not able to imagine anything, you can apply nodal analysis. But I am just giving you a simple shorter method. If you just apply V here, what would be the current? In this direction, GM1 V. But this V value will be negative. Or you can see that there is this current source. Here there is this resistance. Here there is one more resistance, and here there is one more resistance. And this is, let's assume, 3 ampere current source. 1 ampere current would be going this way. 1 ampere current would be going this way. 1 ampere current would be going this way. All the currents are coming from ground. If there is 3 ampere current source which is going through the ground, which is going towards the ground, then all the currents will be coming out from the ground only. So same thing is happening. There is a current source GM2 V in which is going into the ground, so all the currents will be coming out from the ground only. So in this resistance, current coming out of the ground, current coming out of the ground, current coming out of the ground. 3 ampere current was coming out of the ground. 1 ampere, 1 ampere, 1 ampere. Addition of this is 3 ampere. Same thing is happening here. The current will be coming out of the ground. GM2 V in by 3, GM2 V in by 3, and GM2 V in by 3. Addition would be GM2 V in. That's it. So tell me, what is our I out now? What is our I out? So our I out is minus GM2 V in by 3 plus GM2 V in by 3. So I out is minus 2 GM2 by 3 V in. So what is your capital GM? So here your capital GM is minus GM2 by 3, and GM2 value is 3 millisiemens. So okay, let's keep it like this only. So GM value is minus 2 GM2 by 3. What was the GM value in this question? That was equals to GM2 minus GM2 only. Now our answer is minus GM2 by 3. Why so? Because now our GM value depends on R01 and R02 as well. Here R02 and R01 was very high, but now in this case R02 and R01 are considerable. They are not very high. So that's why I took this example, so that you also consider R01 and R02 values as well. You can see GM2 V in, then the currents are divided into 3 equal parts. Addition of both of the currents is equals to I out. So here we could see the addition of both of the currents were 2 by 3 GM2 V in. So GM2 value is minus 2 GM2 by 3. Well and good. Now you need to tell the R out value. What will be the value of R out? I will directly write down R01 plus R02 plus GM1 R01 R02. Well and good. 2 kilo ohm plus 2 kilo ohm plus 1 by 2 kilo ohm into 2 kilo ohm into 2 kilo ohm. So R out value is 6 kilo ohm. So what is my gain? Minus 2 by 3 GM2. GM2 is 3 millisiemens into 6 kilo. So my gain is minus 12 volt per volt. So these kind of questions can be asked any day in the examination, where R01 and R02 are very high. R01 and R02 are not very high. Here R01 and R02 are considerable, so we have to consider the current as well. If you find out by the general method, it will take 2 equations, but still you can find out. Still you can certainly find out. What you will do? If you just find out by the general equation, so you will have to consider a V voltage here. Then you write down one KVL, not KVL, sorry, KCL. You just need to apply nodal at this V potential. So that would be GM V current, GM V current in upward direction, V minus V naught by R naught 1 plus V by R naught 2 plus GM V in equals to 0. Then you need to write one more nodal. What that nodal would be? You need to escape from the potential V that you can find out. Okay, try solving it with nodal analysis as well. You can find it out. But this is the best method to find out by the GMR out method. It would be very comfortable if you solve some problems by this method, then you will be very comfortable with that. Now we will be solving a lot of problems with this GMR out method. So no worries about that. You will be very comfortable with GMR out method as well, because in complex circuitry this will be used a lot of times. Well and good. Yeah. So let's move on to our next topic. That would be, we will be studying all the Pmos amplifier as well. We have studied all the NMOS amplifier, but why not let's study Pmos amplifier. So in next 30 minutes we will be covering all the Pmos amplifier, because we already know the NMOS amplifiers. It will be same as the NMOS amplifier, nothing is different. So what is this? This is common source amplifier, you can certainly see. Why so? Because source is common. Source is common and input is applied at gate, output we are collecting at drain. So everything that we studied in the NMOS amplifier, the same will be in the Pmos amplifier. In NMOS amplifier, what was happening? Source was grounded, input was applied here, output was collecting here. Input at gate, output at drain. Same thing is happening. Input at gate, output at drain. Drain RD. This is V0. And from V0 to ground, we can see one more resistance, that is R0 resistance. The R0 resistance is connected between source and drain. Drain is at V0 and source is at ground. So between V0 and ground we see R0 resistance as well. So from V0 to ground we can actually see RD parallel R0. That's it. Well and good. Are you understanding all the points? Because we have already studied it. Now what is the current flowing in the MOS? That would be GM V in this direction. Are you agreeing to this point? No. That would be GM V in upward direction. I told you one method. What did I tell you? What did I tell you? Let's assume if this is the voltage and this is ground. No, forget it. If this is voltage V1, this is voltage V2. So how will you write the current? You can write the current in two manners. If you are going from this way, you are going from V1 to V2. So your current would be GM V1 minus V2. That's it. If you are going from V2 to V1, your current would be GM V2 minus V1. All these are small signal current. So in the same manner, if you are going from ground to V in, if you are going from 0 to V in, your current would be in this direction, because you are going from 0 to V in. Whatever the direction you are moving from here to here. So your current would be from up to down. So that current would be GM into this potential minus this potential. That would be minus GM V in this direction. So in upward direction it would be GM V in. Or you can write down how? You can say that I am moving from V into 0. That means I am moving in upward direction. So my current would be this potential minus 0 potential. So GM V in upward direction. Well and good. Say yes or no. Right? So this way you can write, or you can simply say that what is the current in the MOS? That would be GM VSG. GM VSG. So GM, what is VS? VS is at 0 potential and gate is at V in. So GM V in current in downward direction minus GM V in current in downward direction. So in upward direction GM V in. But all these things are very theoretical. But if we are solving just the circuit, we can quickly do our analysis. How we will quickly do our analysis? By just seeing the potential direction. Okay, GM V in to 0. That means in upward direction GM V in. That's it. Well and good. So in upward direction the current is GM V in. The same current will be flowing through RD parallel R0. So what will be your V0 by V in? Minus sign would be there, minus GM RD parallel R0. Exactly the same gain will be there. Nothing difference will be there. No difference. Exactly the same gain. No difference at all. The current is flowing in the upward direction. So simply, basically this will be the drop, no? So this is 0, the V0 would be negative. Well and good. This was common source amplifier. And yeah, we can find out other things as well. What will be the current gain, voltage gain? Sorry, voltage gain we have already found. What will be the current gain and input resistance? Both will be equal and equal to infinity. Why so? Because the input current is 0. Why is it so? Because input current is 0. What about output impedance? If you are able to write the output impedance by your own, you can skip this part. So quickly we will see what will be the output impedance. Why quickly? Because we have studied very deeply in NMOS amplifier. Input will be shorted, right? Because we are calculating the output amplifier. VDD will also be shorted. Here we were having RD. From here we are calculating the R out. And from this node to ground, you are having R naught. From this node to ground, you see R naught parallel with, from this node to ground, you see RD. That's it. Is there any current in this MOS? No, because VSG is 0. VSG is 0. Both the potential are 0. So there is no current in this MOS. So this MOS is simply open circuited. So from V0 to ground, you see RD. From V0 to ground, you see R0. So RD parallel R0. That's it. Well and good. Let's see common source amplifier with degeneration. We know the reason why degeneration is used. Everything we know. Now let's just see the voltage gain and everything. What will be the voltage gain? Tell me. What will be the voltage gain? Directly you tell me. Do I need to derive? I remember it. That would be minus, yeah, one thing I will write. This is considering lambda equals to 0. Because if I don't consider lambda equals to 0, what will happen? The expression will be very complex. So what will be the gain? That would be minus Gm Rs. Sorry, minus Gm Rd upon 1 plus Gm Rs. The same gain that we get in the common source amplifier. But because of degeneration, the gain is lesser. That would be 1 plus GMRS divided by 1 plus GMRS. Previously, the gain was minus GMRD. Now the gain is minus GMRD upon 1 plus GMRS. Well and good. You can derive it as well. How will you derive it? This potential is V. So the current here would be GM V in minus V. The current here would be GM V minus V in. Sorry. We are going from this to this potential. So GM V minus V. Right? VDD will be shorted. But you don't need to write the potential of this. You need to write the potential of this. This current would also be GM V minus V in, because in the complete circuit the same current would be there, because there is no R02. Even if there was R02, this current would be there only, right? You just need to eradicate the V potential. How will you eradicate the V potential? You can see that V by Rs is equals to minus V0 by Rd. The same derivation is there. We should not call it derivation, because this is not a derivation. You are just using your brain here. Minus Rs by Rd into V0. So what will be your V0? V0 would be Gm Rd into V is minus Rs Rd into V0 minus V. So V0 into 1 plus Gm Rs is equals to minus Gm Rd into V in. So what will be your V0 by V in? That would be minus Gm Rd upon 1 plus Gm Rs. So I showed you the derivation as well, but we already remember it by the common source amplifier that we studied using NMOS. In NMOS, we have studied the same formula. The source is degenerated by this resistance Rs. So whatever the degeneration resistance is there, that will come in the denominator. Yeah, one more thing I forgot to tell you. Here in the degeneration, one more benefit is there. What is that benefit? in degeneration, what is the gain that we are getting? This is applicable for NMOS amplifier as well, but I forgot to tell you what is the gain we are getting. Gain is minus GMRD. I don't remember if I told you or not, but let's see it once again. This is the gain, minus GMRD upon 1 plus GMRS. If your GMRS is very greater than 1, which you can set by adjusting the RS value. If your GMRS is very greater than 1, then what will happen? What will be your gain? Minus GMRD upon GMRS only. Say yes or no. What is the gain you are getting? Minus RD by RS. Isn't it a constant gain? Constant gain, which is very stable, right? If your gain is GMRD, then it is depending on GM, and GM depends on under root ID, and ID depends on temperature. So your gain depends on temperature. With the temperature, the gain can change. At some temperature, you may hear a very loud noise, and at some temperature, you will hear a very low noise, right? So the gain can change with respect to temperature, and this is not what you want. But using the degeneration, you are getting a constant gain. So this is also a benefit of degeneration. We will remember it. Okay. If you set your GMRS such that your GMRS value is very high, then your gain would be constant. That is depending on simply two resistances. Well and good. Let's move on to the output resistance. You tell me what will be the output impedance. From here you are calculating the output impedance. R out. You are going from drain to source. You are going backward from drain to source. What is the picture in our mind? This is source, this is drain. We are going from drain to source. That means I will need only one step. So in one step only I can go in the backward direction. That would be, so our gain would be RD parallel with this resistance. RD from V0 to ground I see RD. So RD parallel with this much of resistance. And this will be grounded as well. So from V0 to ground I see RD, from V0 to ground I see this resistance as well. So direction of R out should not be like this. I mean this arrow direction should not be this way, because you are calculating the resistance here. So this should be your arrow direction, not upward. If the arrow direction is upward, that means I am taking only this much of resistance. If arrow direction is downward, that means I am taking this much of resistance. But if the arrow direction is in this way, that means I am taking all the resistance. So RD parallel with this RX. RD parallel. What is our RX? RX is you need only one step. In one step, R0 plus RS plus GM R0 RS. That's it. You can also make an approximation here that this value will be very large, so it can be approximated to GM R0 RS. Practically this value is very larger than R0 RS, so we can approximate it in this manner. Well and good. Everything is you are understanding everything, right? Let's move on to our next circuit, that is common gate amplifier. So in common gate amplifier, what is the scene? The gate is shorted and input is applied at source. You collect the output at drain. Did you notice one thing? We never apply input at drain. We never apply input at drain. So your input will be at source and you are collecting your output at drain. Common gate amplifier. We are writing the gain considering lambda equals to 0. If lambda is not 0, you can write it down on your own way, right? You can write it down now. If lambda is not equals to 0, what will happen? If lambda is not equals to 0, then there is this resistance. So the GMV in current that is flowing here, this is the GMV in current. So that is flowing here, that will be flowing through R0, this R0 as well and RD as well. So you can write down your gain in that manner. That we have already seen in NMOS amplifier. But here I am writing the gain only considering lambda is 0. So what is the current flowing? From this to this, we are writing from V in to ground. So what is the current? From up to low, from up to down, GMV in current. Now the same current is flowing through RD. This is the MOSFET current. So in MOSFET, GMVin current is flowing. If there was R naught as well, if there was small R naught, so the current would have been flowing through small R naught as well. So you would have to write down that nodal analysis, and with that you could have find out the gain. But GMVin current that is flowing through RD. So V naught would be V naught by Vin would be GMRD only. That is the gain. Yeah, well and good. You can write down the input output impedance, everything that we will see. So what is the input impedance? Tell me. From here we are calculating. So RS parallel with this resistance. Are you understanding this point? This will be shorted, VGG will be shorted, VGG will be gone. So what will be your input resistance? Did I say parallel? No, no, no. RS in series with this resistance. From here, what is the resistance do you see? RS from VS, what do I see? RS in series with this resistance. So what is that resistance? You are going from source to drain. That means you are going ahead. From source to drain, you are going ahead. That means you need two step. So in two step, what do we write? RD plus R naught upon 1 plus GM R naught. This R naught plus RD plus 1 plus GM R naught. R naught plus RD upon 1 plus GM R naught. That's it. How do you write? R naught plus RD upon 1 plus GM R naught. If there was only one step, what would have written? R naught plus RD plus GM R naught RD. So in this manner, you need to remember this one, and in this manner, you need to remember this one. From source to drain, we are going. The gate is shorted. In both of the cases that we remember, you don't need to remember it is input impedance or output impedance. You just need to remember we are going from source to drain. Okay, and gate is shorted. Source to drain. Source to drain, that means two steps. Numerator and denominator. How do we write? R naught plus RD upon 1 plus GM R naught. That's it. So this is our input impedance. So RS in series with this impedance. Well and good. What else we need to write? Output impedance. So how will we write it? This will be shorted. So here what do you see in output? From V0 to ground I see RD. From V0 to ground I see RX as well. So my R out would be RD parallel RX. And how do I write RX? How do I write RX? How do I write RX? From drain to source. I am going from drain to source. That means I am going backward. If I am going backward, that means I need only one step, and in one step only I can write it down. So how I will write R0 plus RS plus GM R0 RS. Well and good. Let's move on to the current gain. What is the current gain here? 1. Current gain is 1. You can see the same current is flowing. I in and I out. Both current are same. I in is getting divided into two parts, MOS and R0, then going out. So I in and I out are same. Well and good. Let's study common drain amplifier. So here you are applying the input at the gate and you are collecting output at the source. And drain is common. This is the drain which is common. Drain is common. And yeah, what do I mean by VSS? In all those questions I have used VSS. I hope I am able to find. So here only in common drain amplifier only I used VSS. So it is low potential. It can be anything. It can be 0.2. It can be simply ground as well. It can be 0.1. It is lower than VDD. If your VDD is 5-fold, let's assume. So it will be VSS would be some 0.2, 0.1. Lower than VDD. Because in the Pmos, the drain is at low potential. That's why I wrote VSS here. Okay, it can be ground as well. Well and good. You just need to make sure that your transistor is working in saturation region. That's it. Because you are using it as an amplifier. Common drain amplifier it is. So this VGG will also be gone. This Vin will simply be small signal input voltage. So what will be the gain? How will you write the gain? From here to here you see 1 by GM resistance. Here you see 1 by GM resistance, right? What did I tell you? From source to drain. Sorry, from source to gate I see 1 by GM resistance. From source to gate I see 1 by GM resistance. That is, this is what I see. From source to gate I see 1 by GM resistance. So at gate you are having V in. At gate you are having V in. from gate to source or from source to gate you see 1 by Gm resistance, and at this source you are having Rs, and now Rs will be grounded and this will be V0. So what will be your V0 by Vin? Simply the potential divider. So Rs upon Rs plus 1 by Gm. So potential divider would be Gm Rs upon 1 plus Gm Rs. Well and good. This is considering lambda equals to 0. If lambda was not equals to 0, then what would have been the gain? If lambda was not equals to 0, then from V0 to ground you could see 1 R0 as well, right? Because between source and drain you see R0 too. Why I am writing R0 too? It is only R0. So from source to drain you see R0. From source to drain you see R0. So from source to drain you see R0. Rs parallel R0. V0 by Vin would simply be Gm Rs parallel R0 upon 1 plus Gm Rs parallel R0. No need to mug up any formula. What you will do in the examination, you will derive it within seconds. The time you take in remembering the formula, the same time you will be taking in deriving it, because you will be directly seeing, okay, 1 by Gm Rs potential divider, that's it. Here you are directly seeing current gain is 1, output impedance I remember, input impedance I remember. Here what is the gain? You can directly see Gm V in current is going, that is flowing through Rd. What is the gain? Gm Rd. So many times even the educator tell to remember the formula, but you don't need to remember because we have shortened the method. We are not drawing any model or anything. Just using the MOS circuitry we are writing down the final expression. Do I draw any T model, pi model, anything? No. Without using any model, we are writing the gain. And anything they can ask, output impedance, we can write anything with the fastest method. Well and good. Whatever is remaining now. Output impedance I have written. No, sorry. Here I did not write the output impedance. I can write down the output impedance as well. अच्छा भाई को P. So how will I write the output impedance? This Vin will be shorted. This Vin will be shorted. So tell me, from V0 to source, from source to gate. From source to gate you could see 1 by Gm resistance. Now from source to ground you could see 1 by Gm. So from V0 to ground you could see 1 by Gm. From V0 to ground you could see R0. From V0 to ground you see Rs, because Rd is also, this VDD is also gone. Are you getting this point? From V0 to ground I see Rs, from V0 to ground I see R0, from V0 to ground I see 1 by Gm. So what is my R0, R out? That is R0 parallel with Rs parallel with 1 by Gm. That's it. This we have completely studied Pmos amplifier as well, and with that you must have also revised NMOS amplifier. So I hope you are comfortable with this MOS amplifier topic. So a few more things are remaining in MOS amplifier. We are going to study cascode current source, then we are going to study cascode amplifiers, then we are going to study current mirrors. After that it will be completed. Then we have to study frequency response, differential amplifier and feedback topology. That is a different topic. But till now I hope you are comfortable. Now we are going to solve 2 or 3 assignments. Minimum 2 and maximum 3 assignments we are going to solve. So yeah. So whatever the knowledge we have gained, just revise the notes again. You will be very comfortable with all the topics, and then try solving the assignments. Okay, let's meet in the next video. Thank you. Hi everyone. So in this lecture we are going to see the assignment 7. So let me show you the questions. So there are a lot of questions in this one, but these questions don't require much of calculation. So you will be able to solve very quickly. So this is the first one. You have to find small signal voltage gain. Second, third, you have to determine small signal Rx resistance, and GM1 and GM2 value are given for both transistors. Fourth, you have to determine R out. This is actually a very good question. Might be the best question of this session. And there are a bit of tough questions as well. There are some easy questions and some tough questions. So yeah, this is the next one. This is one more good question. This is the next one. This is very straightforward question. Just for conceptual understanding, I have put this question here and then this question. Yeah, that's it. So let's try solving from first question. So this is the question. You have to find the small signal voltage gain. Very easy question. All of you must have solved this question, right? All of you must have solved it. Well and good. So what you would do? You will draw the small signal model. Then what will happen? VDD will be shorted. This is your V in. Then this VB will also be shorted. If VB is shorted, what will happen? This VB is shorted. So if VB is shorted and VGS is gone. No, this is Pmos. VGS is not gone. From V0 to ground, you could see 1 by GM. From V0 to ground, you could see R0 too. Are you getting this point? You can't say that VGS is gone. This is Pmos. VSG is there. VSG is there. From V0 to ground, you could see 1 by GM. From V0 to ground, you could see R0. Well and good. And from V0 to ground, here also you could see R0. From V0 to ground, here again you could see R0. So what you can say? This is the scene. And from V0 to ground, you could see, here you could see 1 by GM resistance, 1 by GM2 I will write. Parallel with, from V0 to ground, you could see R02. Parallel with, from V0 to ground, you could see R01. Well and good. And this is V in. This is grounded. So what is the current flowing in this direction? 0 to V in you can write, or you should write in upward direction. GM V in. Right, because I am going from V in to 0. So in upward direction I am writing GM V in current. Well and good. So this current will be flowing from here as well. This is GM1 V in actually. So what will be your V0? V0 by V in. That would be GM1 into 1 by GM2. The current is flowing in upward direction. So the drop will be like this. So there will be negative sign. Are you getting this point? Or you can say this is common source amplifier. If there is common source amplifier, that means there will be negative sign. Or you can see that GM1 V in current is flowing in upward direction from ground to V0. So this will be positive, this will be negative. So there will be negative sign. Parallel with R02, parallel with R01. That's it. That's the answer. Very easy question. These kind of question we have solved a lot of times, and there is high practice. We have done high practice for these kind of questions. So you should be able to solve these kind of problems now. Tell me what is V1 by V2. This is a very easy question. You should be able to tell what is V1 by V2. What is happening here? You will draw the small signal model, then VDD will be shorted. All these are small signal. It would be written that find V1 by V2. In the question it will be written small signal. Okay. In the question itself it will be written that small signal they are asking. Yeah. So VDD will be shorted. This is RD. This is RD by 2. This is V in. This is V2. This is V1. What do I need? V1 by V2. Do I need V in? Look, ideally the current here should be GM V in minus V2. I know that. GM V in minus V2. But why do I need to introduce V in? In the final answer, I don't even need V in. What do I know? In the whole MOS, there will be the same current. And they are saying lambda is not equal to 0. So here there will be R not connected. Here there will be R not connected. But I know one thing, that if there is I current here, the same current will be flowing here. Because V1 by both will be having the same current. Are you getting this point? Whatever the current is flowing here, that will be divided into MOS and R0 and will get out of V2. Right? So the same current will be flowing. So what will be V1? V1 would be minus I into RD. Right? Because this will be positive and this will be negative. And what will be V2? This will be positive, this will be negative. So V2 will be minus I into RD by 2. What do we need to find? V1 by V2. So V1 by V2 would be 2. That's it. Well and good. Let's move on to the next problem. These are very, very easy problem. This is also very easy. You just need to have the patience and solve this problem. That's it. Just have the patience and try solving this problem. You know everything. You just need to write the equation. You just need to write the current, whatever you need to find. Based on that, you need to write the equation. That's it. What do you need to find? Rx. What you will do? Apply Vx and get Ix current out of it. So this is the first step. And draw the small signal model. So let's draw the small signal model first. Okay, I will draw it directly only. So what will happen? VDD will be shorted. VDD will be shorted. Then you are having 100 kilo ohm. Then you are having the MOS. Then here it is. This current source will be gone because this is DC bias. And this VDD will also be gone. This VDD will also be shorted, whatever there is. Okay, so 0, 0, everything is gone. Well and good. Understood? You need to find Rx. What you will do if you need to find Rx? Here you need to find Rx. So you will apply Vx and get Ix out of it. So what will be your Rx? Vx by Ix. Well and good. Whatever there is the current, whatever the current is Ix, here there will be zero current, right? 0 ampere current. So the complete current will be flowing here only. Ix will be flowing through M1 only. This is M1 and this is M2. Are you getting this point? From Vx you get a Ix current. There is 0 ampere current in the gate terminal. So M2 is having 0 ampere current. So all the current is having M1. M1 is having all the current. So Ix is completely flowing through M1. Now, what do you know? What is the current in M1? Can you tell me? That would be current Ix. Ix would be Gm. If I write in the upward direction, I am writing in the upward direction. So Vx to this potential. Let's assume this potential is V. So Ix would be Gm Vx minus V. Are you agreeing to this point? Yes or no? Tell me. What do I get to know? That if I apply a Ix, the complete current will be flowing through M1. So what is the current in M1? That is Gm Vx minus V. Vx minus V from down to up. That's it. Now you need to eradicate the V. This V you need to eradicate because this is what you don't want. You only want Vx by Ix. So you need to eradicate this V. How will you eradicate that V? This Vx potential will be here as well, right? There is no current but the potential will be there. There is no current but the potential will be there. Vx will be carried. So if Vx is there, that means here there will be Gm Vx current. Yes or no? This Vx is coming, so there will be Gm Vx current. Now what is the current here? 0 amp. So the same Gm Vx current is flowing through this resistance. Say yes or no. Did you understand this point? The voltage drop will be in this direction. So what will be your V? Let's call this resistance as R. So what will be your V? V would be minus Gm Vx current into resistance R. That's it. Here R is our 100 kilo ohm. What did I do? I needed to find Rx. So Rx is Vx by Ix. I got to know that complete Ix is flowing through M1. Okay. So I just need to write the current in M1. I wrote the current. What will be the current? Gm Vx minus V. Now the problem is this V. I need to eradicate it. So I will use the other transistor. In the other transistor, why am I writing Gm only? Because Gm1 and Gm2 are equal. That's why I am writing Gm. Okay. So I got to know that there will be Gm Vx current. Now the same Gm Vx current would be flowing through the resistance R. So the voltage drop across resistance R is equals to V. That's it. Minus Gm Vx into R. Now I will put here. So Ix is equals to Gm Vx plus Gm Vx into R. Right? Yeah, I have the page. So Vx will be common. Ix equals to Gm into 1 plus Gmr equals to Vx. So Rx, that would be equals to Vx by Ix would be equals to 1 by Gm into 1 plus Gmr. 1 by, what is the value of Gm? Gm is 10 to the power minus 4, I guess. Gm is 10 to the power minus 4 into 1 plus 10 to the power minus 4 into what is the value of R? R is 10 to the power 5. So it would be 1 by 11 into 10 to the power 4. 1 by 11 into 10 to the power 4. So this is your Rx. What is 1 by 11? 1 by 11, as far as I remember, it is 0.909. So the answer should be 909.09. 1 by 11 is a very interesting value. Okay, try doing it in your calculator. You will get to know it is 0.909090909. Okay, so that's why I remember it. That would be 909.09 as far as I remember. Okay, so yeah, this should be the answer. So this is your Rx. So I hope you are comfortable with these kind of questions. In the examination, no question will be tough. I am pretty sure 99.99%, 99.9% students will not be able to answer these kind of question in the examination, because they will think, okay, what they have asked. But very easy question. Step by step we will go. What we need to find, that we will write. Then whatever that is creating the problem, we need to eradicate that. That's it. With the similar concept, we will try to solve this problem. This is the best question of this set. If you are able to solve it, believe me, you will be able to solve every single question in the examination. So V in 1 and V in 2 are the small signal input. You have to find the small signal R out. So this is the question. First draw the small signal model and then try to think. V in 1 and V in 2 are small signal input. So if you are finding any resistance, they will be shorted. This current source is also DC, this will also be shorted. This is also DC, not shorted, open circuited. Current source will be open circuited, this will also be open circuited. So first draw the small signal model, at least that should be correct. At least you should be comfortable with drawing the small signal model. Also note that lambda is not equals to 0. That means R naught will be existing. So let's draw the small signal model now. So what will happen? This will be gone. Now VDD is gone because there is no use of VDD. This will be shorted. Both transistor are M, so both will have same GM and both will have same R naught. So this will have the R naught. This will also have the R naught. Now this current source will also be gone. What do you need to write? V naught, you apply V naught and get I naught out of it. So R out is V naught by I naught. This you need to find. R out is, लिख देते हैं R out is V naught by I naught. So this you need to find. So how will you find that? And V in 1 and V in 2 are shorted. These are also gone. Okay. Does that seem like an common gate amplifier? Gate is shorted, so common gate amplifier is there. Certainly we are going to use something that we remember. Certainly we are going to use that. You need to write the impedance from here. So what if I replace this complete transistor with an impedance? Look, what you need to write. This is your MOS. From here you are writing your output impedance, right? From here you are writing your output impedance. What if I replace this complete by an impedance? Because I am writing my impedance from here. So my answer would be this impedance plus whatever the impedance I see downward. So what impedance I see downward? Tell me where you are looking. First thing is gate is common. Okay. Now you are going from source to drain. That means you are going ahead. If you are going ahead, that means you need 2 steps. So what this will be replaced with? If you are going ahead, you will need 2 steps. So what it 2 steps means? Numerator and denominator. R naught plus R naught plus R upon 1 plus GM R naught. R naught plus R upon 1 plus GM R naught. That's it. So this is how it is replaced. Now you need to write the impedance from here. What is happening? Gate is shorted. Gate is shorted. Now you are going from drain to source. You are going from drain to source. That means you are going backward. So in one step only you will be able to write down the final answer. So what will be the final answer? That would be R naught plus this impedance. R naught plus this impedance plus GM R naught into this impedance. R naught plus this impedance plus GM R naught into this impedance. This impedance is R naught plus R upon 1 plus GM R naught. So what you can take common here? You can take this value common, right? So you can take R naught plus R upon 1 plus GM R naught common. So this is common. So here I am getting 1 plus GM R naught. So GM R naught and GM R naught are cancelled. So what you are getting? 2 R naught plus R. This is your R out. That's it. So this is the final answer. So in the examination, they can give you this value of small R naught and R. They can ask you the final R out impedance. So that would be very interesting. So whenever you see the gate is common, something you already know. Whenever you see the gate is common, then there will be something that you certainly already know. You know the resistance from source to drain. You know the resistance from drain to source. What is the resistance from source to drain? From source to drain we are going. We would need numerator and denominator. R naught plus R upon 1 plus GM R naught. If you are going from drain to source, that means you would need only one step. So R naught plus this resistance plus GM multiplication of both of the resistance. That's it. This is how we are able to write down the answer. So that's why I said just remember these two formulas. It will be very, very helpful for you. Well and good. Let's move on to the next question. Small signal voltage gain, very easy question. What you need to do? Draw the small signal model. Very easy question, you should be able to solve it. So this VG is a DC supply. All these will be written in the examination. I should have written it here. But yeah, I hope you must have understood what is VG. VG is the small signal, large signal voltage only. That means DC supply only. VDD will also be shorted. This is also gone. That's it. Now here gate and source both are shorted. VGS is gone. Lambda is 0 or not? Lambda is not 0 here. Okay. This should be given. Lambda is not 0. So we will consider the worst case. So yeah. So M3 VGS is gone. VSG is gone. VSG is gone. So there is no current. M3 will simply be replaced by its resistance. That is R03. That's it. What about this? Tell me. From V0 to ground here you see R03. What you will say? What did I tell you? From source to gate I see 1 by GM. From source to drain I see R0. What did I tell you? From source to gate I see 1 by GM. Right? From source to drain I see R0. Always remember this thing. That's it. If the MOS is there, if this is the MOS, this is source, this is gate, this is source, this is drain. You just need to say from source to gate I see 1 by GM, and from source to drain I see R0. Always remember it. Always, very, very important. It will reduce your problem a lot of times. And you can see it, right? It's not something that you need to put pressure on your brain, then only you can remember. I told you this is 1 by GM because the current here is GM VGS, and here we connect R0 only. So between source to gate drain I see R0, source to gate I see 1 by GM. Now here gate and drain are shorted because gate is also grounded and drain is also grounded. Both are grounded. So what you can say, from source to gate IC 1 by GM, or you can say from source to ground IC 1 by GM, from source to ground IC R0. So this M2 will be replaced with what? 1 by GM parallel with R0, right? From source to ground IC 1 by GM, from source to drain IC R0. So this M2 will be replaced with 1 by GM parallel with R0. Say yes or no, right? Now from source, from V0 to ground IC R0 1 as well. What you can say, from V0 to ground IC R0 3, from V0 to ground IC R0 1, from V0 to ground IC 1 by GM2 parallel with R0 2. Say yes or no. Say yes or no. From V0 to ground IC 1 by GM2 parallel with R0 2. So this is our circuit. Common source amplifier it is. This is my small signal Vin. This is my V0. From V0 to ground, what do I see? From V0 to ground I see M1. From V0 to ground I see R0 1 I see, R0 3 I see. What else I see? 1 by GM2 parallel with R0 2. Say yes or no. All are grounded. And this GM Vin current will be flowing like this. GM1 Vin. So basically your gain would be minus GM1 into 1 by GM2 parallel with R0 2 parallel with R0 1 parallel with R0 3. These kind of questions are considered to be the toughest question of GATE examination. I will tell you, these kind of questions are considered to be toughest question as per the students. But once you have studied the MOSFET amplifier, now I hope you are comfortable with these kind of questions. Within second you will be able to solve because there will be options given. Okay, you could see GM Vin current will be V0 to ground R0 1, R0 3, 1 by GM2 parallel with R0 3. Simply you will take the option. Within 30 seconds you will be able to answer. So yeah, these kind of depth we are going to cover for analog electronics, and even in the network analysis we have covered, even in the control systems we have covered. So these three subjects combined of 30 marks, and no matter how tough problem they set in the examination, kitna bhi tough paper aa jaye, you are going to score the complete marks. Well and good. Okay, let's not talk much about the examination, but let's solve the next question. This is also one of the finest question. Try to solve it on your own. I'm not telling from where I am getting these questions from. Okay, you can DM me, you can personally DM me, then I can tell you where I am getting these questions from. Also, I am changing the data. It's not that I am blindly putting the data, but I am changing the data as well. Okay, yeah. So these transistors are biased such that all transistors are working in saturation region. So VB1, VB2, VB3 are set such that all transistors are working in saturation region. Now from M0 to M3 are biased with 5 milliampere current. So in M1, M2, M3, M4, sorry, M0, M1, M2, M3, all these four transistors are having the same current, that is 5 milliampere. VT value for all the transistors is 0.4 volt. VT value, threshold voltage value. You need to find the small signal voltage gain, V0 by Vin. This is your V0, this is your V. So let's copy this circuit. So what do I need to find? I need to find the small signal voltage gain. So what I will do the AC analysis. This will be shorted, this will be shorted. This is shorted, this is shorted. This 0.6 will be gone. 0.6 will be gone because that was the DC supply. And this 0.8 will be gone because that is the DC output. So only V0 I am having. Well and good. Now if here it should be mentioned that lambda is equals to 0. I am really sorry that I forgot to mention lambda is equals to 0 here. Lambda is equals to 0. It should be mentioned in the question only. Lambda is equals to 0. So here VSG is gone. So complete M4 will be replaced with the open circuit. Complete M4 will be a open circuit. Well and good. Are you agreeing to my point? VSG is gone. You would have replaced M4 with R0 4. But there is no R0 4. R0 4 is also infinity. So complete M4 will be gone. There is no use of M4 now. Okay. What do I know? That here my current would be GM naught V in. Well and good. Now this same current would be flowing through M2 because there is no other path. So the same current will be flowing through M2. Now what will happen to this current? This current has to flow like this, right? Because there is no ground. If there was ground, then you can say that some current can go into ground, some current can flow from here. But there is no ground. So the other path is simply to flow like this or to flow like this. So here in the upward direction you can see that there is GMV in current. Say yes or no. GM not V in. GM not V in. This GM not V in current is flowing in the complete loop. What is the current in M1? What is the current in M1? What is VGS here? This is V0. What is the current in M1? That is GM1 V0. Say yes or no. The current in M1 is GM1 V0. Are you getting this point? This was the circuit. I could see that there is one current flowing in the complete loop because there is no other path. So that current is GM1, GM0 V in. I also got to know that in terms of V0, what is that current? GM1 V0. So here this GM1 V in current will be flowing in this direction as well. So in the complete loop, this is GM0 V in current is flowing, not GM1 V in, GM0 V in. So in the complete loop, this GM0 V in current is flowing, and in the downward direction, GM1 V0 current is flowing. So what did you get to know? That this GM0 V in is equals to minus of GM1 V0. Say yes or no. This current GM1 V0 is equals to minus of GM0 V in. Whether you write down this current or this current, both are same current only. So both currents are equal. So what is your V0 by V in? V0 by V in is minus GM0 divided by GM1. V0 by V in is minus GM0 divided by GM1. Now tell me, if both are equal, GM0 and GM1, we have to find the values of GM0 and GM1 as well. So what will be the scene? The DC voltages are given, right? Also, what is given? That all are having the same current, 5 milliampere. All are having the same current. What is the formula of GM? GM is, I told you, 2IDC upon capital VGS minus VT. All are DC parameter. IDC is DC, VGS is DC, VT is DC. All are DC parameter. What will be GM naught? 2IDC, the current that is flowing in M naught, divided by VGS of M naught minus VT. VT is same. Even the current is same for everything. So 2 into ID. What is the current flowing in M naught? That is 5 milliampere. 5 milliampere. What is VGS M naught? VGS. VGS of M naught. What is that? 0.6. Large signal value. Large signal value. That is 0.6. VGS of M naught. That is 0.6 minus 0, 0.6. And what is VT? That is 0.4. Right? That is 0.4. So it would be 10 by 0.2. So 50 millisiemens. So 10 milli divided by 0.2. 100 by 2, 50 millisiemens. So this is GM naught. What about GM1? GM1 would be 2ID. What is ID? What is ID? Tell me. Just tell me. ID for M1. Is it 5 milliampere or minus 5 milliampere? Tell me. If your answer is minus 5 milliampere, then it's absolutely wrong. What is this? This is DC current. So here you are saying that I am having 5 milliampere current. Can DC current flow in this direction? No. What we did here, it was the AC analysis. But in the DC analysis, what would have been happening? In the DC analysis, there will be this 5 milliampere current. Now this 5 milliampere current, 5 milliampere current is flowing in this direction. 5 milliampere current is flowing in this direction. 5 plus 5, 10 milliampere current would have been flowing from here. So in DC analysis, this will not be open circuited. M4 will not be open circuited in DC analysis. VB1 is there, VB2 is there. So it makes sure that it will be having some current. M2 will also be having some current. M1, M0 will also be having some current. So M0 and M2 are having 5 milliampere current. M3 and M1 are having 5 milliampere current, both from source to in this case source to drain, and in this case from drain to source. Are you getting this point? So we have to set that DC bias such that all transistors are on and are in working in saturation region. So it is made sure. So it's not that minus 5 milliampere current is flowing. That we did in the small signal analysis, because small signal does not determine the region of operation of a MOS. I told you, because the signal is very small, so it doesn't determine the region of operation, right? Okay, so there is 5 milliampere current here and 5 milliampere current here. Oh, we can keep it like this, right? Yeah, I would just remove it. Both are having the 5 milliampere current. Five milliampere current. What will be VSG or VGS? Sorry, what will be VGS? This M1 is an NMOS. So what will be VGS? VGS would be 0.8. This is the 0.8. That would be VGS, because gate is at 0.8, source is at 0. 0.8 minus 0.4. That will 10 by 0.4, 100 by 4, 25 millisiemens. 25 millisiemens. So what would be the answer? What I can do, I can shift all this upward. So what will be the answer? V0 by V in minus 50 millisiemens divided by 25 millisiemens. That would be minus 2 volt per volt. Say yes or no. Understood? Current here, both are equal. My gain is minus GM0 by GM1. My target is to find GM0 and GM1. I got to know both are having the same DC current, 2 IDC upon VGS. What is the VGS here? That was 0.6 DC. 0.6 minus VT 0.4. Here, what is VGS? 0.8 minus 0.4. That's it. Found the value and go to the gain. Well and good. Let's move on to the next question. You have to find the small signal voltage gain. Lambda is not equal to 0. M1, M2 both are the different transistor. Can you do it? Very easily we can do it. We will draw the small signal model. So this ID will be open circuited. So there will be no, this is the DC current, this will be open circuited. So there will be no use of VDD as well. So simply, how will our circuit look like? This is V in. There is certainly R01 as well. Then there is this other MOS. It is having V in here, and certainly there is R02 as well. This is V0. So from V0, at V0 we can apply nodal analysis. We need to write the current in this branch, in this branch, in this branch, and in this branch. What is the current in this branch? That is GM1 V in. Yes or no? What is the current in this branch? V0 by R01. What is the current in this branch? GM2 into V in minus, sorry, GM2 V0 minus V in. GM2 V0 minus V in, because we are going from V0 to V in. So GM2 V0 minus V in. So better I should write the current here like this. What is the current here? GM2 V0 minus V in. That's it. So what is the scene? GM1 V in plus V0 by R01 plus GM2 V0 minus V in plus V0 by R02 is equals to 0. Right? So I will put V in one side and V0 one side. So V0 by R01 plus GM2 V0 plus V0 by R02 is equals to GM2 V in minus GM1 V in. right? We are taking it on this side. So V naught by, tell me, what will be the resistance? On the next page I will be writing. What will be the resistance? V naught by R naught 1 parallel with R naught 2 parallel with 1 by GM2. Remember it? I told you V by R1 plus V by R2. What you can write? V by R1 parallel R2. Right? So similar thing we are doing here. So that this is V naught by R naught 1, V naught by 1 by GM2 plus V naught by R naught 2. So what we will write? V naught by R naught 1 parallel with R naught 2 parallel with 1 by GM2, right? 1 by GM2 is equals to GM2 minus GM1 into Vin. So what will be your V naught by Vin? That would be GM2 minus GM1 into R naught 1 parallel with R naught 2 parallel with 1 by GM2. That's it. Now I will give you one more task. Solve this question by GMR out method. Solve this question by GMR out method. Can you do it? Solving it with GMR out method. Method 2. GMR out method. It will be easier with that. Also, if you apply GMR out method, you also write down the output impedance. So that is also a good practice, right? It's a good practice if you are writing the output impedance as well. So first you need to find GM. So for GM, what you will do? Short circuit the output. This is your V. You are not going to do anything with V. Then again this is your V, and this is R naught 2. What you are going to do? You are going to short circuit the output. Output is shorted and the current should be going into the output. This is your I out. So I out by V in. This is your target. I out by V in. So what is the scene? What is the current here? GM1 V in. What is the current here? This is 0. This is V in. So you are going from V in to 0. Better I should write. You can go from 0 to V in as well. So what you would write? GM2 into 0 minus V in the downward direction. So in the upward direction, we are having GM2 V in. GM2 V in. Will this R01 have some current? No, because this is also 0. This is also 0. Between 0, 0 it is. So it will not have any current. Will this R02 have any current? No, because this is 0. This is also 0. So no current. I can simply apply nodal here. What is the outward current? Outward current is GM1 V in. What is also outward current? This I out is also outward current. Is equals to inward current. What is that inward current? Inward current is GM2 V in. GM2 V in. So here you can see that capital GM, that is I out by V in, that is equals to GM2 minus GM1, right? So this is capital GM here, GM2 minus GM1. What about R0? चल रहा है ना भाई रिकॉर्डिंग? मेरे को बहुत डर लगता है रिकॉर्डिंग बीच में ना रुक जाए यार और मैं बोलता रह जाऊँ. बहुत बार होता है मेरे साथ ऐसा. It happens a lot of times that I just keep on speaking and I forgot to turn on the recording. This is very frustrating actually. So what about R out? What about R out? चलो मैं बना ही लेता हूँ. You can skip this part when I'm making the R out. If you have solved this question by GMR out method, you can skip the complete solution as well. Just save your time. This is R not 1. V in is shorted because you are finding R out. Here also Vin will be shorted. This is R naught 2. From here you are seeing the R out. So tell me, this is your V naught and this is your I naught. So what you will say? From V naught to ground I see R naught 2. From V naught to ground I see R naught 1. This VGS is completely gone here. VGS completely gone. So there is 0 ampere current. And what you will say here? From V naught to ground, from V naught to source, I see 1 by GM2. Right? Here VGS is not 0. Here VSG is not 0. VSG is V naught here. So what is the current here? Basically GM V naught. So either you can write the equations or you can directly see that from V naught to ground I see 1 by GM2. Since this is M2, so you can say that from V naught to ground I see 1 by GM2, and from V naught to ground I see R naught 2 as well. Right? So simply you can say that my R out would be, I see R naught 1, I see R naught 2, and I see 1 by GM2. Well and good. Okay. This is my R out. Well and good. So what will be my gain? Gain would be GM R out. So GM is GM2 minus GM1 R naught 1 parallel with R naught 2 parallel with 1 by GM2. This is the gain. Well and good. Let's move on to the next one. What is Rx? Tell me. Within second you need to tell me. 1 by GM parallel with R naught. That's it. Why so? Because this VDD will be shorted. I told you one thing. From source to gate I see 1 by GM, and from source to drain I see R naught. And if both are shorted, that means both are grounded. So I can say that from this node to ground, I see 1 by GM, and from this node to ground I see R naught. That's it. That's the answer. Now this will be used in solving the next question. So solve this question. Okay, in within 50 minutes we are able to solve all the problems. So I guess I can add more problems in the assignment. I will try to add more problems. So yeah, this will be a shorter lecture, so I will add more problems if I have those, or otherwise we can see it in some other assignment. So yeah, this will be the last question of this assignment. We will make another assignment, all because there are a lot of more problems. So we'll make other assignments as well, and there we can solve more problems. Okay, so no worries about the MOSFET amplifier. We will solve nearly 100 problems. Already we have seen so many problems. We will see more problems. No worries about that. Try writing the gain of this one. If you are able to write the gain of this one, you are done with MOSFET amplifier. Okay, you can do every single question of MOSFET amplifier in the examination. So try writing the gain. Some people will do it by GM R out method. They can do it by GM R out method as well. They need to write GM, they need to write R out. So what will be the GM? Directly we can see. What will be the GM? All are the same transistor. So capital GM would be equals to GM only. Why so? Because if you short circuit the output, then the current that is flowing here is GMV. Now since there are R out also available, but the current will go into the short circuit path only. Say yes or no? Look, there are some other resistances available also, but there is short circuit path, no? So the current will be going through the short circuit path only. So let's not solve with the GMR out method. You can do it on your own. And the next task would be to find the R out. So this is the scene. You need to find the R out. So I know one thing, that there will be GMV in current here. This is what I know. They have not mentioned about lambda. So here lambda is not equals to 0. So there will be this GMV in current that I know. Now from where this current would be flowing? This current would be flowing from this much of resistance. Say yes or no? And also there is one more resistance, that is R naught, this R naught, right? So let's make a small signal model, then we can understand it better. You just need to find the small signal voltage gain, nothing else. I will just copy it and paste it on next page. This VB is shorted, VDD is shorted. Let's forget this M and N. Let's make this V naught here. So here I know one thing, between drain and source I have R naught. Between these two also I am having R naught. And between here also I am having R naught. Now I can replace this upper one because there is no small signal input, nothing is there. Everything is shorted. So I can replace this upper one, this much of transistor, by simple one resistance. What will be that resistance? Tell me. What will be that resistance? If you see from here, what do you say? Don't think that I remember something. No, no, no. If gate is shorted, that means I remember something. But that happens if there is some resistance here. You remember the formula for this one, right? Remember the formula for this one. Here, what is the scene? What you can say? From this node to ground, I see 1 by GM. And from this node to ground, I see R naught. Say yes or no. From this node to ground, I see 1 by GM. From this node to ground, I see R naught. Here, why you cannot say this? This is RD, let's say. Yeah. So what you can say here? From this node to ground, I see 1 by GM. But can you say from this node to ground, I see R naught? No. So that's why we remember the formula. But here you can directly say from this node to ground I see 1 by GM, from this node to ground I see R naught. So simply this resistor, this much of part can be replaced by 1 by GM parallel with R naught. That's it. So the equivalent is 1 by GM parallel with R naught. This is grounded. And okay. Now tell me, what do you see from here? What is the equivalent of this much of circuit? Let's use a different color of pen. What is the equivalent of this much of circuit? What did I tell you? From source to gate, I see 1 by GM. From source to gate, I see 1 by GM2, you can say. From source to drain, I see R02. But gate and drain are shorted. So both will come in parallel. Say yes or no. Are you able to understand this? This is the same as this question. But the different thing is there. That is here VDD. So this was shorted. So you could directly see that from V node to, from this node to ground, from this node to ground. But since this is not shorted, sorry, these are shorted but not to the ground. But here we are writing the impedance of this much part. Are you getting this point? So here what you can say? From source to gate I see 1 by GM, and from source to drain I see R02. But since drain and gate are shorted, so what I can say? I can say that from source to drain I see 1 by GM. Because from source to gate I see 1 by GM and gate is shorted to drain. So I can say that from source to drain I see 1 by GM and from source to drain I see R0. So this total impedance would be 1 by GM2 parallel with R02. Say yes or no. Did you understand this concept? So just if you see this much of configuration. Okay, ये erase हो जाएगा यार. Sorry. Yeah. So just as you see this much of configuration, what you can say? 1 by GM2 parallel with R02. Say yes or no. So let's make the below circuit. This is V in, this is V out, this is R0. Although they are the same only, there is no R0 too, because I told that all transistors are same. So what you can say, from here to here I see 1 by GM, from here to here I see R0. So this particular will also be replaced with, this particular configuration will also be replaced with 1 by Gm parallel with R naught. Now 1 by Gm parallel with R naught in series with 1 by Gm parallel with R naught. So from here, what do you see? It is grounded. 1 by Gm parallel with R naught. This is grounded. This is 1 by Gm parallel with R naught. This is also 1 by Gm parallel with R naught. From here you can see that both are coming in series, so you can replace it with one resistance only, that would be 2 into 1 by Gm parallel with R naught. Now it will be a very simple question for you, just a cakewalk. Why so? Because here you can see that from V0 to ground you see R0, from V0 to ground you see 2 into 1 by Gm parallel with R0. Say yes or no. From V0 to ground you see R0, from V0 to ground you see 2 into 1 by Gm parallel with R0. So let's see it in the next page. So our final circuit is something like this. From V0 to ground, what do we see? V0 to ground we see only one single resistance, that is R0 parallel with 2 into R0 parallel with 1 by Gm. Or you can write R0 parallel with 2R0 parallel with 2 by Gm. Now this GMV in current is flowing like this. So simply the gain would be minus Gm into 2 by Gm parallel with 2R0 in parallel R0, 2R0 parallel R0, that would be 2R0 by 3. You can see the parallel combination of this, 2R0 into R0 upon 3R0. So this will be 2R0 by 3. This will be 2R0 by 3. This is the final answer. You could solve it with the GM R out method as well. What will be the R out? This will be the R out. This will be the R out. And what will be GM? This will be the GM. Minus Gm would be the Gm and this would be the R out. I have also told you how to find the R out, because just V in will be shorted, so this will be open circuited. So from V0 to ground you could see this much of resistance. So this is the R out only. So what did we do? We saw the circuit. Okay. Here there is supply. So we cannot do anything with this transistor. So we have to replace all these transistors with the resistance. We will try to do that. From here I saw, from this to ground I see 1 by Gm, from this to ground I see R0. I replaced it with the resistance. From here I saw, I can see 1 by Gm parallel with R0 between two common terminals. So from here to ground 1 by Gm, from here to ground R0. So this is also replaced with 1 by Gm parallel with R0. Both come in series, so both will be one resistance, 2 into 1 by Gm parallel with R0. So from V0 to ground I see 2 into 1 by Gm parallel with R0. From V0 to ground I see R0. This is my final resistance. Now this is my V0 by Vin, that is minus Gm into 2 by Gm parallel with 2R0 by 3. That's it. So this is the assignment 7 that is completed. Now we will see assignment 8. There we will see only 3 questions, but those 3 questions are very conceptual and very calculative as well. There you will need to do the calculation. Now in this particular assignment, did we need to do much of calculation? Look, there is no calculation in this question. No mathematical calculation, no arithmetic is there, right? There are no numbers are there, right? Here also no mathematical calculation, arithmetic calculation is not there. In the next lecture you have to do the arithmetic calculation, so be ready with that and go with the clear mindset that next assignment you will be solving on your own. But that is not really easy, that will be more difficult than this. Okay, so I am preparing you for the worst. Once you see the gate questions now, you will see what kind of easy question they have asked. You will be able to solve the gate question within seconds. So that much you have prepared. So let's solve the next assignment. That will be very conceptual. Your concepts will be much stronger after that assignment. Okay, so let's meet in the next lecture. Thank you. Hi everyone. So in this video we are going to study about Cascode. First we will study about Cascode current source, then we will study about Cascode amplifier, and then we will see Cascode amplifier with Cascode current source. So this we are going to see, but let's study one by one, not directly jumping onto the topic. So first we will study current source. So what is a current source? You might have studied in basic network analysis. So what is the current source? Current source provide a constant current irrespective of the voltage across it. So that is an ideal current source. But every current source has some internal resistance. So let's just assume this is our current source which is having some internal resistance that I am calling is R out. R out. So current source is having its resistance. This could be anything. This supply could be VDD. So current source is having its resistance. Now this is the load. This is the load resistance. RL is the load. So in load, how much current is going? Let's assume this is some I dash current. So one thing I certainly know that I dash is less than I. Say yes or no. I dash will certainly be less than I. Why so? Because this R out will eat up some current. This R out will eat up some current. Right? Tell me one thing. If R out is infinity, if R out is tending to infinity, or if R out is infinity, then what will happen? This I dash will be equals to nearly equals to I. Or I can say this I dash will also be tending to I. Right? So more the R out, better the current source. More the R out, better the current source. If R out is high, that means you will have more current in the load. Your target is to get the current in the load, right? Not in this R out. You are collecting your final output here. You are collecting your final current here. So your target is to get the more current in the load. So more R out, better current source, right? So as much R out you are having, better the current source you will be having. So if you are making a current source, you should make sure that it has maximum output impedance. If you are making a current source from a device, what devices we have studied? We have studied diode, we have studied MOSFET. Now we are going to make a current source using some device. What that device will be, that I will tell you. So we have to make sure that its output impedance is high. That's it. So what we have studied? We have studied MOSFET. So we can make the current source using MOSFET. So making a current source from MOS. This is the characteristics of MOS, right? ID versus VDS. In which region it should be working as a current source? Tell me. What is the property of current source? It should provide a constant current. Is the current constant here? No. If VDS changes, the current is changing, current is increasing. Here the current is nearly constant, right? In this region the current is nearly constant. That means when you are using the MOS as a current source, it should be biased in saturation region. So what is the point? For using MOS as a current source, it should be biased in saturation region. This is the saturation region. Now I have made these characteristics for three different MOS. For three different MOS. For one of the MOS, this is the scene. In saturation region, it is going like this. For the next MOS, it is going like this. And for the next MOS, it is going like this. So which one is the best? Tell me. Which MOS is the best current source? Let's call this MOS as M1, this MOS as M2, and this MOS as M3. So tell me which MOS is the best current source? Which MOS will act as best current source? M1. Why so? Because it has the highest output impedance. R01 is greater than R02 is greater than R03. R01 is nearly infinity because this slope is 0. If del ID by del VDS is 0, that means what is R out? 1 upon del ID by del VDS. So that would be nearly infinity. So ID by VDS, that is nearly equals to 0. So R out is the highest. So in M1, R out is highest. M2, R out is lower than R01. And in M3, R out is lower than R01 and R02. So this is the best R out. That means highest R out. That means this is the best current source. Best current source. So M1 being the best current source. So what did you understand? If you need a MOSFET as a current source, you need to bias it in saturation region. Also, better the R out, better the current source. More the R out, better the current source. If you are having more R out, that means your current source will be better. So here M1 is the best current source. This is what we have understood till now. So if we are making a current source, you can use a MOS. So this is what we are going to write. You are making a current source, you can use a MOS. What is this VN? VN is a node. And this is a ground. So you are making a current source using MOS. So this is a VN. Between VN and ground, we need a current source. So I will use a MOSFET. This potential will be VN. This potential will be some VGG. We can give a supply from our own side. It would be some VGG, and this is the ground. What is the output impedance? Small signal output impedance looking from here. Tell me. This VGG will be grounded. VGS is gone. So only it sees R0. Say yes or no. What did I say? Small signal output impedance we are saying. So this will be shorted. So VGS will be gone. This MOS will be replaced with open circuit, but it is having some R0 here. So final output impedance is R0. Say yes or no, right? Now, why did I use NMOS? Why did not I use PMOS? Let's check what if I use a PMOS. So this will be my VN. I will be using a PMOS. This will be some supply VGG, right? If I use a PMOS, tell me what will be the impedance looking from here? If I use a PMOS from VN to ground, if I use a PMOS, what will be the impedance looking from here? What will happen? This VGG will be shorted. Then from VN to ground, you see 1 by GM. From VN to ground, you see R0. Here VSG is not gone. Here VSG was gone. So complete MOS was replaced with open circuit and R0 only you could see. But here what is the output impedance? 1 by GM parallel with R0, which is not greater than R0. So if you are getting a current out of a node, if you need a current source where the current is getting out of the node and going into the ground, you will use a NMOS, not PMOS. Because if you are using PMOS, then if you look from here, your impedance is 1 by GM parallel with R0, not R0. And you need very high impedance, not 1 by GM parallel with R0. 1 by GM parallel with R0 is nearly equals to 1 by GM only, which is not that high. Let's just assume 1 by GM is some 100 ohm and R0 will be some 100 mega ohm. So what will be the equivalent impedance? That would be nearly 100 ohm only, right? So this is not what you want. You want a higher output impedance. Here you are getting the output impedance as R0 only, right? So you don't use a PMOS. So when you are, if you are going from a node to ground, that means you will use NMOS, not PMOS. Now, if you are going from VDD to VN, then we will use PMOS. Because this is your VDD. Yeah, one more thing. It's not that this will not be working as a current source. Yeah, it will work as a current source. And in some circuit, you will see they use PMOS as well. But this is desirable. What I am saying, it's not that it will not work as a current source. It will also work as a current source, but very weak current source because it is having 1 by GM parallel with R0. So it's not that you cannot use it. You can certainly use it. But generally, from VN to ground, you use NMOS, and from VDD to VN, you use PMOS. You don't need to mug it up. You don't need to mug it up. When you draw a circuit, it will directly come to you. Okay, I cannot use PMOS here because this is the impedance. I cannot use NMOS here. This is the impedance. So no need to mug it up. And once we see further circuit, it will come to you all, by its own. So no need to mug it up. This VGG supply we can give, and this is the VN. So you will see the impedance from a node, not from here, because VDD will be shorted. If you do the small signal analysis, this VDD will be shorted, this VGG will be shorted. So this will be shorted, this will also be shorted. You need to see the impedance from here. So VSG is gone. That means this MOS will be replaced with open circuit. So from VN to ground, you only see R0. That's it. VDD is gone, VGG is gone. So VSG is gone. If VSG is gone, that means zero current. So MOS is replaced with open circuit. So from VN to ground, you see only R0. So what is the impedance you see? That is R out. From here, the impedance is R out. What if I had used NMOS? So what I would have done? This is my VTD. I would have used the NMOS. This would have been my VN. And this is VGG, whatever it is. So what would be the impedance looking from here? That would be from VN to ground I see 1 by GM. From VN to ground I see parallel with R0. So impedance would have been 1 by GM parallel with R0, and this is not desirable for me. So you have made a current source using MOS. So what I will write, from node to ground, if you are going from node to ground, that means you will use NMOS. If you are going from supply to node, you will use Pmos. If you are starting from node, that means NMOS. Node NMOS. If I am starting from a node and I am going towards ground, I will use NMOS. If I am starting from supply to node, that means I will use Pmos. Where the supply will be? Supply will be at top, because we have seen a lot of circuits where always VDD is here. VDD will be at top. Supply will be at top, right? So supply will be at the top. So if you are going from top to a node, you will use Pmos. How you can remember? P, top. Last word is P. So if you are going from top to some node, that means you are going to use Pmos. Supply equals to top, top means P. Last word is P. So I am using Pmos. That's how you can remember, just a method to remember. Otherwise, you will certainly be habitual of making the current source by using NMOS and Pmos. Once we end the lecture, at the end of the lecture, you will be very comfortable with making the current source and everything. So this is what we have made. Now the R out we are getting is R0, right? The R out we are getting is R0. What if I get a higher output? I will try to make a higher output. I want a higher output impedance. My output impedance is R0. I want a higher output impedance. So what do I need? What if I need a higher output impedance? So try thinking of the circuit. What that circuit will be? Tell me. Do you remember any formula of impedance? Any formula? Do you remember any formula of impedance? Yeah, we remember. R0 plus RS plus GM R0 RS. Is that impedance higher than R0? Yeah. We remember this formula. And what is that formula? If you are going from drain to source and your gate is common, if you are going from drain to source and your gate is common, that means this will be the impedance you will be getting. So simply make that circuit and you can use that as a current source. That's it. If you are going from drain to source, that means from here, from this node, you will see R out. That would be R0 plus RS plus GM R0 RS, which will nearly be equals to GM R0 RS. Say yes or no. So if you are going from a node to ground, that means you are going to use NMOS, node to ground. Now if you are going from a node to, if you are going from a supply to node, that means you have to use a Pmos. So basically this circuit will be replaced by something like this. A current source, a DC current source from a node to ground, and that is having an output impedance, that is this R out, which is nearly equals to GM R0 RS. Here, what do you see? What is the impedance here? You are going from drain to source. If you are going from drain to source, that means you need only one step behind. So it would be R0 plus RS plus GM R0 RS, which will nearly be equals to Gm R naught Rs only. So what do you see here? From VDD to a particular node, that is Vn. This is your VDD to a particular node, and in between you are having a resistance. That resistance is Gm R naught Rs. So this is my current source. Okay, so this is what I have made. Now what if this is my output impedance? What is my output impedance? Nearly that is equals to Gm R naught Rs. This is a very high value. Now this Rs is depending on you, right? You can connect this R naught. Sorry, you can connect this Rs. This Rs is depending on you. What if I make it very high? Rs should be very high. How I can make it very high? Tell me. Rs is the impedance looking from here, right? Rs is the impedance looking from here. So I need to make an impedance which is very high if I see from this output. How can I make it? This, and this. VB. What will be the impedance from here? That will be R naught. Right? Now don't say, sir, connect one more Rs here. So impedance will be more higher. But we don't want to use this much of elements. Okay, we don't. If I use another in place of Rs, if I use another this circuitry, my impedance will be more higher. But we don't want to use like that. If I keep on adding up, my impedance will be very higher. But we don't want to use that much of circuitry. Minimum circuitry also we need to use. If we use that much of element, then first thing is that power consumption will be more, and second thing, the device will be costly. The chip will be costly. But you don't want to make or design a costly chip. So simply you are replacing your Rs with this MOS. That's it. So from here, what will be the impedance? If you look from here, what will be the impedance? This VBB will be shorted. So this VGS is gone. So only impedance is R naught. So you have replaced your Rs with R naught. Say yes or no. Right? So this is what we are going to do. We are keeping this as it is. This also as it is. We will just replace this Rs. We will replace this Rs by using a MOS, right? And this gives rise to our cascode current source. So what we are going to make from VDD to ground, first we are going to make, this is our VDD. From VDD to ground we are going to make a current source. Sorry, not from VDD to ground, from a node to ground, sorry, not VDD to ground, from a node to ground. This will be our some DC supply, bias supply we are saying. So VB1 I am calling it. This is my bias supply. It will be having some R naught here. Let's just forget about R naught. Then we are making this Rs by using a MOS only. So this is the current source. So what will be the impedance looking from here? R out. That would be Gm R naught. Let's call this one as M1, this one as M2. So the impedance would be R01 plus R02 plus Gm R01 R02. That's why I told you to remember this formula, because here you are directly writing it. You are directly writing the impedance, which is nearly equals to Gm R01 and R02. And this is known as cascode current source. This is not cascode amplifier. This is cascode current source. From Vn to ground. From Vn to ground, you have made a current source. That is cascode current source. Are you getting this point? How did I write the impedance? This VB2 will be shorted. So this M2 will be replaced with the R02 only. We have already seen this configuration for output impedance. But at that time I did not tell you what is this. Now here I am telling you this is cascode current source. And what about this M1? This M1 will be made something like this. You just have mugged up one formula R0 plus Rs plus Gm R0 Rs. By using that only you are writing the impedance. From here you are writing the impedance. That would be R01 plus R02 plus Gm R01 into R02. That's it. Well and good. Directly you are writing the formula. So this is using NMOS. Now task for you is make the current source from VDD to some supply. Sorry, from supply to some node. From VDD to VN. Make the current source using Pmos. Because if you are going from top to some node, you have to use Pmos. Top to some node. So this was the first one. This is the Cascode current source. Now you are going from top to some node. This is your VDD. Both bias we can give VB1 and VB2. And this is the node Vn. And from here you need to see the output impedance. Tell me what will be the output impedance. What will happen to this? Let's call this as M2, this as M1. What will happen to M2? VDD will be shorted, VB will be shorted. So VSG is gone. So M2 will be replaced with R02. Now M1 and in M1 and in degeneration there is R02. Degeneration means this will be the circuit. VB2 will also be shorted. So this will be R02. So doesn't it look like common source amplifier with degeneration? Isn't it common source amplifier with degeneration? Common source is common source amplifier with degeneration. So the resistance would be Gm R01 R02. You are going from drain to source, that means you need only one step, Gm R01 R02. That's it. So our output impedance is R01 plus R02 plus Gm R01 R02, which is nearly equals to Gm R01 and R02. So this we have studied. We have studied the cascode current source. So this is the cascode current source, right, which is having a very higher output impedance. So this is a great current source which we have made using MOS circuit only. So in the interviews, sometimes they can ask you make a cascode current source, and even in the gate examination, they can make 4 options, and they can ask you to choose which is a cascode current source. They can make it using NMOS as well. They can make it using PMOS as well. So these kind of questions can be asked. So this is the cascode current source. Well and good. Now let's write down the summary. So if you are going from VDD to a node, if you are going from top to a node, that means you will use PMOS. So what are the other ways? First way we saw by using a simple MOSFET. So what was the output impedance here? The output impedance was simply R0. This was your VDD and this was your VN. So the impedance here was R0 only. But then we came to our cascode current source. So in cascode current source, what did we do? Or before going to the cascode current source, what we made? This was the first one. Then we made RS here. This was the RS we were already having, and then we were having a MOS. So if you look from here, the impedance would be, this is VDD. So the impedance would be GM nearly the impedance would be GM R0 RS. Right? This is the second question. What about the third? Not the second question, sorry. Second method. What about the third? We made RS using MOS only. So we made RS using MOS only. This is VB1, VB2. This is your VN. Your R out would be, let's call this one as, what did I call? M2. This one as M2, this one as M1. Here also GM also we need to write. This is GM1, GM1, GM of this, GM1, GM1, GM1. So R out would be GM1, R0 1. This will be replaced with R0 2. Right? So these were the three methods we studied, and this one is given a name, that is cascode current source. Right? Now we will make the same for from Vn to ground, from a particular node to ground. So what was the first one? We simply used a, this is the way, we simply used a NMOS. This is the first one. What about the second? Vn, what was the output impedance here? That was R0 only. Impedance from here is GM R0 RS. Right? So this was the second one. In the third one, we made the RS using MOS only. So what will be the impedance from here? That would be GM1 R01 R02. So till now, whatever that we have studied, that is covered in the last two slide only. So if you just revise this last two slide, you will be able to understand everything. And this is not the complete one. This is the approximate R out. GM1 R01 R02. So in the last two slide, we have seen everything. So our target was to make a cascode current source. Now we have made the current source. What we will do with that? So let's understand by a question. So you have to design a common source amplifier using cascode current source in the load. So in the load you are going to use cascode current source, and then you need to write down the small signal voltage gain. Small signal gain means small signal voltage gain, and you need to make the common source amplifier using both Pmos and NMOS. So let's make CS amplifier using CS amplifier common source amplifier using NMOS with the current source in load. With current source in load. So what is our common source amplifier? Our input is applied at what? Gate. This is the input that is applied at gate. And where do we collect the output? At drain. We collect the output at drain. So in the output you need a current source. Load means in the output. In the output you need a current source. I will make it better. So VDD, in the output I need a current source. And here I am collecting my output. So at the load we used to connect RD, but here we are connecting a current source. So this is the amplifier we have designed. Well and good. Now they are saying that this current source should be made using cascode. So this current source should be cascode current source. Yes or no? So we have to make a cascode current source. So how will you make a cascode current source? You are going from VDD to a particular node. You are not going to ground. You are going to a particular node and you are starting from top. So from top to a particular node, you will use Pmos. So you have to use Pmos. So now this is VDD. I need to use cascode current source. This will be a particular VB1, VB2. Let's call this one as M1, this one as M2, and this one as M3. And here you are collecting your output. So this is this particular configuration that you see here. This is a cascode current source. What is this complete configuration? What is this complete figure? That is common source amplifier with cascode current source in load. Cascode current source in load. That's it. So don't confuse it with cascode amplifier. This is not cascode amplifier. This is common source amplifier with cascode current source in load. Say yes or no. Right? So in the examination, they can give you this particular circuit and they can ask you what kind of amplifier it is. Then people will say this is cascode amplifier. Wrong. This is common source amplifier with cascode current source in the load. What will be its gain? Tell me. You need to replace this much impedance with this much of circuit with some impedance. What will be that impedance? We have seen exactly the same circuit in the previous videos. In the assignment, we have seen exactly the same. So what will happen to M3? M3 will be replaced with the R03. And from here, what is the resistance you see? Nearly it is equals to GM2, R02, R03. Right? And from here I see nearly equals to R01. So what will be my gain? Gain will be minus GM1 in parallel to this resistance. So V0 to ground I see R01. From V0 to ground I see R01. From V0 to ground I see this is R03 and this is some MOS. So this impedance is GM2 R02 R03. So from V0 to ground I see R01 parallel with GM2 R0 to R03. So R01 parallel with GM2 R02 R03. So this is the impedance this is the gain that I am getting. This is the approximate gain because the impedance that we have right, that is approximated. This impedance is approximated. This is not the exact impedance. This is approximated impedance. Which one is the approximated? Here this R01 is not approximated. This is exact. R01 is exact. But this is approximated. Exact is R02 plus R03 plus GM2 R02 R03. Right? Well and good. Okay. So this we have made using NMOS. Now we have to make using PMOS. Current source should be in the load. Current source should be in the load. So what we are going to make now? Common source amplifier using PMOS with current source in load. Current source in load. So there should be common source amplifier. Common source amplifier. Where do you collect your output? At drain. This is the output. In the load there should be current source. That's it. Did you understand it? Common source amplifier is that, and you are collecting your output at drain. So in the load there should be current source. This is the current source we are talking about, right? Now you have to make a current source that should be using cascode configuration. So this should be cascode current source. How you can make it? You are going from a node to ground. Node to ground. Node means NMOS. So you will be using NMOS. So in the next page, I guess I will have to add a page. Now this is the common source amplifier. No need to do anything with that. This is VDD. Now the current source should be made using cascode configuration, using NMOS. This is VB1, this is VB2, and here you are collecting the output. What is the impedance do you see from here? What is the impedance? That is, let's call this one as, M1, this one as M2, and this one as M3. So what is the impedance do you see from here? That is R01. What is the impedance do you see from here? This will be replaced with R03. This MOS will be replaced with R03 because this VB2 is gone. This VB2 is gone, so R03 will be replaced. So this VB1 will be shorted. So the impedance would be GM2 R02 R03. GM2 R02 R03. Right? So what will be the gain? The gain would be from here. What will be the current going in? Did I use the negative sign in the previous gain? Yeah, there is negative sign. So what will be the current going in? This would be the current. GM1 V in. The current would be GM1 V in the upward direction, and that would be flowing through this impedance. That would give the negative gain. This is common source amplifier. We have already seen all these things. We have already seen. So what will be the gain? The gain would be minus GM1 into this impedance. That is R01 parallel with GM2 R02 R03. Say yes or no. Are you able to understand these points? So we have made common source amplifier with current source in load, and we have made the common source amplifier using both Pmos and NMOS. When we were making common source amplifier using NMOS, then the current source in load was using Pmos. This current source that we made, that was made using Pmos, but the amplifier was made using NMOS. So what is this particular configuration? This configuration is common source amplifier that is made using NMOS with cascode current source in load that is made using Pmos. Say yes or no. This common source amplifier is made using NMOS, and this current source is made using Pmos. What about this? This is the figure is common source amplifier with cascode current source in load. Current source in load. So this common source amplifier is made using Pmos, but the current source is made using NMOS. Are you able to connect all these things? I hope you are able to connect all the things. For you as a gate aspirant, what is important? You should be knowing which configuration is known what. This is common source amplifier. Okay. This is cascode current source. So you should be knowing this thing. The second thing is you need to write the gain. You should be able to write the gain. How you can write the gain? I have told you multiple methods. I have told you the GMR out method as well. So if you needed to write the gain using GMR out method, how would you write the gain? Output is shorted. Then the current flowing is GM1 V in. So that current would be flowing like this in upward direction, GM1 V in. So your I out would have been minus GM1 V in. So your GM would have been minus GM. And then output impedance, this is the output impedance. So output impedance also you could have written, right? So this is how you could have write the gain. So for a gate aspirant, it's important that you should be able to write the gain. Also, you should be knowing what configuration is known what. This configuration is known as common source amplifier with cascode current source in load. Because in the examination, they can ask you which one of the four option is that particular configuration. So I hope you are comfortable with all these things till now. In gate field, in gate industry, this is not even taught. Forget about explaining it. This is not even taught because a lot of teachers and even the educators, even the student, I should not say it, but yeah, they are not that much of comfortable with these kind of topics. But here we are dealing it in very good manner. Slowly we are going. We started from one MOS. Now this is the configuration. Now we will make it more complex. Now what is the issue in this one? Tell me. What is the issue? You made this common source amplifier with using cascode current source. What is the gain you are getting? This is the gain you are getting. In the output impedance, what is the seen? R01 is parallel to GM2, R02, R03. Right? R01 is parallel to GM2, R02, R03. What will be the equivalent of this? This is very high, right? And this is not that much high. This is high, but this is very high. So what will be the equivalent? R01 only. So what will be the gain? The equivalent gain you are getting is minus GM1 R01. Is that high? Is that pretty high? No, this is not that much high, right? Your target would be, now my target is to get a high gain. I have made a current source which is having higher output impedance. So this current source is good. This current source is good. But when I check the gain, it is nearly minus GM1 R01, which is not that much high. But I need a higher gain. What I would do? I need a higher gain than this. And in the next one, here also the gain is nearly minus GM1 R01 only. Now I need a higher gain. So what I would do? I use Cascode amplifier. I will use Cascode amplifier. So we need to build a higher gain amplifier. So what we can do? This is our gain, GM into R out. So keeping GM constant, increase R out. The design we made in the previous problem. So what is our R out in the previous design? That is R01 parallel with GM2, R02, R03. So this is the R out. You need to increase this R out. Increase R out. So you need to increase this R out. So in the previous problem that we made, this was the R out. So keeping the GM constant, I need to increase the output impedance. How I can increase the output impedance? There is a current source in the load. There is this current source in the load. So this is actually very high, right? This impedance is actually very high. The problem is this is low. I need to increase this impedance. What can I do? The first thing that can come to your mind is that, sir, degenerate it. If I degenerate it, sir, degenerate it. Okay. So, sir, if you degenerate it, what will be the impedance here? Let's call this one as M1 and this will be shorted, whatever it is, because here you are applying V in. So what will be the impedance looking upside? That would be, let's call this as RS. That would be GM1 R01 RS. You are going from drain to source, only you need one step. So GM1 R01 RS. Sir, you have increased your output impedance, but your GM is changed. I told you, keeping the GM constant, your capital GM would be changed. How it will be changed? Where you would apply the input? You would apply the input here. Right? Now the current is GMV in. Tell me, the current is GMV in. In the all the previous questions, your current here was GMV in. Right? Now the current is not GMV in, because this end is not grounded. This end is connected to RS. So this is not what we can do. Right? So what we will do? We will make this RS using MOS only. But we will apply the input here. This is the different thing we are going to do. That's why it is known as cascode amplifier. If I do this, what this will be? This will be common source amplifier with degeneration and cascode current source in load. Say yes or no. What this configuration would be called? And there will be this current source also in the load. So common source amplifier with degeneration and cascode current source in load. But now what I am going to do? I am going to apply my V in here in the RS part. in the RS part, I am going to apply my V in. So what that will do? My current here would be GM V in. So my GM will be constant. And this configuration is known as cascode amplifier. Are you getting this point? So let's just write it down. So I have given you the idea how did I thought of it. But that is not that much of important because no one is going to ask you how did you thought of it. Actually we did not thought of it. The engineers thought. ठीक है, जो लोग बना गए उन्होंने सोचा ऐसा, हम तो बस देख रहे हैं. But what is the criteria? If you keep on thinking the things like that, you will end up designing a very good circuit in the future when you go into the industry. So I am developing that thing in you so that you get comfortable with thinking as well. It's not that you just need to write the gain, etc. You should be thinking how we are getting this much of high gain. So now I will come up with cascode amplifier. Okay, so this is my cascode amplifier. So I am coming up with cascode amplifier. So I told you one thing. I will make something like degeneration only. Okay, so let's make it like using NMOS. We will make the cascode amplifier using NMOS. So in my NMOS, what do happen? There will be a current source that would be coming here. This would be some ID. This would be your output. Where will I apply my input? Here I will apply my input. And this will be some bias. Are you getting this point? So what will be the output impedance here? Since this is a constant current source, the output impedance is infinity. So what is the output impedance here? Looking here, let's call this one as M1, this one as M2. So what is the output impedance? Tell me. Approximate impedance you need to tell me. That would be, this will be shorted, this will also be shorted. We are writing output impedance. You are writing output impedance. So if you are writing the output impedance, this will be shorted, this will also be shorted. So if V in is shorted, then this MOS M1 will be replaced with R01. And what will be the scene then? This is M2, this is replaced with R01, this VB is shorted, and this is R02. So from here, what do you see? That is GM2, R02, R01, right? You are going from drain to source. You need only one step. GM2, R02, R01. So the impedance would be nearly GM2, R02, R01, right? And what will be capital GM? For capital GM, what you will do? You will short circuit the output. So what is the current flowing here? That is GMV in. And you need to find out this I out current. So I out is equals to GMV in minus GMV in. I out is equals to the same current will be flowing. That would be minus GM1 V in. It should be approximated. Why so? Because I am considering that R01 and R02 are very high. If I am considering R01 and R02 are very high, then only this GMV in current would be equals to I out. We have seen this in assignment. In previous assignment, we have seen this. If I am considering R01 and R02 are very high, then only this GMV in current will be flowing directly in the output. Otherwise, the R02 and R01 can eat up some current. But this is not happening here, right? So my capital GM is approximately equals to minus GM1. So what is my gain now? That is, here I can write down my gain. That is GM R out, so it would be minus GM1, GM2, R02, R01. So this is the gain I am getting, which is very high. Although we have seen this gain in previous videos in the assignment, but there I did not tell you which configuration is known what. So here I am telling you this particular configuration. This particular configuration is known as cascode amplifier. This is what? Cascode amplifier with the current source in load. Cascode amplifier with current source in load. Now we will make the same thing using what? Using Pmos. So in Pmos, common source amplifier. Common source amplifier. This is the common source amplifier. This supply. Where will I apply my input? Here I will apply my input, not here. If I apply my input here, this will become R02 or whatever it is. We will call this one as M1, this one as M2. So if I apply my V in here, what will become? What will happen? This will become R01. So my GM would be changed. I do not want my GM to be changed. So this is M1, this is M2. Here I will give DC supply VB1, and here there will be current source. And this is where I am collecting my output. I am collecting my output at drain. Right. So this particular configuration is Cascode Cascode amplifier, right? And what will be the gain? Tell me. The gain would be this only. You can write down the gain on your own. Say yes or no. What will be the GM value? The current is GMV in. GM value would be minus GM1. What will be R out? Minus GM1. What will be R out? From here to ground, this is the DC current source. So it will be infinity impedance. And now from here to ground, what is the impedance do you see? What is the impedance do you see? This will be shorted, so this will become R01. So GM2, R02, R01. That's it. GM2, R02. This will become GM2, R02 and R01 then. GM2, R02, R01. That's it. That's the gain we are getting. So this is Cascode amplifier using NMOS. This is Cascode amplifier using Pmos. Now what you can do? You can make this current source using Cascode current source. So now we are going to make Cascode amplifier with Cascode current source in load. Cascode amplifier with Cascode current source in the load. So that will be our last circuitry. This should be Cascode amplifier with Cascode current source in load. So this one we are going to make, this current source we are going to make using the Cascode configuration. So where we are going? We are going from supply from top to some node. That means we need to use Pmos. So Cascode amplifier with Cascode current source in load. So we are making a current source using Pmos. That will go from supply to some particular node. And then we are having a Cascode amplifier. This I can call VB1. This will be VB2. This will be VB3. And here is the output. Say yes or no. Are you agreeing to this point? This is our circuit, and what is this configuration known as? This is a Cascode current source. This is what? This particular configuration is Cascode current source. And what is this? This is Cascode amplifier. Writing कितनी सही होगी ना मेरी? So this is Cascode amplifier. This is Cascode current source. Say yes or no. Are you agreeing to my point? What will be your approximated GM here? Approximated GM. Where is the input? Here is the input. The current would be GMV in. You are shorting the output, right? So approximately it will be GM1. Let's call this one as M1, this one as M2, this one as M3, and this one as M4. So approximately the GM would be GM1 minus GM1. Why it is minus GM1? Output will be shorted. This current you need to write I out. and the current here is GM1 V in. Why approximately? Because there is R01 and R02 as well, which can eat up some current, but we will assume that R01 and R02 are very high, so it is not eating up some current. So GM1 V in would be flowing through output only. So I out would be minus GM1 V in. So capital GM would be minus GM1 only. Well and good. Okay. So GM is GM1. What about R out? Write down the R out on your own. Tell me what will be the R out. See the impedance here. VB3 is shorted, VB2 is shorted. If VB3 is shorted, this M4 will be replaced with R04. VDD is ground. VB3 is shorted, VDD is shorted. So M4 is gone, only R04 will be there because VSG is gone. And what about this? This is the scene, this VB3 is shorted. So what is the impedance from here? GM3, R03, R04. Say yes or no. GM3, R03, R04. The same thing is happening downward. This is shorted, right? This M1 V in is shorted, so VGS is gone. If V in is shorted, VGS is gone. So M1 will be replaced with R01. So what is the impedance downward? This is our V0. So what is the impedance downward? This is M2. So GM2, R02, R01. So what will be the total impedance? From V0 to ground you see this. From V0 to ground you see this. The impedance would be GM2, this is R02. GM2, R02, R01 parallel with GM3, R03, R04. Say yes or no. Well and good. Actually we can keep it here like this. So yeah, this is M3, this is M2. What is our R out? R out we can write down here. This is also approximated because exact one is the bigger formula, that is R03 plus R04 plus GM R03 R04. So which is we are not writing. So this is the R out we are getting. GM3 R03 R04 parallel with GM2 R02 R01. So this is the GM R out value you are getting. So what will be the gain? So this is your gain minus GM approximated, again approximated, minus GM1 GM3 R03 R04 in parallel to GM2 R02 R01. That's it. This is the small signal voltage gain. And what is this figure? This figure was, okay, it is written cascode amplifier with cascode current source in load. So this was the cascode current source and this was the cascode amplifier. This was the cascode amplifier, this was the cascode current source. Now you made the cascode amplifier using NMOS. Now you have to make the cascode amplifier using PMOS. And in the load you will use what? Cascode current source. That will be made using NMOS. Are you getting confused? Look, this is cascode amplifier made using PMOS. If you are listening very carefully, you will not get confused. That is my guarantee. This is cascode amplifier made using PMOS. Cascode amplifier using PMOS. And this is cascode amplifier made using NMOS. Now we are going to make this configuration. Now this current source will be made using cascode configuration. So if you are going from a node to ground, node N, that means you will be using NMOS. So for making this current source, you need to use NMOS. Now this will be as it is, this will be made as it is, and this you need to make using NMOS, and that we have previously made. We have made the current source using NMOS, where here it is. So this configuration will be used. Right? Cascode amplifier using. So this I am making, that is cascode amplifier, and current source will be made later on. This is the cascode amplifier we are making. Where will we apply the input? We will apply the input this side. If I apply the input here, this will be made RS. That will change my GM. How it will change, that we will see. This is my VB1. Now we are making the current source. So this is our cascode current source. This is VB2, VB3. If you take interest, this will be very, very interesting. This complete analog electronics is very interesting. If you take interest and study it in that much of depth. In the examination, you will solve the problems in seconds. And you will say, sir, analog electronics came tougher, but we solved it very quickly. So we are getting a very good rank. Believe me, if you study from prep fusion, you will treat your examination very lightly. Yeah. So enough of self-praise. Let's write down the gain. But before writing down the gain, let's clarify what is what. M1, M2, M3, M4. This is cascode current source. And this is cascode amplifier. What will be GM? Capital GM. That would approximately be equals to minus GM1 only. What is R out? From here, what do you see? From here to here, what do you see? GM2, R02, R01, because this will be replaced with R01 only. So GM2, R02, R01. GM2, R02, R01. Parallel with what will happen to this one? This will be replaced with R04. So that will be GM3, R03, R04. GM3, R03, R04. So what will be the gain? The gain will be minus GM1, GM2, R02, R01 in parallel to GM3, R03, R04. So this is the gain. Say yes or no. Right? So this is the small signal gain. Now we will see what if I had applied this input here. So I will copy this structure. I can copy this structure. So I have written what if. Yeah. मिट जा भाई. Okay. बनाना ही पड़ेगा. So first let's make the current source. This was the current source. These were the DC bias. So this was the current source. VDD. And then this was the amplifier. Okay. So in the cascode amplifier, what we were doing, we were applying the input at this M1. This was M1, M2, M3, M4. Here we were collecting our output. So this was our bias, VB3, VB2, VB1. And here we were applying the input, right? This we were doing. But what if I apply my input here? I apply my input here, and this is the bias. What if I do this? Okay, the main thing to notice here is this. I have applied my input on M2 and this is my bias. What will happen to R out? R out will be same, because when you are calculating the R out, you short circuit the input as well. So R out will be same. This will be replaced with R01 only. So what will be R out? R out, if you look from here, that would be GM3 R out. From upward direction, GM3 R03 R04, right? And what about this? This M1 will be replaced with R01 only. M1 will be replaced with R01. So again here GM2 R02 R01. So this is unchanged. This is same as before. Same as before. But what about GM? That is the task. What about GM? So what you will do for GM? You will short circuit the output. अरे भाई ये क्या कर दिया मैंने? वापस बनाना पड़ेगा. Let me pause the video and make it again. Yeah. So this is how I will find my GM, right? I will short circuit the output. All the DC bias are also shorted. So this will be my I out. I just copied this circuit. The same circuit is there. This is M4. This is M3. This is M2. This is M1. So I just copied this circuit. I am writing my GM. So this V in will be there. All the other bias will be shorted. I need to find the relation between I out and V in. Right? This will be replaced with a particular impedance. That will be GM3, R03, R04. And this M1 will be replaced with the R01 because this is gone, so R01. And this is your V in. Your output is shorted. And this is the I out we are getting. Right? Will there be any current in this impedance R0, GM3, R03, R04? There will be no current here because this is also grounded, this is also grounded. So there is 0 ampere current here. Right? So in conclusion, how your circuit is looking like now for GM, for finding GM. This is your R01. This is your V in. Here, this is your M2. This is the output. This is my I out. How will you find GM now? You need to find the relation between I out and V in. So what you can do, you can assume a V here. So the current here would be GM V in minus V. GM V in minus V. So your I out is equals to negative of GM V in minus V. What also you can write down that my V by R01 is equals to negative of I out. Say yes or no? V by R01. This I out current is flowing this way. I out current is flowing this way. I am assuming what I am assuming that my R02 is very high. This is my GM2. I am assuming my R02 is very high. This R02 is not eating up any current. This is what I am assuming. Because if I take R02 in action, what will happen? This I out will not be equals to minus GM2 V in minus V. Because here there will be R02. So that will also eat up some current. So let's forget about that. We will write down the approximate formula. So I am assuming R02 is very high. So I out is flowing this way. So what will be your V? V will be minus I out R01. Say yes or no? V will be minus I out R01. Just put it here. So I out would be minus GM2 V in and V would be minus I out R01. ठीक है ये let's open it up. So I out is equals to minus GM2 V in plus GM2 R01. Is there something wrong in the calculation? GM2 V in minus V naught. Okay, I out. And this I out is flowing like this. So I out by R01 minus, put the sign there. Yeah, this will be plus. This I was thinking. This will be plus. So here GM2 V in minus GM2 R01 I out. So here I out by V in, that is equals to capital GM, that is equals to minus GM2 upon 1 plus GM2 R01. This will be your capital GM, right? So what will be your gain now? Gain. Now what is happening to GM? Previously what was your GM? Here. Here your GM was GM1. Now your GM has reduced to this much of. Your GM has reduced. Minus GM2 divided by 1 plus GM2 R01. So your GM has reduced. GM is reduced. So your gain will also be reduced. That would be minus GM2 divided by 1 plus GM2 R01. And what was the output impedance? Output impedance was same. GM3 R03 R04 parallel with GM2 R02 R01. So this gain is reduced. Gain is lesser than, gain is reduced. Just I am writing reduced than what? Reduced than cascode amplifier. Reduced than cascode amplifier. So if it is not cascode amplifier, then what amplifier is it? Think about it and tell me. What is the name of this particular configuration? Tell me. If this is not cascode amplifier, then what is the name of this configuration? This is common source amplifier with degeneration that is having cascode current source in load. Say yes or no. This is common source amplifier with degeneration only. Are you getting my point? What is the gain of common source amplifier with degeneration? Minus GMRD upon 1 plus GMRS. Say yes or no. This is the GM for them and this is the output impedance. What is the output impedance? This is the output impedance. What was the GM? Minus GM2 upon 1 plus GM2 R01. GM2 GM upon 1 plus GMRS. GM upon 1 plus GMRS. GM2 upon 1 plus GM2 R01. So this is the GM2 upon 1 plus GM2 R01 and this was the output impedance. Say yes or no. So this was common source amplifier with degeneration with cascode current source in the load. Right? So this is not our cascode amplifier. What is our cascode amplifier? This is the cascode amplifier. This is the cascode amplifier. And that was cascode amplifier with degeneration in the, that was common source amplifier with degeneration in the load. So I will write down one last thing, that is cascode amp versus common source amplifier with degeneration. Common source amp with degeneration, right? I will make a divider. Here I am writing cascode amp. Amplifier I will make using NMOS. Current source you can make using cascode. So I am not making current source here. This is VDD only. Here I am getting output. This is my cascode amp. And if it is cascode, where will I apply my input? Here I will apply my input. Right? This is VB. Right? And here I will be writing common source with degeneration amp using same NMOS. So what I will do, I will just copy this structure. थोड़ा छोटा करना पड़ेगा. I will just copy this structure. I will just interchange this supply and so here there will be this supply, here this will be VB. Let's call this one as M2, this one as M1 and here let's call this one as M1, this one as M2, or let's make the same name only, M2 and M1. So what will be the gain here? What will be the gain? The gain here would be minus GM1, and what is the R out? GM2 R0 2 R0 1. That will be the gain. What will be the gain here? That would be minus GM2 divided by 1 plus GM2 R0 1. Degeneration resistance is R0 1 into what is the output impedance? Output impedance is GM2 R0 2 R0 1. So that will be the gain here. The gain is reduced, right? And same cascode amplifier, cascode amp using Pmos. So this is VDD. This is our V out. Here I am giving the DC supply. If it is cascode, I will be using my V in here. I don't need to write the gain because the gain will be the same only as this. So here I am writing this is M1, this is M2, right? And if I am making common source with degeneration, okay, this was the third one, and this is the fourth one. So I am making common source with degeneration amp using Pmos. What I need to do, I just need to copy this circuit. Just copy it. Okay, again I need to copy this circuit. Just copy it. Just interchange these. Let's call this as ID, this as ID. You can make this ID using cascode current source, right? So here you will be having your V in, here this will be your bias. I hope the complete lecture is clear to you, right? Everything that I have taught here, that is clear. What is cascode current source? What is cascode amplifier? Cascode amplifier with cascode current source. Common source amplifier with degeneration that looks like it is a cascode amplifier, but it is not cascode amplifier. This is cascode amplifier with degeneration. Sorry, this is common source amplifier with degeneration. So in the summary, what is the definition of cascode amplifier? We forgot to write definition of cascode amplifier. Just a simple note. What is cascode amplifier? So sometimes in the interviews, not in like VLSI interviews, but in some PSU interview, they can ask you what is a cascode amplifier. So cascode amplifier is common source amp in series with common gate amp. Say yes or no. This is your cascode. Common source in series with common gate. Common source in series with common gate. But the condition is common source should be either connected to the source. This is here. This is here. This is common source in series with common gate. Is this common source in series with common gate? Is this common source with series in common gate? No. This is common source with degeneration. Can you call this one as common source in series with common gate? Nah. This will be shorted, so this M1 will be replaced with RS. This is not an amplifier. M1 is not working as an amplifier. Only M2 is working as an amplifier. So here this is common source in series with common gate. The gate is common here. This is common source. Common source in series with common gate is known as cascode amplifier. Common source in series with common gate amp. So this is known as cascode amplifier. Sometimes in the written test or in 1 mark question they can ask this question. In the PSU interviews they can also ask this question. Well and good. One more thing I would like to tell you, one last thing. I will give you one intuition here. So here we found out the value of GM like this, minus GM2 upon 1 plus GM2 R01. Okay, well and good. This is also a good method. I can find out the GM value by one more method. What do I know? This is V in. Here I am having V in. From gate to source or from source to gate, I know there is 1 by GM, right? 1 by GM2. And then there is this R01. And this is V in. This is V in. Here is 1 by GM2. Here there is R01. What will be the current here? V in by 1 by GM2 plus R01. So the current here, that is V in by 1 by GM2 plus R01. And this current is equals to minus I out. Say yes or no. From here also, from this equation also, you will get this GM only. GM2 will go ahead up. So GM2 by 1 plus GM2 R01. Are you agreeing to my point? One more intuition. By this also you can write down GM in one step only. This is V in 1 by GM2 R01. So the current downward is V in by 1 plus GM2 plus R01. That is equals to minus of I out. So I out by V in would be equals to GM2 upon 1 plus GM2 R01. Say yes or no. So this is my capital GM, that is minus GM2 upon 1 plus GM2 R01. Right? Well and good. Okay. This was just an intuition. You can write down in your notebook somewhere if you want to write down. Yeah. So sometimes in the interview, if you tell the things like that, interviewer will be impressed a lot of times from you. Right? So if you study from this playlist, I am pretty sure interviewer is going to be impressed from you. That is for sure. So let's meet in the next video. In the next video, we will be studying about current mirror circuit. So now we have made a current source, but that current source has some issues. What is that issue? First, we will see that we have made a current source, right? Cascode current source, but that is having some issue. What is that issue? We will address that, and then how do we eradicate it? We eradicate that using current mirror. So that we will study, and then we will see an assignment. In that assignment, we will study a lot of questions from current mirror circuit. Okay, thank you. Hi everyone. So in the previous video, we saw MOS as a current source. When we are using MOS in the saturation region, it acts as a current source with some output impedance, right? This is what we have seen. Now, what is the issue with the MOSFET when we are using it as a current source? So what is the issue? That we will see. So there will be a current I. If the MOS is acting in a saturation region, there will be a current I. So what that current I would be? That would be mu n Cux W by 2L VGS. What is VGS? That is VB minus VT whole square. How will you make this VB? If you have only one supply, if you have only VDD supply, how will you make this VB? By potential divider, right? By potential divider, you will be making this VB. This is R1, this is R2, and this will be your VB. So VB would be R2 upon R2 plus R1 into VDD. So this will be your VB. So basically your I would have been mu n Cux W by 2L R2 upon R2 plus R1 into VDD minus VT whole square. What do you see here? Now this VT is depending on temperature dependent. This VT threshold voltage, this depends on temperature. This mu n, this is also temperature dependent. This VB voltage, bias voltage, this is supply dependent. Supply dependent. This was temperature dependent. Right? This is also temperature dependent. So what do you observe here? You observe that this VT, mu and VDD, this is supply dependent. So all these are temperature dependent. So this I is not constant. with respect to temperature, with respect to change in the supply, it can change. The thing is, in a chip, let's assume you design a chip and there is a VDD supply. So this supply is also not constant. Let's assume if my supply is 1 volt, sometimes it can change to 1.1 volt and sometimes it can change to 0.9 volt. This you will learn when you go into industry. When you see a chip, the supply can change. So this current will not be constant. So here what we get to know is that this I is not constant. So that is the issue. When you use MOSFET as a current source, this I is not constant. So this is the conclusion. So we actually need a constant current source. And for making that constant current source, we use a circuit that is known as band gap circuit. So for making a current source which is independent of supply and temperature variation, we need to use band gap circuit. Now this band gap circuit is out of the scope of this course. Out of the scope of this course. That means in the GATE exam, it will never be asked. Band gap circuit is not useful for your GATE examination. It is not mentioned in the syllabus. Even in the interview, they do not ask it. If you are someone who is doing M.tech and you have mentioned some project using band gap circuit in your CV, then only they can ask you question on band gap. Otherwise, they are not going to ask you question on band gap reference circuit. So if you have a project mentioned, then you can expect some question. Talking about the placement course, in the end I will teach you band gap reference circuit. But for the GATE aspirants, I am not going to teach band gap reference circuit, band gap circuit. Okay. So you just need to know that by using a band gap circuit, we can get a constant current source which is independent of supply variation and the temperature variation. And that current source is known as golden current source. Golden current source. That is constant current source, basically constant current source. So we get a constant current source from this BGR circuit, from band gap reference circuit, from band gap circuit. So we get a constant current source. Now you have that current source with you. Now you have a constant current source with you. Now using that current source, you have a constant current source, you have a golden current source. I golden, or sometimes we call it I reference. You have that reference current source. Now using that current source, you need to make more current sources. This is your target. And for that we use current mirror circuit. You already have a current source. By using that current source, you need to make more current sources, which is identical to this IREF or this I golden. So from band gap circuit, you will make a constant current source, and by using that current source, you will make copy of those current sources that will be identical to this IREF. So for that we use current mirror circuit. So with the help of golden current source, we will generate other current sources which are identical to the golden current source or reference current source. So basically, you will already have a golden current source. This is the golden current source you are having. By using this current source in a circuit, this is a circuit. This is a particular circuit. This is a particular circuit. By using this current source, you will make copy of other current sources. You will make copy of the current sources. I copy 1, I copy 2, and this, let's call this as I ref. So this I copy 1 will be proportional to I ref. So if I ref is temperature independent, if I ref doesn't change with respect to temperature variation or supply variation, then this I copy will also not change. If this I copy 2 will also not change, because this is also proportional to I ref. So for that we need to use current mirror circuit, but we directly will not use current mirror circuit. what we need to do, we have a golden current source, okay, and from that we need to generate an output current that should be independent of the supply and everything. You have a golden current source. With the help of that, you need to generate a I copy 1 and I copy 2, and that should be independent of supply variation or temperature variation. So we will try making the circuit. First, what we are going to do, we are going to use a resistor. We are going to use a resistor. So what I am going to do, I have a golden current source, or I have a reference current source. I will use a resistor now. What I will do, I will use a resistor R. I am calling this reference current source as I naught. Okay. So I am going to use a resistance R. Now this current is flowing through the resistance R. So what voltage drop it will give here? I naught into R. Now this I naught into R voltage drop will be fed to the MOSFET. Now this voltage drop is fed to the MOSFET, and from there we are generating some current. There will be some other particular circuitry here. Let's not make the circuitry, and we will make sure that this MOS is working in saturation region. MOS in saturation region. Let's call this node as V naught. So adjust V naught such that MOS is working in saturation. So till now what we have studied, we have already generated a constant current source. We are passing it through a resistance R. With the help of this voltage drop we are giving it to a MOS, and now this voltage drop that is here, that is I naught R. Now this voltage drop will generate some current that we can call I copy. So let's check out what is the equation of I copy. What will be the equation of I copy? That would be mu n cox W by 2L. What is your VGS? VGS is I naught R minus VT. Now this current is not depending on the supply. This is your VDD. So this current I copy. This doesn't depend on supply. So if there is variation in supply, still the current will be constant. If there is some variation in the supply, still the current will be constant. Why so? Because this current is not depending on the supply, but this current is depending on mu n and Vt. Both are temperature dependent. Temperature dependent. Both are temperature dependent. So that is the issue here. We try to make a current source, we try to make a copy of this current source which should be independent of the temperature variation. But this is not the independent of the temperature variation, it is depending on the temperature. So this is not a good idea. So what we will do now? We will use diode connected transistor. What we will use? Diode connected transistor. Have you studied about it? Yes. In the common source amplifier, I told you about diode connected transistor. So how does the diode connected transistor look like? This is a diode connected transistor. Okay. So I will make it properly. So what I will do? I will pass the current. I will pass the current which I was having, which is I naught. So I will pass this current from a diode connected transistor. Passing the current from a diode connected transistor that will generate some voltage V. Are you getting this point? And then this voltage V, I will be giving it to some MOS. This voltage V will be fed to some MOS. This I am going to do. So let's find out what is that voltage V. So what is this I naught? This I naught will be flowing here because there will be no current coming here, right? There will be no current coming in this path, and there will be no current here as well. So there is zero current here. So let's find out the voltage V. So what that voltage V would be. So what is I naught? I naught is equal to mu n cox W by 2L. VGS, what is VGS? VGS is V minus VT whole square. So what is your V? V is under root 2L by mu n cox W 12 by mu n CoX W into I naught plus Vt. Well and good. 12 I naught plus Vt. This is V. Now this V is fed to some other MOS that we are going to connect here. This V is fed to some other MOS. There will be some particular circuitry there. Let's not talk about it. So now here there will be I copy, and we have to adjust V naught. By using some circuitry here, we will adjust V naught such that let's call this one as M1. Okay, this one as M2. So this W by L would be of M1. We will replace it. This W by L would be of M1. This W by L would be M2. So here the W by L is W by L of M1, and here the W by L is W by L of M2. Right? So I guess I should change those equations because I need to write W by L of M1. So what will be your I naught? I naught would be mu n CoX W by L of M1 divided by 2 VGS minus VT whole square. So what will be V? V will be 2 I naught upon mu n CoX W by L of M1 under root plus Vt. This is the equation 1, and this voltage is fed to this M2, and you have adjusted V naught such that M2 is working in saturation region. Now if M2 is working in saturation region, then what will be the equation of I copy? I copy would be mu n CoX W by L of M2 by 2 into V minus Vt whole square. What is V? This is V. V minus Vt whole square. So that would be equals to mu n CoX by 2 W by L of M2. What is V? V is this root 2 I naught mu n CoX W by L, root 2 I naught mu n CoX W by L of M1 plus Vt minus Vt whole square, right? This was your V. I replaced V here, nothing else. Vt will be get cancelled, and this root will be cancelled by square. So what you are getting? This mu n CoX will be cancelled, 2 and 2 will be cancelled. So what do you get? So this I copy would be simply equals to W by L of M2 divided by W by L of M1 into I naught. That's it. This is your I copy. So here the current is independent of the supply variation, also the temperature variation, because the current is neither depending on mu n, neither it is depending on Vt, nor it is depending on VDD. Are you getting this point? Neither on supply, neither on temperature. So this I is independent of supply and temperature variation. So no matter if supply changes, variation. If supply changes or temperature changes, the current will be constant, and that will be proportional to I naught. So this was our target, to produce a current which is proportional to the golden current source, and that we have done using two MOS transistor. One was diode connected load, and the other was you made sure that M2 is working in saturation region. So this particular configuration is known as current mirror circuit. Okay, so let's write down the conclusion of the current mirror circuit, or better I should write the conclusion here only. So we are doing the alternative analysis of current mirror circuit. So let's just assume this is V naught. Now this is current mirror circuit only when Both M1 and M2 are in saturation region. M1 is certainly in saturation region. Why so? Because drain and gate are shorted. If drain and gate are shorted, that means it is certainly working in saturation region. We have to make sure that M2 is also working in saturation region. M2 is also working in saturation region. How you will make sure? By adjusting VDD and R. By adjusting VDD and R, you can make sure that it is working in saturation region. Because if you adjust VDD and R, V0 will be adjusted. So you have to keep V0 such that your M2 is working in saturation region. So what is the condition? What is the condition for current mirror? Both M1 and M2 are working in saturation region. Both M1 and M2 are in saturation. This is the major condition, that both should be working in saturation region. If one of them is in linear, then the situation will be different. Well and good. So write down the I naught equation. That would be mu n Cux W by L of M1 VGS minus VT. Let's assume this is V. Both have same VGS. This has VGS equals to V. Here also VGS equals to V. So VGS of M1 should be equals to VGS of M2. That is equals to V. Say yes or no. Right? Mu n select W by L VGS minus VT whole square. What will be your I out? This is your I naught. What will be your I out? This is the I out. What that will be? That will also be mu n Cux W by L of M2. VGS, what is VGS? V minus VT whole square. Let's call this as equation 1, this as equation 2. So equation 2 divided by equation 1. What do you get? Equation 2 divided by equation 1. I out by I naught. That would be equals to W by L of M2 divided by W by L of M1. So from here, what do you get to know? That your I naught is equals to W by L of M2 divided by W by L of M1 into I naught. That's it. So the current that is copied, that depends on that W by L ratio only. That's it. Let's see a simple example, very simple example we can see. I will add up a page. Very straightforward, very simple example. I will just frame it here only. Let's call this as VDD. VDD is, I am assuming it to be 5 volt. VDD is 5 volt. This resistance R is 2 ohm. Then there is this diode connected transistor. Then there is this another transistor. Okay, there will be some circuitry ahead, and this is your, forget about it, no V not nothing. W by L of this, if this has W by L, this has 2 into W by L, and this is your I out. This potential is given, that is equals to 1 volt. And also what is given? It is given that both transistors are working in saturation region. In saturation region. This is given. Find I out. Find I out. This is the question. Find I out. So what will be I out? I out would be W by L of transistor itself. Okay, forget that. First find the current here. If this is 1 volt, if this is 0, this will be 1 volt. So this will also be 1 volt. So what is the current here? That is 4 ampere. Sorry, 4 by 2, 2 ampere. Now, is there any current here? No. 0 ampere current here, 0 ampere current here. So there will be 0 ampere current here. So the complete 2 ampere current is flowing through this transistor. So this is the 2 ampere current that is flowing. So in the transistor, if 2 ampere current is there, what will be the current here? That would be 2 into W by L of this transistor divided by W by L into 2 ampere. So I out would be 4 ampere. That's it. You just need to go by the W by L ratio. 2 ampere current is flowing. If the W by L is doubled, current will be doubled. If 2 ampere current is there, if W by L is tripled, then the current will be tripled. If W by L is half, the current will be half. 2 ampere, half, 1 ampere. 2 ampere double, 4 ampere. 2 ampere triple, 6 ampere. Are you getting this point? That's it. 2 ampere current is here, it will be doubled. But make sure both the transistors are working in saturation region. That is the most important point. Both should be working in saturation region. That's it. That was the complete analysis. Let's move on to our next topic, that is current mirror circuit but using Pmos. Same, that's it. This is the current mirror circuit using Pmos. So here, this is the current that is flowing through M1. I naught current is flowing through M1. And the what will be I out? So I out would be equals to W by L of M2 divided by W by L of M1 into I naught. So this will be your I out. That's it. Are you getting this point? So this is the concept of current mirror circuit. Well and good. Let's solve a question. So both transistors are perfectly matched. This is given. Both transistors are perfectly matched. What do you mean by perfectly matched? That means they are having same W by L. Same W by L. W by L is 10 for both of them. You need to find the value of R to get 100 microampere output current. So it is given that output current is 100 microampere. If both are having the same W by L, that means what is the current here? Tell me. Look, both transistors are perfectly matched. Okay, it should be written that V0 is adjusted such that, okay, it is not given. Okay, what is the lowest possible value of V0? This is what they are saying. What is the lowest possible value of V0 such that this transistor M2 is working in saturation region? The question is incomplete. I should have such that M2 is working in saturation region. So M2 is working in saturation region. This is working in saturation region. This is also working in saturation region. That means both are in current mirror and both are matched. That means if 100 microampere current is there, this will also have 100 microampere current. So in the transistor M1, I know there is 100 microampere current. Well and good. There is 100 microampere current. What else is given? Vt value is given. Mu n so x W by L value is given. So mu n so x W by L value I am having. I don't have the VGS value. So first I will find the VGS value. This potential V. First I will find the potential of V. So what I can see here is that 100 microampere current is equals to mu n so x is 200 micro into W by L is 10, right? W by L is 10. VGS by 2. What is VGS? VGS is V minus VT is 0.7 whole square. So you can solve this equation. It will be V minus 0.7, that is equals to under root 10. Under root 10 is nearly 0.3, 0.314 near around that. So V will be nearly 1 volt. So V value you are getting is nearly 1 volt. So this V we got, that is 1 volt. This we can show in the next page. So this potential came out to be 1 volt. And the same potential will be going here, right? So what do you understand by that? 3 minus 1 by R is equals to 100 microampere. Say yes or no? Because there is 0 ampere current here, 0 ampere current here, so 0 ampere current will be coming from here. So 3 minus 1, that means potential drop is 2. 2 by R is equals to 100 microampere. So what is the value of R? That is 20 kilo ohm. The value of R is 20 kilo ohm. That is our first answer. Well and good. Very good. Okay. Now they are asking what should be the minimum value of V0 such that M2 is working in saturation region. So what should be the minimum value of V0 for saturation region? VDS should be equals to VGS minus VT. What is VDS? That is V0. What is VGS? That is 1 minus VT is 0.7. So V naught value should be 0.3. So what is the answer? V naught is 0.3 volt. What did you understand here? You understood that you have to make this, if you are making this circuit, you have to adjust V naught such that it is 0.3 volts so that it is working in saturation region. Now both are in saturation region, both have the same VGS, that means it is in current mirror. So 100 microampere current here, 100 microampere current here. By that you can get to know the value of R as well. So this was a very easy question. You could have solved it very easily, right? V value we find out, from that we could find out the value of R and V naught. Well and good. Okay, let's move on to our next concept. We will be building multiple current sources using current mirror. Multiple current sources. Here what did we do? We found out only one current source. I out. Only one current source we have made. We can make multiple current sources. How we will do it? So this is our VDD. We already have a golden current source, that is I naught. Now from this golden current source, I got to know there will be some circuitry here. Forget about that. This was M1, this was M2. So here what was my I copy 1? This was the current that I was getting, which was I copy 1. So my I copy 1 was, better I should write what here. I copy 1 was proportional to the W by L ratios. W by L ratio of M2 divided by W by L ratio of M1 into I naught. This was the I copy 1. Now what I can do, I will make one more MOS here. Similar thing I am doing. Okay, this is M3. I have to feed some voltage here, right? I have to feed some voltage here. That voltage will be this potential only. Simply this potential. I am feeding this potential only. Similarly, I can add more transistors. This will be my I copy 2. Similarly, I can add more transistor. Let's assume I add M3. So the same voltage I am applying it here as well. So I am giving the same bias to this one as well. Bias means DC voltage. I am giving the same bias to this one as well. So if this is having V potential, if VGS value is V here, then this is also having VGS value. Now this is 0, this is V. So V is traveling here and V will reach here. So basically, again the potential is V. This is 0, this is V. So V is traveling, will reach here. So this is again V. So all are having V potential, and we make sure that all the transistors are working in saturation region. All transistors are in sat. We have to make sure this, that all transistors are working in saturation region. So all are working in saturation region, all are having the same potential. So basically the current will be copied, right? This will be I copy 3. So the current will be proportional to the W by L ratio. That's it. So I copy 2 would be what? Better write it here. What will be your I copy 2? That would be, if this is M2, this should be M3 and this should be M4. So W by L of M3 divided by W by L of M1 into I naught. This will be your I copy 2. And what about I copy 3? I copy 3 also you can write W by L of M4 divided by W by L of M1 into I naught. Say yes or no, right? So this is the circuit. Now this circuit sometimes is shown in a different manner. So I will add a page. So here I will write other way of showing the same circuit. Other way of showing the same circuit. Same circuit. So sometimes in the questions, this particular circuit that is shown here, this particular circuit, it's shown something like this. Let's copy this circuit first. So these supplies will be gone. They will not make the connection like this. Instead, what they will do, they will make a line like this, like this. They will make a line like this. Okay. Let's make a clearer structure. They will make a line like this. Here also they will make a line like this. What do they mean by that? That this node is connected to this node and this node is connected to this node. So all these nodes are connected. So the same circuit is shown like this. Are you getting this point? This is M2, this is M3. So in the examination, if you see these kind of circuit, what will you understand? You will understand this, that this potential is connected here, again this potential is connected here. So all the potential are common. That means this V potential is here as well. This V potential is here as well. This V potential is here as well. It doesn't mean that they connected a wire like this. They connected a wire like this in the previous question that we have shown. They are connecting the wire like this, but shown like this. Okay. This will be your I copy 1. And this will be your I copy 2. This will be your I copy 2. So in the same way it is shown, and these equation will be the same, nothing different will be there. Are you getting this point? So this is the same way of showing the other way of showing the same circuit, right? Let's see what we are going to check. So this is a question which we will be solving now. Okay, so let's solve this question. Actually someone came in the room, so I had to stop the video. So yeah, let's solve this question now. You have to make a common source amplifier using NMOS. So common source amplifier that will be made using NMOS with the 100 microampere current source in load. Okay, till now this is the question. 100 microampere current source in load. 100 microampere current source in load. This is the common source amplifier. Load will be at output. So this is the 100 microampere current source. Now this 100 microampere current source, from where you will be getting this? They are saying that you have a reference current source of 200 microampere. So from 200 microampere, you need to make 100 microampere. This is your task. Your task is to make this current source. How will you make from this 200 microampere current source? So that we will do. Okay. And what else they are giving? They are saying that you have only one supply VDD. You have only one supply. Here I cannot apply my input like this. That this is my small signal input Vin plus VGG. I cannot apply like this. Why so? Because I don't have VGG. I have only one supply. So if there is only one supply, how do you bias it? We have already seen it, right, in MOSFET amplifier. This is how we bias it. You have only one supply, that is VDD, R2, R1, and here I will apply my small signal input, that is my Vin. What else they are saying? Your small signal input Vs has an internal resistance Rs. So this my small signal input is something like this. It is having Vs and it is having Rs. So this is how I will apply my small signal input. Are you getting this point? This is the coupling capacitor. So when you do the DC analysis, only this will be in action. And when you do the AC analysis, this will come in action and there will be no use of this R1 and R2. Are you getting this point? Well and good. And now after designing the complete circuit, you have to find the small signal voltage gain. Now this is not the final design. Why it is not the final design? Because you have to design this 100 microampere current source. So how will you design that? Using current mirror circuit. Are you getting this point? What did they ask you to design? A common source amplifier with a 100 microampere current source in load. That's it. Then they said that you have only VDD. Okay, only VDD I am having. Then I have to bias it. How will I bias it? By using potential divider. R2 by R1. Resistor divider or potential divider using R2 and R1. I have to apply small signal input as well. Small signal input is having RS resistance. So VS, RS, then there is coupling capacitor. So this is my design. This is not the final design because I have to make this 100 microampere current source as well. So now my next task would be what? What is my next task? That is designing 100 microampere current source from 200 microampere reference current. Now, where is your current source going? Your current source is going from VDD to some node. Say yes or no. It is going from VDD to some node. So if it is going from VDD to some node, so what we will have to use? Top to some node, we will use Pmos. You cannot use NMOS. We will use Pmos because it is going from VDD to some node. Top to some node. Top P for Pmos. So we are designing a 100 microampere current source from 200 microampere reference current. So you are having a 200 microampere reference current. 200 microampere reference current. This is what you are having. You will pass it through a Pmos, which is a diode connected transistor. So you are passing it through a Pmos. You have only one supply, that is VDD. And then one more Pmos will be there. You have only one supply. Source should be at higher potential. And here there will be some circuitry that we have already seen. So this is the 200 microampere current source which is flowing in this MOS as well. Let's just call this has W by L ratio. If this has some W by L ratio, what should be the W by L ratio of this transistor? It should be half of this. Are you agreeing to my point? Because if this is having 200 microampere current, and then if this is having half of W by L, then it will be having 100 microampere current. Are you understanding this point or not? So what was the question? You have to, these specs are given, you have to design the circuit. We started designing the circuit. We made this much of circuit, then we got to know we have to design a 100 microampere current source from 200 microampere reference current. This is the 200 microampere reference current we are having. We also got to know we have to design the current source such that it is going from supply to some node, supply to node, top to node, top P. That means we have to use Pmos. So we are using Pmos, 200 microampere current that is flowing through W by L. Then half of W by L will have 100 microampere current. So this is the current source that we have made. So this was our next task. So what will be your final design? Final design. So this is the final design I am having. This is 200 microampere current source. Here both are having the same VSG. Both are having the same VSG. And yeah, I have to write one more thing. Making sure that this transistor is working in fact. You have to make sure that this transistor is working in saturation region. Okay. This is, let's call this transistor as M3, this transistor as M2. Now this 100 microampere current source is fed to a common source amplifier. This is the V0 we were having. Also by using this VDD supply, and a potential divider I was getting my DC bias. This was R1, this was R2. This was the DC bias I was getting, and then I had my small signal source here. So this is my final design. I am done with my final design. I used only one VDD. I used only one supply. I had the resistance R1, R2. I got the bias from there. These are the transistor I am having. Let's call this transistor M1. I will adjust VDD R1, R2 such that all transistors are working in saturation. All transistors should be working in saturation. Why these two should be working in saturation? Because this is current mirror. And why this should be working in saturation region? Because you are using it as an amplifier. So all transistors are working in saturation region. This is having 200 microampere current, and what is the other relation? W by L of 3 is 2 times of W by L of 2, right? This is doubled, M3 is doubled, so this is half, right? So W by L of 2 is half of W by L of 3. So here there is 200 microampere current, so this will be having 100 microampere current. So this is our final design. Now what did they ask? This is not the final answer. They asked to, after designing the circuit, find the small signal voltage gain. Now you have to find the small signal voltage gain. So how you will find it? This is a very, very important concept. Watch it carefully. So I will find the small signal voltage gain now. So for finding the small signal voltage gain, what do we do? This supply will be shorted. So this will be shorted. What will happen to this current source? This will be open circuited. This current source will be open circuited. This circuit will be reduced something like this. Say yes or no. Are you agreeing to my point? This is M3. So from source to drain you are having a R0 resistance. This is M3, so it will be having a R0 3 resistance. Say yes or no. R0 3 resistance, right? Forget about this 100 microampere. This VDD will also be shorted. This will also be shorted. This is having a R0 2 resistance. What about this? This VDD will be gone and R1 R2 will come in parallel. So better we make it like this. What will happen? This is Vs, this is Rs, R1 and R2 will come in parallel. R1 parallel R2 will be connected like this. Say yes or no. Are you agreeing to my point? What will happen to this circuitry? This is the task. What will happen to this much of circuitry? Because one thing I know, that from V0 to ground, from this V0 to ground, I see R01. From V0 to ground, I see R01. From V0 to ground, I see this MOS. And from V0 to ground, I see this much of circuitry. What will happen to this circuitry? Tell me. Let's assume there is V potential here. There is V potential here. So what I can say? From V to ground, I see R03. And from V to ground, I see 1 by GM3. Say yes or no. I told you, if there is this arrow, that means there is 1 by GM. Or how you can say, if this is V potential, then how much current is there in this MOS? GMV. Will there be any current? No. Will there be any current? No. So will there be any current? No. So this V potential is, this M3 is having GMV current. So this V potential will be coming here as well, right? So from V potential, what do you see? From V potential, there is R03 current. Sorry, from V potential, there is V by R03 current, and from this V potential, there is GM3V current. This is GM3V current. So what is the impedance you can say? R03 parallel with 1 by GM3. Say yes or no. Let me show you the circuit once again. What is the circuit? This is the circuit. These are shorted. This is also shorted. Here there is R naught. And this is potential V. This potential V is carrying here as well. If this is V potential, that means here there is GMV current. Forget about this R naught. Let's call it R naught. You need to find the impedance from here. You need to find the impedance from here. So let's just assume if this is V potential, then what is the current here? That is I. So if this is V potential, this is the current I. So this I current would be equals to, there is no current here, there is no current here. Just a second. Yeah, so what I was saying, so from V to ground you see GMV current, from V to here you see V by R02 current, right? So V by R02 plus GMV R02 or whatever it is R0, V by R0 plus GMV is equals to I. So what is the resistance you see? 1 by GM parallel with R0. Or you can directly say from V to ground I see 1 by GM, from V to ground I see R03. So this much of circuitry, this much of circuitry will be replaced by simple resistance. This much of circuitry here will be replaced by simple resistance. From V to ground, what do you see? 1 by GM3 parallel with R03. Now, this is the circuit. 1 by GM parallel with R03. Now, this potential is being fed here. Now, this is the same, right? You are checking from V0. You are checking from the point of view of V0. Because your final target is from V0 to ground, what do you see? This is your final target. Okay. Now, this much of circuitry is replaced with a single resistance, that is 1 by GM3 parallel with R03. Now, how much current is this will have? Because here there is 0 ampere current. So, how much current this resistance will have? 0 ampere current only. This will also have 0 ampere current. This is ground, that means if, and this resistance is having 0 ampere current. So, that means this voltage will be 0 volt. Are you agreeing to this? 0 ampere current is flowing. So, this potential will also be 0 volt. So, basically, this potential, this will be replaced with ground only. Yes or no? Here there is 0 ampere current, right? Also, this is also 0 ampere current. So, this will be replaced with ground. Here VSG is gone. If VSG is gone, that means there is 0 ampere current. So, basically, this much of complete circuit is replaced with single resistance R02. Say yes or no. Did you understand? This configuration was replaced with resistance 1 by GM3 parallel with R03. Then I got to know that this became grounded because there was 0 ampere current here. So, this node would become grounded. If this is grounded, that means VSG is gone. If VSG is gone, that means MOS is having 0 ampere current. If MOS is having 0 ampere current, so from V0 to ground, I see only R02. Say yes or no. So, from V0 to ground, I see R02. From V0 to ground, I see here R01. Right? So, what is the equivalent? Now, what is the final equivalent? This is my Vs, Rs, R1 parallel R2. This is Rs, this is Vs. This is V0. So, from V0 to ground, I see R01. From V0 to ground, I see R02. Now, whatever the potential that you get here into GM, into GM1 will be the current flowing. So, then you can write down the gain. We have seen it in common source amplifier. So, no worries about that. This was our one, this was our second, this was the final circuitry. So, I hope you are understanding it. What will be the gain? Now, I will directly write down the gain. You should be comfortable with this. What will be the gain? V0 by Vs. That would be GM1 into R minus sign certainly will be there because this is common source amplifier. R01, R02 into R1 parallel R2 upon Rs plus R1 parallel R2. Say yes or no. This is V naught by Vs. Are you agreeing to my point? This gain you can write. First write down the potential here, then the current here would be GMV, GM1V. The same current is flowing through R0 or this final output impedance. That current would be GMV. That current is flowing through V0. So what will be your V0? V0 would be GM1 into R01 parallel with R02 and minus sign. And what is the value of V? Value of V is R1 parallel R2 upon R1 parallel R2 plus Rs. So from there you could get this final answer V0 by Vs, that is this. So this was the first method from where you could find the small signal voltage gain. Now what is the other method? Here I know that this is a 200 microampere current source and this current source is copied into 100 microampere, right? So I can replace this much of circuitry with a simple current source, but that has some output impedance. This much of circuitry can be replaced with a simple current source that has the output impedance of M2. The output impedance of this side will not matter. Why? Because whatever the impedance we are having here, that will be going towards 0 only. Whatever the impedance we are having here, that is going towards 0 only. So only the impedance of this side is mattering. Impedance of this side is matters. Only impedance of this side matters. That's it. So the side which is connected to the M1 MOSFET, only the impedance of that side is mattering. So whatever the current that is being pushed into M1, whatever the current that is being pushed into M1, only the impedance of that side matters. That's it. So what is our method 2 now? Method 2. So simply we have a 100 microampere current source here. Now how much output impedance this 100 microampere current source is having? From this particular node you will see that is R02, right? So you will make that this is the 100 microampere current source you are having, which is having a resistance of R02, and then you are having a common source amplifier. This is Vs, this is Rs, this is V naught, and this is grounded. And if you are doing the small signal analysis, then this 100 microampere current source will also be gone. Why it will be gone? Because this is a DC current source. What do you see? From V naught to ground, you only see R0 2 resistance, right? And from here you see R0 1 resistance. So simply your circuit is replaced with from V0 to ground R1 parallel with R0 2, right? So here I will just make the circuit once again. Here I will make the 100 microampere current source so that students will be comfortable. This is VDD and this R0 2 is connected like this. Then if you do the small signal analysis, this will be gone. And here we are having R1 parallel R2. Or better I should make. Here I am making the complete circuit only, not just the small signal. This is R1, this is R2, this is VDD, this is RS, this is V, this is VS, this is capacitor C. So what will be the final circuit after the small signal analysis? This would be RS, this would be R1 parallel R2, and here you are having this MOS, and from V0 to ground you are having R0 1 parallel with R0 2, and this is your VS. That's it. This was your M1. So this is the small signal analysis. Did you get to know? So for gate aspirant, what will be the question? For the gate aspirant, this circuit will be given. In the examination, they will not ask you to design a circuit. But if you learn to design a circuit, it will be very helpful for you. Because just by seeing the circuit, you will get to know, okay, they have designed it in a way that 100 microampere current is acting as a load for common source amplifier. If I had directly given this circuit to you, okay, and I had asked you to find the small signal voltage gain, then you wouldn't be learning anything. You would be only learning how to solve a particular problem. But what we are doing in the complete course, first we are designing something and then we are learning how to solve it. Are you getting this point? This is my objective of teaching this course. First we design, and once you see the question, you should be knowing what they actually want to ask. So if this question was in front of you and they ask you the small signal gain, what you would understand? That they are using a 100 microampere current source as a load. Now this 100 microampere current source will have the output impedance similar to what M2 is having. So from here, what is the output impedance do you see? That is R02. So directly you will make R02. Nothing you will see. You will not even see here because the current is copied here. That's it. So you will make R02, then you will make this M1 and directly you will write down the final gain. So this was the objective. That's why we are spending so much of time, so that in the examination you have to spend the minimum time. And toughest of toughest question you will be able to solve. Say yes or no. Let's move on to our next question. Next question you will be solving it on your own. So this is the next question. You have to design a common drain amplifier. Common drain amplifier will be made using NMOS. Design a common drain amplifier which will be made using NMOS with a 100 microampere current source in load. So you have to design a common drain amplifier. They are not talking about the supply, so we have different supplies now. So common drain amplifier using NMOS. This is the common drain. In common drain, you apply the input here, you get the output here. Apply the input at gate, get the output as a source. 100 microampere current source in load. In load, you are using 100 microampere current source. This 100 microampere current source, you have a reference current source of 200 microampere. From 200 microampere, you need to make 100 microampere current source. But what is the condition? That all the transistors are having the same W by L ratios. This is the condition now. Here, what did you do? That sir, here I am having W by L ratio of W by L, and here my W by L ratio is half of the previous one. But now they have said that all the transistors are having the same W by L ratio. So what you will do now? This is the question. Think about it and tell me. Use your complete brain. Think about it. If you are able to think, then it's very good. If you are not able to think, no worries. Even I was not able to think about it in the first chance. Okay. So no worries if you are not able to think. If you are able to think, that is very good. So what this Vin would be, let's first write it. It will be small signal Vin plus VGG. But they are not talking about supply and anything now. Here I talked about supply and everything. So here I have eradicated all those things. So now our task is to design a 100 microampere current source from 200 microampere golden source, but W by L ratio is same. So what you will do? So my task is now designing 100 microampere current source. How will you design it? You have a 200 microampere current source. One thing I know, that this current will be copied. One thing I know, the current will be copied, right? But the current that is going to be copied, that has to be 100 microampere because W by L ratio is same. What is the copied current? Copied current is W by L of someone divided by W by L of the other one into the current. Now W by L is same. So copied current will be the same as whatever the current that you are having. But the current that you are having is 200 microampere. So you need to get 100 microampere out of it. Say yes or no. How you can get 100 microampere from 200 microampere current? If there is I current flowing, I pass it through two equal resistance. This is resistance R, this is resistance R, this is I current. What will be the current in this one? I by 2. What will be the current in this one? I by 2. The same thing we are going to do here. 200 microampere current you are having. I am going to, okay, Now secondly, what you will use for making a current source now? NMOS or PMOS? For making a current source, what you are going to use? NMOS or PMOS? We are going to use NMOS. Why so? Because we are going from some node to ground, node N, node to ground. That means I am going to use NMOS. Okay, better, I will make a better circuit. Basically, this 200 microampere current should be divided into two parts. 200 microampere current should be divided into two parts, and then that current will be copied here. This current will be copied here. And here there will be the MOSFET amplifier. Here that will be the circuit. This current will be copied. टेढ़ा हो गया भाई. You have to divide the current. How will you divide the current? This should be looking here like this. This should be diode connected as well. Say diode connected, and the same kind of transistor I can add here. That's it. This is your VDD. VDD 200 microampere current is coming. Now that current will be divided into two transistors. Both are having the same W by L, so both will have the same current, 100 micro. This will also have the 100 microampere current. Now this current, this is having V potential. If this is having 100 microampere current, this is having V potential. That means this will also have V potential. Now this same V potential will be fed to this. All are having the same V potential. All are in the saturation region. That means all will have the same current. That this will also have the same 100 microampere current. Say yes or no. Did you understand this question or not? You had 200 microampere. You need to get 100 microampere current out of it. You need to divide that current. I divided that current into two diode connected MOS. Both are in saturation region. Both are in saturation region. Both have the same W by L ratio. That means both will have the same current. So 200 will be divided into two parts, 100, 100. Say yes or no. Right? 100, 100, both current are divided. If 100 microampere current is flowing, that means there will be a voltage developed V across them. Both of them will have the same voltage. Why both of them will have the same voltage? Because both are having the same current. That's why both of them will have the same voltage. Or better, I should short circuit their voltages. Or it is already shorted actually. If this is 0, this is V, then this will be V only. Both have the same voltage already. So both have same VGS, both have same WIL, both have same VT, everything is same. That means both will have the same current. So 200 microampere current will be divided into two parts. That will be 100 microampere and 100 microampere. Are you getting this point? So both are having 100 microampere current. Because of this 100 microampere current, some voltage is developed. That is V. The same voltage is fed to the other transistor. Now I am making sure that this transistor is working in saturation region. I will make sure by the supply, I will make sure that this transistor is working in saturation region. So that is having 100 microampere current, which is acting as a load for a common drain amplifier. So what will be my final design? So in my final design, I will copy this circuit only. Array, wow. This current source I have made. So simply I need to use a common drain amplifier here. This was VDD. This is V in. And this is my V out. If this transistor is M, all the transistor that you are having is having same W by L. So all the transistors are identical. All what you are having is NMOS, all transistors are identical. Tell me the small signal voltage gain for this. Write down your final answer and then match it. What is your final answer? Gm R naught upon 2 plus Gm R naught. If you are getting this answer, just close this video and move to the next video. If you did not get this answer, then watch the solution. If you are getting this answer, forget it. You are great. You have understood everything from this lecture. Just move to the next lecture. If you are not getting it, then watch the video. यही आएगा ना यार कहीं GM R naught यही आएगा. Okay. What did I tell you? This will have 100 microampere current. This will also have 100 microampere current. What they will act as? They will act as a current source, and their impedance doesn't even matter. Also, what we can do, first let's solve it by the conventional method. What is the conventional method? I need to look the impedance from here. What is the impedance do I see from here? So I need to look that impedance. So if this is voltage V, this will also be voltage V. So here from V2 ground I see 1 by Gm. From V2 ground I see R0. From V2 ground I see R0. From V2 ground I see 1 by Gm. So from V2 ground what do I see? 1 by Gm parallel with R0, parallel with 1 by Gm, parallel with R0. Say yes or no? From V2 ground I see 1 by Gm. From V2 ground I see R0. From this V2 ground I see 1 by Gm. From V2 ground I see R0. From V2 ground 1 by Gm. From V2 ground R0. So this much of region will be replaced by 1 by Gm parallel with R0, parallel with 1 by Gm, parallel with R0. Say yes or no? Let's do the small signal analysis of this. This is the final design. Now we are going to do the small signal analysis. Small signal analysis. All transistors are already working in saturation, so forget about it. This is 200 microampere, which will be gone. From V to ground 1 by Gm parallel with R0, parallel with 1 by Gm, parallel with R0. So this much of circuitry will be replaced by, from V to ground, you are having 1 by Gm parallel with R0, parallel with 1 by Gm, parallel with R0. Whatever the impedance you are having here, does that matter? No, because this is 0 ampere current. If this is 0 ampere current, this will also be 0 ampere current. That means this node will be grounded only. And if this node is grounded, that means VGS is gone. And if VGS is gone, so from V0 to ground, you only see R0 resistance. That's it. Are you getting this point or not? And this is also grounded in small signal analysis. And in place of V in, I will write small signal V in. So from V0 to ground, I see R0. From V0 to ground here also I see R0, because the same current, 0 ampere current is flowing here. The resistance is having 0 volt drop. This is 0. This is 0. This is also 0. So VGS is gone. So complete 0 it is. So from V0 to ground, I see only R0. From V0 to ground, I see only R0. So here, this is my V in. V0 to ground, I see R0 parallel with R0. That would be R0 by 2. And this is grounded. What will be my gain now? This is 1 by Gm here. This is 1 by Gm. So what will be the gain? V0 by V in. That would be R0 by 2 upon 1 by Gm plus R0 by 2. So what we will get? Gm R0 upon 2 plus Gm R0 V0 by V in. This is the final answer. So always remember one thing. No matter how many current mirrors do you use here, only the current mirror will matter which is acting as a load. That's it. Only the current source which is acting as a load, that will matter only. These will not matter, because everything which we are having here, that will be replaced by a single resistance. So this is replaced by a single resistance, and here there is 0 ampere current. So this resistance will also have the 0 ampere current. So here that voltage drop will also be 0. If voltage drop is 0, that means there is no use of this. Now VSG is also gone. If VSG is gone, what does that mean? If VGS or VSG is gone, that means this M will be replaced with open circuited. whatever the output resistance it is having, that will come into action. So this M was having R02 output impedance, so only R02 output impedance will come in action. Say yes or no, are you able to understand the complete concept? I hope you are able to understand the complete concept. So this is the current mirror that should be taught in the gate field, but it is not taught in this manner. In the small signal analysis should be taught for this current mirror as well. And I will show you the questions which have been asked in the previous gate examination from the small signal analysis of current mirror. So what is the conclusion that we got to know in current mirror? No matter whatever the circuitry you are having here, the final resistance would matter, that is here. So I will write down a conclusion. What is the conclusion? Let's just assume this is a VDD. From here you are having a current source of some ID. Then there will be a lot of diode connected transistor. There can be a lot of diode connected transistor. One, then more will be there. Two, this is also diode connected. There will be more like that. Then there will be this final one. The voltage from this will be fed to the final transistor here, and above that you will be having some circuitry, some amp you will be having. So what do you see from here? What do you see from here? So from here, from V0, what do I see? From V0, at the above side I will see an amp, and here I will see a current source, whatever the current I get, a current source, and the output impedance of this. That's it. What is the output impedance of M? So R0 of, let's call this M dash. So R0 of this M dash. That's it. This is the conclusion. Are you getting this point? No matter whatever you are having, all will be replaced with a single resistance. And if this is replaced with a single resistance, then 0 ampere current would make the potential here 0. Then VGS will be gone, and if VGS is gone, then only one resistance I see. That is it. I hope you have understood the concept of current mirror. In the next video, we will see very interesting question on current mirror circuit and cascode amplifier. So next will be an assignment which you will be solving. Okay, so that will be assignment 9, I guess, or 10, I don't know. I will check it. Assignment 9 as far as I remember. So next we will see assignment 9. Okay, thank you. Hi everyone. So in this video we are going to solve assignment 8. This is there. But before that, let's see one simple thing. Sometimes students get confused in these kind of circuits. So I'm dealing this circuit. So you just need to tell me R in value, here R in value and Rx value. This is your question. You need to tell me those values. If you see from here, if you put V in here and get I in out of it, what is the current going here? That is 0 ampere. So V in by 0 ampere, the impedance from gate terminal is always infinity. Impedance from gate terminal is always infinity. Say yes or no. Impedance from gate terminal, impedance looking from gate terminal is always infinity. Now I am asking, what is the R in looking from here? So in the previous lecture, I am continuously saying that from gate to source I see 1 by Gm. If I say from gate to source I see 1 by Gm, why not the answer is 1 by Gm here? Why 1 by Gm is wrong? Because gate is driving 0 ampere current. Now what will I do here? What do I need? I need V in by I in, right? If I apply this V in, the same V in will be coming here. Now the same V in is coming here, so here it will be driving Gm V in current. Say yes or no? And there is R not connected as well. So this same V in will be traveling here as well. So from V in there are two currents, this current and this current. Addition of this current will be going this way. So what is your I in? I in is simply Gm V in plus V in by R naught. So what will be your V in by I in or R in? That would be 1 by Gm parallel with R naught. So in the previous questions, When I was saying that from V in to ground I see 1 by GM, in that case the drain and gate were shorted. Did you understand this point? If I apply a potential here, it will drive GM V in current, but here the current is 0 only. Addition of these two current is flowing from here and that current is going that way. That's it. This current is going that way. This current is equals to I in. So from I in this current is going, then GM V in plus V in by GM V in plus V in by R naught is equals to I in. And from there I could see that I have the impedance 1 by GM parallel with R naught. So did you understand this point? It's not that from V in to ground I am seeing 1 by GM. Since I have applied V in, then there is current GM V in, and the same current is coming out of V in only. So then only you can say 1 by GM parallel with R naught. What is the case in this one? You need to find Rx. So yeah, if I was finding this small signal impedance, then there was no use of this ID. This ID would have been open circuited. ID would have been open circuited. So I will just draw it and I will just call it open circuited. It would have been open circuited. What about this one? This will also be open circuited. Now you will apply Vx here and get Ix out of it. So from Vx to ground you are having R0 as well. What I am doing is I need to find Rx. So what I will do, first let's just extend it. And from here I need to find Rx. This was my question. So I will apply Vx and get Ix out of it. Apply Vx here and get Ix out of it. Here I am having R0 resistance. So what will be my Ix? Ix would be this current Vx by R0 plus the same Vx. This same Vx will be traveling till here. And this current would be GmVx. So Vx by R0 plus GmVx is equals to Ix. So what will be my Vx by Ix? That would be same as 1 Vx by Ix is equals to Rx, and that would be same as 1 by Gm parallel with R0. Say yes or no. So what did you understand here? What did you understand? The point why I wanted to take this example was to make you understand of this current mirror circuit. This is VDD and this is ID. And there will be some circuit there, some circuit would be there, whatever the circuit is there, forget about that. So in the previous lecture, what we were doing, we were replacing this side with 1 by Gm parallel with R0. We were replacing this complete side with 1 by Gm parallel with R0. So some student may get confused. What they would think that, sir, from here to here I see infinity resistance. So why I am replacing it with 1 by Gm parallel with R0? Because you are replacing from here, not from here. From here you see infinity resistance, that's fine. But from here, what is the resistance you see? 1 by Gm parallel with R0. Right? Because if you apply V potential here, then what will be the current? GMV. And what GMV current, and then there is R0 connected as well. There is this R0 connected as well. So the current would be V by R0. So from V you are having two currents, 1 by R0 and GMV. You are having two currents, that is 1 by R0 and GMV. And because of that you replace this much of circuit, this much of complete circuit with 1 by Gm parallel with R0. If I had some circuit like this, just there is some circuit, forget about that. So if I replace my circuit from here, how will I replace it? With open circuit, because from here I see infinity resistance. So I will replace it with open circuit. Are you getting this point? But here I will replace it with 1 by Gm parallel with R0. So basically this is how it could be replaced. This will be replaced with 1 by Gm parallel with R0. From here 1 by Gm parallel with R node. Then there is zero current here, and if there is zero current, this will be shorted, and if this is shorted, this will completely have no effect. So those things we have already seen. Just I wanted to clear this fact because some guys might be having this doubt since these videos are recorded. So some guys might be having this doubt that, sir, how did you replace it with 1 by GM parallel with R node? It's not that from gate to ground, you are seeing 1 by GM. No, no, no. You can say from source to gate I see 1 by GM. From source to gate I see 1 by GM. It's not that from gate to ground you see 1 by GM. From gate there is 0 ampere current. But if your gate and drain are shorted, then there will be two components of current that will be coming out from V only. This potential V only. So because of that, this will be replaced with 1 by GM parallel with R naught. Well and good. Everything is crystal clear. Let's start with question 1 now. You have to find the small signal voltage gain. Let's start solving it. Let's copy the circuit and write our solution. So for finding the small signal voltage gain, what we are going to do? Let's make it open circuited. This VDD is gone. This VDD will be shorted. Lambda is not equal to 0 anywhere. It is not given that lambda is equal to 0. So you have to consider lambda. What will happen to this one? From here, what you will replace? Let's just call this potential as V. This potential as V. And if I replace this potential as V. So from V to this node, what do you see? So from V to this node, I see 1 by GM and R naught 4. Say yes or no? 1 by GM and R naught 4. So from V1 to this node I see, and let's just assume this node I am calling V2. So from V1 to V2, what do I see? Actually, here I see infinite resistance. From V1 directly I see infinite resistance, but I know because of V1 and V2, there will be a current GM V1 minus V2, GM V1 minus V2 flowing. Because of this V1 and V2, there would be some current flowing here, and that would give me 1 by GM resistance. Are you getting this point? So this will be replaced with 1 by GM, and from here you get R naught 4. So basically what is happening is that this is your V1. Between V1 and V2, what do you see? From V1 to this node is V2 only. This node will travel towards V2. So from between V1 and V2, what do you see? So from V1 to V2, there is R naught 4. And between V1 and V2, there is 1 by GM4. This is your V2. Now let's talk about V2. From V2 to ground, what do you see? R naught 3. This is the R naught 3. From V2 to ground, you see R naught 3. And from V2 to this node, you see 1 by GM. Okay, this is M1. So from V2 to ground, you see R naught 1. From V2 to ground, you see R naught 1. Parallel with, from here to here, you see 1 by GM1. You could only see it because here drain and gate are shorted. If the drain and gate are shorted, then only you can see 1 by GM parallel with R naught. Why so? Because this will give a component of current in the MOS, and that current will be flowing from V2 only. In this case, this potential V will give a component of current for sure, but that current will not be flowing from V. The current flowing from V is 0. But in this case, this potential V2 will give some component of current. That current would be GM1 V2, and that current will be flowing from V2 as well. From here, that current would be flowing from V2 as well. That's why we replaced it by R01 parallel with 1 by GM1. Getting this point? Now this VM1, this is connected with M3 resistance like this, and this V2 is connected, and this V2 node is connected to gate of M2. Right? This is your V0. This is V in. So from V0 to ground, you see R05. From V0 to ground, you see R05. Right? Now, how much current they will have? 0 ampere current. Why so? Because here there is 0 ampere current, here there is 0 ampere current. If this is 0 ampere current, the same current 0 ampere current will be flowing from here. If there is also 0 ampere current, then this will also have 0 ampere current. So all those will have 0 ampere current. So all those resistance will have 0 voltage drop. So what will happen? Eventually these nodes will be shorted. Eventually these nodes will be shorted, right? In the examination you will not have to draw this much of big circuit. What you will see, okay, from here to this node I see 1 by Gm parallel with R04. From here to here I see 1 by Gm parallel with R04. Both of the resistance will not drive any current. If both of them resistance are not driving any current, then simply this will be shorted. That's it. So you will only draw this side only. You will only draw this side. But here I am explaining, that's why I need to draw all those things. I need to explain you as well that how you are seeing the resistance. From here you see 1 by Gm parallel with R01, 1 by Gm4 parallel with R04, and all are having 0 ampere current, so all will be having 0 voltage drop. So all those will be shorted. This is M3, this is M2. Let's make the final circuit on the next page. So upward direction we are having M5. This is V in, this is ground, this was V0. So from V0 to ground you are having R05. This is your M5. And here you are having this much of thing. This is shorted and this is also shorted. This was your M3 and this was your M2. This was your M3, this was your M2. Tell me what will happen to M2? M2 will be simply open circuited because VGS is gone. So M2 is open circuited, but it will leave R02. M2 will simply be open circuited and it will leave R02. Right? Say yes or no. What about M2? M2 VGS is gone. So here it is only having R02. So it will leave that. VGS is gone, it will only leave R02. And here you are having R03 as well. This R03 as well you are having. So this R03 is also there. Now tell me one thing, can you replace this complete circuit with some resistance? Can you replace this complete circuit with some resistance? Yeah, we can replace it. We are moving from drain to source. If you are moving from drain to source, you are moving backward. If you are moving backward, then you need only one step, and this is a common gate amplifier. Gate is shorted, you are moving from drain to source. So what is the resistance? The resistance is GM3 R03 plus GM3 R03 R02 plus R03 plus R02. So this is the total resistance. So from V0 to ground, you see this resistance. From V0 to ground, you see this resistance as well. So what is the final circuit? This is shorted. Here you are having V in. From V0 to ground, what do you see? This is your V0. So from V0 to ground, I see R05 parallel with, from V0 to ground, I see this resistance. That is GM3 R03 R02 plus R03 plus R02. Say yes or no. So I have reduced my circuit like that. This I replaced with the given impedance, then I replaced this with as R05. So this is how I have reduced. Now what is this? This is simply a common gate amplifier, common drain amplifier. This is simply a common drain amplifier. So what is the gain for common drain amplifier? Let's call this resistance as R. This resistance I am calling it as R. So what is the gain of common gate amplifier? Simply GM5R upon 1 plus GM5R. Right? That's it. This is your answer. Where R value is, what is the value of R? R value is R05 parallel with GM3 R03 R02 plus R02 plus R03. That's it. In the examination, in the one step only, I will be writing the answer of this particular question. What I will do, I will replace it with the resistance. Whatever the resistance it is replaced with, I know that will be grounded. If that is grounded, all these nodes will be coming to ground. If these nodes are coming to ground, that means this M2 will be replaced with simply a resistance. M2 will simply be replaced with R02, and M3 will be a common gate amplifier that has a source resistance of R02. So for that I know the formula. If you are moving from drain to source, I am going backwards. That means I need only one step. There will be no denominator, so only numerator will be there. So GM3 R03 R02 plus R02 plus R03. And from V0 to ground I see this resistance, and from V0 to ground I see R05 resistance as well. So basically from V0 to ground I see R05 parallel with this much of resistance. And this is simply becoming common drain amplifier. I remember the formula of common drain amplifier. Even if I don't remember, I can derive it very quickly, because from here I will put 1 by Gm, and here I will see R. So R upon R plus 1 by Gm. That would be GMR upon 1 plus GMR. That is my formula. GMR upon 1 plus GMR. That's how I can derive it. Well and good. Okay. So yeah, that's it. Let's move on to this question. You have to plot Vx versus Ix. You have to plot Vx versus Ix. You are sweeping your Vx voltage from 0 to 3 volt. So you will sweep your Vx voltage, and then you will see how your Ix goes. So this is 2 volts. This is 0. This is 2 volts. So this 2 volt will be coming here. If this 2 volt is coming here, that means here it is driving 1 ampere current. Now what you will say, sir, this is in current mirror, so Ix will always be 1 ampere. Wrong. What did I do? This is 2 volt, and then I put 2 volt here. 1 ampere current is flowing. If this 1 ampere current is flowing, then this is a current mirror circuit, so Ix will always be 1 ampere. Is that correct? No, that is wrong. Why so? Actually, I should put 3 kilo ohm here, because 1 milliampere sounds better. 1 ampere, that much of current, this MOS cannot drive. So 2 volt will be coming here, and it will drive 1 milliampere current. So the same current will be Ix. That is wrong. Why it is wrong? Because it is in current mirror only when both of the transistors are in saturation. Let's call this transistor as M1, this transistor as M2 and M1. Ix will be 1 milliampere when M2 is in saturation. So when M2 will be in saturation? When your VDS should be greater than VGS minus VT. VT value is given or not? VT value should be given in the question. Let's assume that to be 1. VT value is 1 volt. So your VDS should be greater than VGS, that is 2 minus VT. So when your Vx is greater than 1 volt, your M2 is in saturation. If M2 is in saturation, then M1 and M2 are in current mirror. If M1 and M2 are in current mirror, that means your Ix will be 1 ampere. So your Ix will be 1 ampere. Only for Vx greater than 1 volt. So for Vx greater than 1 volt, Ix will be 1 milliampere. Right? Not 1 ampere, 1 milliampere. So let's remove this curve from here. And for Vx less than 1 volt, your M2 is in linear region. If M2 is in linear region, what do you understand by that? Current in linear region is always less than current in saturation region. Right? For a fixed VGS. So you remember the curve, right? ID versus VDS curve, you remember, right? ID versus VDS. ID versus VDS. So how does the curve look like this for a fixed VGS? So this was the linear region and this was the saturation region. So in the saturation region, always the current was more. Now we can draw the final curve, that was Ix versus Vx. Ix versus Vx. So when Vx is greater than 1 volt, when Vx is greater than 1 volt, after that it acts like a simple current source. The value is 1 milliampere. But before that, current will be rising linearly. It will be in linear region, so it will rise like this linearly, and somewhat it will rise like in this manner, right? So here it is acting as current mirror. But before that it was not acting as current mirror. So only purpose for picking this question was that you need to understand when you can apply the concept of current mirror. You can apply the concept of current mirror only when both of the transistors are working in saturation region. M1 and M2 both should be working in saturation region. M1 is certainly working in saturation region because drain and gate are shorted. So there is no issue with that. But for M2, your Vx value should be greater than 1 volt. Then only it will work in saturation region. Otherwise, it will increase linearly. So here, what is the relation of Ix? What is the relation of Ix? Ix is some constant into VDS minus VGS minus VT. VGS minus VT, that was 1 into VDS. VDS is Vx minus VDS square by 2. So this is the relation with respect to VGS in this region, and in this region your current Ix is 1 milliampere. Say yes or no. Everything is crystal clear, right? Everything is clear that your Vx should be greater than 1 volt, then only it will work in saturation region and current mirror concept can be applied. But before that, it will rise linearly only with respect to Vx. Well and good. Let's this is a very simple question. Let's find the R out value for the case lambda equals to 0 and lambda not equals to 0. Let's take for the case lambda equals to 0. This 5 milliampere current will be gone because this is a DC current source. So that would be gone. This 2 volt will also be shorted. 2 volt will also be shorted. From here you need to see the R out value, right? So if you need to see the R out value, what you are going to do? You are going to put V naught and get I naught out of it. So what will be your R out? R out will be V naught by I naught. But tell me one thing, will there be any current in the MOS? This end of MOS is open circuited. This end of MOS is open circuited. Will there be any current? It will drive 0 ampere current, no? People will say, sir, the current will be, this node is 0, this node is V naught, this node is grounded. So the current in the upward direction would be GM V naught. No, the current will not be GM V naught. The current will be 0 only. Are you getting this point? So if current is 0, so basically the resistance, what do you see is infinity. So resistance you see is V naught by 0 ampere current. So resistance would be infinity. Well and good. Let's see for the second case, that is lambda not equals to 0. So here we have to consider R naught as well. This is grounded. Here you are going to consider R naught. This is your V naught and get I naught out of it. Right? Now if this is your V naught, this will also be V naught. Now if this drives GM V naught current, then will that current flow? Yeah, that current will flow because now this current has some path. That current can flow from here. Did you understand this point? Here if I say that my current is GM V naught, will that current have any path? No. The current will simply see open circuit. If this is open circuit, the current cannot flow. Understood? Now if I apply V naught here, the current has the path. It can flow through R naught. It can flow through R naught. So let's make the R naught a bit far away from this. Yeah, so the current was GMV naught. The current was GMV naught, which can flow like this. And since this is the path, it has to go like this. Now tell me one thing. If this is V naught, the GM V naught current is flowing. It is going. Does it have any path here? No. There is no ground, no other path. So it has to flow like this. Does it have any other path here? Like if there was some ground or any other circuit connected, so the current could go here as well. But there is no other path. So it has to flow here, flow here, flow here. So the current going out is GM V naught and then coming back. So that means I naught will be 0 ampere. Did you understand this point or not? The point here is this. This is the point. From here I naught current is going. This is what I am saying. And then I am saying that here I have I current. If here I have I current, here also I have I current. Then again here also I have I current. Now this I current cannot go anywhere else. This is also I current. So from here I naught current was trying to go in, but I current is flowing completely in the loop. Are you getting this point? If you apply KCL here, what will be the KCL? I naught is inward current minus I naught. This I is inward current minus I, and this I is outward current plus I is equals to 0. So what is the value of I naught? 0 only. So the same thing is happening. This is I naught and complete GM V naught current is flowing in the loop. So basically this I current is only flowing. This I current is only flowing. There is no current coming from outside. So the current that is coming from outside is 0 ampere. There is complete I current is flowing in the loop. The current coming from outside is 0 ampere. So there is no current coming from the outside. So basically your I naught is 0. So if your I naught is 0, then what will be your V naught? What will be your R naught? R naught will be infinity. That's it. Well and good. If GM V naught current is completely flowing in the loop, so I naught doesn't try to go into that, right? So I naught doesn't go into GM V naught, keeps on flowing. So R naught is infinity. Here also R naught is infinity. So this was just an interesting question. It just struck to my mind and I put it here. That's it. Let's move on to our next question. This is also very interesting question. Find the value of I out. All the transistors are identical. All the transistors M, M1, M2, M2, M, M1, M2, M. All the transistors are identical. You need to tell the value of I naught. What does it look like? That this and this are in current mirror. M and N2 seems like they are in current mirror. If they are in current mirror, then what will be the current here? 2 microampere. What does it look like? Like this M and M1 are in current mirror. It seems like that M and M1 are also in current mirror. If they are also in current mirror, then it will say that it will have 1 microampere current. Are you getting this point? If I am saying M and M1 are in current mirror, your I out would be 1 microampere. And if I am saying M and M2 are in current mirror, then your I out would be 2 microampere. Which one will be correct? बात किसकी मानी जाएगी? The one which is working in saturation region, that will be the correct answer. So one of M1 or M2 will not be working in saturation region. One of them will be working in triode region. Did you understand this point? I connected a M transistor. From there 1 microampere current is flowing. So because of the current mirror, M1 will say I will drive 1 microampere current. And here M transistor is having 2 microampere current. So because of the current mirror, M2 will say I will drive 2 microampere current. But there is a condition for current mirror. That is, transistor has to work in saturation region. Transistor has to work in saturation region. Now in one branch, one is saying 1 microampere current and the other guy is saying 2 microampere current. Is that possible? No. That is not possible. In one branch, two currents cannot be possible. So I will write, if M and M2 are in current mirror, then I out is 2 microampere. And if M and M1 are in current mirror, then I out would be 1 microampere, right? I out is equals to 2 microampere and that is equals to 1 microampere, which is not possible. Not possible. This is not possible. That means there will be only one current mirror working. There will be only one current mirror working. There will be only one current mirror working, right? So there will be only one current mirror working. That means one of M1 or M2 will go into triode region. Go into triode region and not in saturation. So one of M1 or M2 will go into triode region. It will not be into saturation region. So which transistor will go into triode region? Tell me. If I say that M and M2 are in saturation, M2 is in saturation region. If I say M2 is in saturation region, then what will happen? M2 will drive 2 microampere current and the same current will be flowing through M1, right? If M1 was in saturation region, then how much current M1 could take? What I am saying, if M1 was in saturation region, then how much current M1 could take? 1 microampere only. Look, I am saying, let's say, let, अरे यार पेज नहीं छोड़ा. Let M2 is in saturation and M1 is in triode. This is what I am going to assume. Then what will happen? I out will be 2 microampere, right? I out will be 2 microampere. Now the same current is flowing through M1. The same current is flowing through M1. But tell me one thing, if M1 was in saturation, what is the maximum current it can take? What is the maximum current it can take? That is 1 microampere, right? Are you getting this point? What did I assume? I assumed M2 is in saturation region and M1 is in triode. If M2 is in saturation region, that means it will drive 2 microampere current because both will be in current mirror, so it will drive 2 microampere current and the same current will be flowing through M1. Now I am saying that M1 is in triode. Even if M1 was working in saturation region, it could have get maximum current of 1 microampere. Now you are saying it is getting 2 microampere current, which is possible? No, it is not possible because M1 can take maximum 1 microampere current. That means M1 can take maximum 1 microampere current, but here even in triode region, it is taking 2 microampere current, which is not possible. So the assumption that you made there, that is wrong. Assumption is wrong. Say yes or no. So the assumption that you made, that is wrong. Why it is wrong? Because it cannot take 2 microampere current. Now what will be the correct assumption then? Then I will assume that M1 is in saturation region and M2 is in triode. I am assuming let M1 is in saturation and M2 is in triode. So this is the second assumption that I am taking. M1 is in saturation and M2 is in triode. So if M1 is in saturation region, then I out will be 1 microampere. Now the maximum current M2 can take is 2 microampere. The maximum current M2 can take is 2 microampere, and it is taking 1 microampere now. So is that possible? Yeah, this is possible. The maximum current M2 can take is 2 microampere, but now it is taking 1 microampere. So that is possible? Yeah, that is possible. So that's why M1 will go into saturation and M2 will go into triode, right? Let M1 is in saturation region and M2 is in triode, then I out would be 1 microampere. I out would be 1 microampere. Same current is taken by M2. M2 can drive maximum current of 2 microampere in saturation. So it can certainly take 1 microampere current in triode region. So your assumption is correct. Correct. So your I out is 1 microampere. And I will tell you one thing, always the answer will be minimum current. Always the answer would be minimum current. Here there is 1 microampere, here there is 2 microampere. So always the answer would be minimum current. Why so? Why minimum current? Because if this can take 1 microampere, if this can take 2 microampere, then certainly it can take 1 microampere. But this is taking 2 microampere, but the maximum it can take 1 microampere only. So that is not possible. Now M1 will say I can't take 2 microampere. That too in triode region. No. In saturation region only I am taking 1 microampere. How I can take 2 microampere in triode region? I cannot take. But if M1 says I go into saturation, so M1 is saying I will drive 1 microampere current. So M1 will ask M2, can you take 1 microampere current? M2 will say, yeah, I can take 1 microampere current because in saturation region maximum I can go up to 2 microampere. So 1 microampere is there in my range. So 1 microampere is there in the range, so it can take 1 microampere current. So I out would be equals to 1 microampere. Say yes or no. Understood? Watch it again if you did not understand it. This is a very good question. 2 microampere current here, 2 microampere current here, 1 microampere current here, 1 microampere current here. Which one will be applicable? 1 microampere. The minimum one. Why so? Because M2 can take 1 microampere current, but M1 cannot take 2 microampere current. Well and good. Understood? Everything is clear. You can read all those statements. You can read this statement as well. You will understand very clearly. Let's move on to our next question. Both of the transistors are identical. You need to find the operating condition of M1 and M2. That means M1 is working in saturation region or linear region. M2 is working in saturation or linear or in cutoff. That you need to tell. So we don't know anything about the operating condition. Let's assume let both M1 and M2 are in saturation. So I am assuming both are in saturation. So both will be driving same current, right? Both will be having same current. So ID of M1 is equals to ID of M2. So mu n Cux W by L, all the transistors are identical. Mu n Cux W by L. VGS minus VT square. What is VGS? Minus VT is 1. VGS minus VT square. That will be equals to mu n Cux W by 12. Mu n Cux W by 12. What is VGS? VGS is 2. Okay, here I wrote ID of M2 and here I am writing ID of M1. Mu n Cux W by L, VGS 2.5 minus V0 minus 1 whole square. Mu n Cux W by L, VGS 2 minus VGS minus VT whole square. So from here, if I solve it, what is the V0 value you will get? 0.5, right? Yeah, V0 value you get is 0.5 because this and this will get cancelled. Then if you put V0 equals to 0.5, it will be 1.5 here, 1. Yeah, so V naught value we are getting is 0.5 volt. So now after V naught value, I will check the operating condition of M1 and M2. So let's check the operating condition of M1 and M2. So this was your M2. So for M2, this was 2.5 volt, this is 3 volt, and this is 0.5, right? 0.5 volt. This is your M2. And what about your M1? M1 gate is at 2 volt, this is grounded, and V naught will be 0.5 volt. Let's check for VDS. VDS is 2.5 volt. What is V overdrive here? VGS minus VT, 2 minus 1, that is 1 volt. So here VDS is greater than V overdrive. So certainly it is in saturation region. Assumption is correct. This is in saturation region. This assumption is correct. What about this? What is VDS here? VDS is 0.5. What is V overdrive? V overdrive is VGS minus VT, 2 minus 0.5. It would be 1.5 volt. So here VDS is less than V overdrive. And if it is less than V overdrive, that means it is working in linear region. Working in linear. Or I should say not in saturation. Not in saturation. So this is the scene. It is not working in saturation region. So the assumption that I made that both M1 and M2 are in saturation region, that is wrong. So now I have to make another assumption. I will make the assumption with respect to the result that I am getting. So I will make the assumption that is, let M1 is in linear and M2. Now this I am doing only to find the value of V naught. Only to find the value of V naught. This is not the final value of V naught. That is wrong. Because V naught value will be something different. I got this V naught value considering M1 and M2 in saturation region, but that is not the correct V naught value. So I will find with respect to the result that I got, I will make the assumption, then I will again check if my assumption was correct or not. So I am assuming M1 to be in linear region and M2 to be in saturation region. Saturation. So again the current will be the same only. There is no doubt about that. ID of M1 would be equals to ID of M2. So what is the ID of M1? That would be mu1 Cux W by M1 is in linear, W by L, VGS minus VT. VGS minus VT is 1 into VDS. What is VDS? VDS is V naught minus VDS square by 2. That would be equals to mu1 Cux W by 12. M2 I have considered to be in saturation region. M2 I have considered to be in saturation region. So what is VGS minus VT? VGS minus VT. VT is 1. VGS minus VT. VGS minus VT. Right? This and this will get cancelled. This 2 will go here. So 2 V naught minus V naught square. 2 V naught. Wait a second. This 2 is going here. 2 V naught minus V naught square. 2 V naught minus V naught square would be equals to 1.5 minus V naught. 1.5 minus V naught. 1.5 minus V naught whole square. So 2 V naught minus V naught square, A square plus B square minus 2AB. A square minus B square. A square plus B square minus 2AB. Okay. So 2 V naught square minus 5 V naught. 2 V naught square minus 5 V naught plus 2.25 is equals to 0. So from here I will get the value of V naught. Let me check that. So two values of V naught I am getting, that is 1.9 volt and 0.6 volt. So I will check again for which value of V naught my assumption is getting correct. Which value of V naught my assumption is getting correct. So let's check that out. So here 3 volt 2.5 volt, 3 volt 2.5 volt, and this is your V naught. And in case of M1, this is your V naught and 2 volt and ground. 2 volt and ground. If you put this value, If you put this value, then what will happen? If you put 0.6 here, this will go into linear region, right? And this is what I assumed, right? M1 to be in linear region. And if I put 1.9 here, if I put V0 equals to 1.9 here, then what will be my VDS? 1.9. What will be my VGS minus VT? VGS minus VT would be VGS minus VT would be 1. So this would be greater. So this would make my assumption to be wrong. If I put V0 equals to 1.9, this would make my assumption to be wrong because I want M1 to be in linear region. So for that, I need to put V0 equals to 0.6 volt. So if I put V0 equals to 0.6 volt, this is the correct one. If I put V0 equals to 0.6 volt, this is 0.6 volt. So here this is certainly working in saturation region and this is working in linear region. My answer is this. So assumption is also correct. So basically what is the answer? M2 is in linear. Sorry, M2 is in saturation and M1 is in linear. And V0 value is 0.6 volt. Although in the question they did not ask the V0 value. So here only your question will be completed. Here only your answer would be completed if they just ask the operating condition. If they are only asking the operating condition, here only your answer would be completed. That your M2 is working in saturation region and M1 is working in linear region. But if you need to find the value of V0, then you need to do this analysis as well. You can find the value of V0 as well. Right? What did you understand? When I was doing this analysis, I got to know that my M2 is working in saturation region, but M1 is working in linear region. First, I assumed both of them are working in saturation region. So that was wrong. From there, I got the V0 value to be 0.5, but that was also not correct. V0 value 0.5 was not correct. Then I got to know that M2 is in saturation, M1 is in linear. Then I applied this condition, and from there I got to know V0 value will be 0.6 volt, and for 0.6 volt, both of my condition are being satisfied. Both of the condition are being satisfied, then there is no issue about that. Well and good. Also, one more thing. In this example, you can directly see that M2 will certainly be in saturation region. Why so? Because what is VD? VD is 3. What is VG? 2.5. VD is 3. So what will be VDS? VDS will be 3 minus VS. What will be your VGS? 2.5 minus VS minus VT. What is VT? 1. So this value will always be greater than that because VS and VS will get cancelled. So 3 is always greater than 1.5. So certainly M2 will be in saturation region. That's for sure. So you just needed to check for M1. So first we consider M1 to be in saturation. That was wrong. M1 was not in saturation region. Then I got to know that M1 will be in linear region. So for that I applied this voltage. I got this voltage and then I could get my final answer. So V0 was 0.6 volt. I hope you have solved this question on your own. Okay, so yeah, let's move on to the next problem. This is the problem based on current mirror only. First, what you need to find, that only we will see. You need to find the small signal voltage gain. There was one error in this question is that here they are giving the RDS value. And then here they are saying that ignoring the channel length modulation. You can't ignore the channel length modulation, no? If you are giving the R0 value, then how you can ignore the channel length modulation? So this was a small error from the people who made this question. So there was a small error. This question was in GATE 2019 as far as I remember. So this was the error there. But yeah, let's solve this problem. So what we are going to do, we are going to replace this one with something and this one also with something. So let's make the circuit on the next page and then we will start solving it. Well and good. This will be the circuit, right? All the transistors are identical only. Okay, forget about that. Okay. So what let's just call this potential as V1 and this potential as V2. This potential is V2. So if this is V1, this will also be V1. So from V1 to ground, what do you see? From V1 to ground, what do you see? V1 to ground, I see some 1 by Gm, 1 by Gm, 1 by Gmp I can write, parallel with R naught P. Are you agreeing to this point? From here, what will be the current? Gm V1. And if there is R naught P as well, if there is R naught P as well, there will be R naught P as well, right? There will be R naught P as well here. So from V1 to ground, what do you see? From V1 to ground, you see R naught P, and from V1 to ground, you see one current as well. That is GMP V1. So basically, from V1 to ground, you see two components, V1 by R naught P and V1 into GMP. So two components you see. So what will be the resistance? 1 by GMP parallel with R naught P. And this you see from V1. Right? This node is grounded. And then, okay, let's talk about V2. This was your V1. Between V1 and V2, what do you see? V2 is simply ground only. V2 is ground only. V2 is ground only, right? V2 is ground only. This is your V1. Between V1 and V2, what do you see? From V1 to ground, I see 1 by Gm. From source side, from V1 to ground, I see 1 by Gm, and then one more resistance, that is R naught P. So from V1 to ground, I see 1 by GMP. From V1 to ground, I see R naught P. Ground is V2 only. So this potential is V2 only. So from V1 to ground, I see 1 by GMP parallel with R naught P. Well and good, right? And then there is this V in somewhere here. And you need to calculate this V out. Now what is the current here? 0 ampere. That means what will be the current flowing here? It has to be 0 ampere, right? It has to be 0 ampere. So all of those resistors are having 0 ampere current. That means this will be shorted. Say yes or no. So this node will be shorted. So what will be the final circuit? Look, I have seen few teachers, they just tell them, if you see gate and drain are shorted, then just replace it with the current source and take this node to ground. But this is absolutely wrong. Directly you can't do it. You always have to see some resistance. In the next assignment, I will pick some questions where you cannot replace it with ground. I will deal some questions there. Then these shortcuts and everything will be gone. So always see the resistance. From V1 to ground, I see this much of resistance. From here to here, I see this much of resistance. What is the current? 0 ampere current. So this will be shorted. Very simple. If you just remember some shortcut and all those things, you will be messing it up in the examination. I have seen some like people saying that, okay, this will be a current source, this will also be a current source, so simply make this one as ground. If there is a current source there, that will be a current mirror, so simply make this ground. I will deal some example in the next lecture. There, this will not be grounded. It will come in action. Because what I am going to do, I am going to apply V in here only. So if I am going to apply V in here only, then V in will see some resistances. Are you getting this point? So that's why I am again and again focusing on the resistance part. I know this will be grounded. I can directly say this will be grounded. But why I am making this circuit again and again? Because that is important. Right? So eventually this is becoming grounded. And here you are applying V. And did you understand the sign convention? This is NMOS. Sorry, this is PMOS. And this is your NMOS. I hope you understood the sign convention, because in the lecture I taught you. But this is not the general way. This is the PMOS. Okay. And this was the NMOS. Well and good. So I made this sign convention here. PMOS, 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 and then NMOS. And this is your V out. Now what will happen? Here VGS is gone. Here VSG is gone. So only this will be replaced with R naught P. This will be replaced with R naught P. So what will be your final circuit? This is being replaced with R naught P. This was your V naught. You understood it, right? VSG is gone, so this will be replaced only with R naught P. This is grounded, and from V naught to ground, here you are having R naught N. This is grounded, and this is your V in. So simply, what will be your V naught by V in? From V naught to ground, you see R naught P. From V naught to ground, you see R naught N. So from V naught to ground, you see R naught P parallel with R naught N. R naught P parallel with R naught N. Well and good. So what is the current here? The current here is GMN V in. So V naught by V in would be minus GMN R naught P parallel with R naught N. That's it. This is the final answer. What are the values you are having? You are having the value of R naught P and R naught N, because all are having the same output impedance. So it is given that R naught P is equals to R naught N is equals to 6 mega ohm. It is given in the question. So only task is to find GMN. Your task is to find what will be the value of GMN. This is the task. So how you can find the value of GMN? What are the values given to you? Mu n Cux W by L value is given. Mu p Cux W by L value is given. Okay. Then based on that, what you can find? You need to find GMN. So for GMN, so this would take some, this is potential 0. If I know the potential of this point, then I will get to know the VSG value here, right? And then I can proceed. Okay, yeah, so I thought about it. What do I need? I need the value of GMN, right? I need the value of GMN. What is the formula of GMN? What is the formula of GMN? There are a lot of formula of GM, but let's just say if I apply this formula, root 2 mu n Cux W by L, because I have the value of mu n Cux W by L into ID. This formula if I apply, I can apply this formula, right? So for that I need the current in NMOS. I need IDN. What do I need? I need IDN, the current in NMOS. So let's draw the circuit once again. Do I have the circuit? I can just copy this one. Now I am doing the DC analysis, because you need the GM value, and GM value will be taken by the DC analysis only. So I am doing the DC analysis now. This was your 4 volt, right? This was your 4 volt. So I need the current here. All these are AC signal. You don't need to care about those signal. Here you cannot apply root 2 ID upon VGS minus VT, because you don't know the value of VGS minus VT. Do you know the value of VGS minus VT? No. Because they haven't given the DC supply here. There is certainly some DC bias. But they did not show it here. They did not show the DC bias here. So there is certainly some DC bias connected here. Certainly some DC bias is there, but you don't know that value. So you have to apply that current formula only. Root 2 mu n Cux W by L. So you need IDN. So if I find the current in this NMOS, in this Pmos, then the same current will be flowing through NMOS as well. So my target is to find the current in this NMOS. If I need to find the current in this NMOS, I need to know the potential of this one. So if I need to know the potential of this one, then I can use the current in these branches. Well and good. What do I need? I need this current. For this current, I need this current. If I need this current, I need this potential. If I need this potential, I can use it somewhat here. So what do I know? That in both of the transistor, the current would be same. In both of these transistors, the current would be same. So what that current would be? Let's just say this potential is V. So this potential will be V, and this is grounded only. So this potential will be grounded only. So what I can write is that mu p Cux W by 2L. Both of the transistors are working in saturation region, because drain and gate are shorted. Mu p Cux W by L would be equals to VSG minus VT. Source to gate, VSG minus VT whole square. That would be equals to mu p COX W by L VSG minus VT whole square, right? So from here, what do you get to know? 3 minus V is equals to V minus 1. So V voltage you are getting is 2 volt. Let's call it VA. Better, we should call it VA. 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 So VA voltage you are getting is 2 volt. This potential is 2 volt. This potential is 2 volt. Now, since all these are working as an amplifier, so certainly this will be in saturation region. Say yes or no. Certainly this MOS will be in saturation region. Are you getting this point? All these MOSes are working as an amplifier, so this MOS will certainly be in saturation region. So for that, let's call this current as IDP. So what that IDP would be? What that IDP would be? So current IDP would be mu P COX W by 2L VSG minus VT whole square. So, and here you will say, sir, why aren't you considering this 1 plus lambda VDS? I am considering lambda to be very small. Because RDS value is very high. RDS value is in mega ohms. RDS value is in mega ohms. And here also they have written that ignore the effect of channel and modulation. So I am considering lambda to be very small. So here I am writing, I will not consider 1 plus lambda VDS. Lambda to be very small. So I am ignoring that lambda factor. So mu P COX W by 2L. Mu P COX W by 2L. So 300 micro by 2. It would be 300 micro by 2. What is VSG? VSG would be 4 minus 2. That would be 2. What is VT? VT value is also given. VT value is 1. 1. So IDP I am getting is 150 microampere. Right? This is the IDP I am getting. That would be equals to IDN. So what will be your GMN now? That would be root 2 into mu n COX W by L. Mu n COX W by L. That is also 300. Root 2 into 300 micro. Root 2 into mu n COX W by L into ID. And ID is 500 micro. 150 micro. So what will be your GMN? That would be 300 micro Siemens. This will be your GMN. So what will be your gain? What was your gain? Gain was minus GMN into R0 P parallel with R0 N. So R0 P is equals to R0 N. That was given equals to 6 mega ohm. So GMP is minus 300 micro into 6 mega ohm parallel with 6 mega ohm. So minus 3 into 10 to the power minus 4 into 3 mega ohm 10 to the power 6. So your gain is minus 900. Basically your gain is becoming minus 900 volt per watt. So this is the gain you are getting. This is the final answer. This was asked in GATE 2019, but it was a simple question only. You will be replacing with short circuit. So here your gain is simply minus GMN R0 P parallel with R0 N. So GMN value you need to find. For finding the GMN value, you need the current in the NMOS. For the current in NMOS, you need to find the current in PMOS. So for the current in PMOS, you need the source potential. Sorry, you need the gate potential. For gate potential, you can use the current in this one. So both of them are having the same current. So I go to know the potential here. That will be 2 volt. If I know the potential here, then I can know the current in the PMOS. So I know the current in PMOS, that was coming out to be 150 microampere, and the same current is flowing through the NMOS as well. So same current is flowing through the NMOS. I could find the value of GMN. So GMN value I am having, that is 300 microsiemens, and output resistance was 3 mega ohm, because 6 mega ohm parallel with 6 mega ohm would be 3 mega ohm. So 3 mega ohm into 300 micro. So answer would be minus 900 volt per volt. That would be your final answer. Well and good. Let's solve the last question of this assignment. This will be the last question of the assignment. So here V1 is 0. This is 0. this is grounded, and V2 is equals to VDD. If this is grounded, then how much current it will drive? 0 ampere current. Say yes or no. If this is grounded, then if gate is grounded, it will not drive any current. So if this is open-ended, this will also not drive any current, right? So it will get 0 ampere current. It is having 0 ampere current. This is 1 milliampere current, and WIL is 2 here, and here WIL is 3. So what will be the current here? The current here would be 3 by 2 into 1. That means 1.5 milliampere current. Now this side is having 0 ampere current. This complete side is having 0 ampere current. So I will make it something like this. This complete side is having 0 ampere current. So this complete 1.5 microampere current would be flowing here. Milliampere. 1.5 milliampere. Now this is having W by L ratio of 5. This is having W by L ratio of 10. Does that matter? That if this is having 1.5 milliampere current, then this will have 3 milliampere current. Is that so? No, because they are connected in series. They are connected in series. So if this is having 1.5 milliampere current, this will also have 1.5 milliampere current only. This will also have 1.5 milliampere current. Now WIL ratio is 10 here and 40 here. So what will be the current here? 40 by 10 into 1.5 milliampere. So that would be what is 15 choke? Yeah, 6 milliampere. So the current would be 6 milliampere, right? So understood this problem? 1 milliampere came, 3 by 2, 1.5 milliampere. If this W by L here it is shorted, so it is driving 0 ampere current. So 1.5 milliampere current completely will be flowing from here. Then 1.5 milliampere current, since they are connected in series, both of the transistors are connected in series. So since they are connected in series, so both of them will drive the same amount of current. So both of them will have 1.5 milliampere current. So from 1.5, 4 times of current will be flowing in the final MOSFET. So 1.5 into 4, that would be 6 milliampere current. So output current is 6 milliampere. That's it. Very easy question. 1.5, no current here. 1.5, 4 times of that, 6 milliampere. That's it. No issue with that. So here we are done with our 8th assignment. This was the 8th assignment as far as I remember. So this was not that much of tough assignment. This was basic assignment only. But next assignment is going to be fusion special. Okay, so we are going to deal very conceptual questions. Only 5 questions are there, but they will be very conceptual. It will clear your concept in very depth. Also, educators can also watch this video, because I'm pretty sure here they will understand a lot of new concepts. So yeah, everyone will watch these videos. Watch this video. It can be around 2 hours or 2.5 hours. It can be around 3 hours as well. But this will be very conceptual. So yeah, this is the first question. I am showing you the question. You can try it on your own. This is the second one. This seems like an easy question, but I will tell you an intuitive method to solve these kind of problems. Third one. Fourth. And the fifth one. These are the 5 questions that we are going to solve, and all those questions are very intuitive. Sixth question, one more question I can frame. So there can be 6 questions. That question I can frame. So these 6 questions we are going to solve will be very intuitive and will be very interesting. So we will deal those questions, and then we will be complete. The part will be completed. Okay. So yeah, let's meet in the next lecture. Okay. Thank you.